So in this lecture, we're talking about arrays and linked lists. In this video, we're going to talk about arrays. So here's some examples of declarations of arrays in a couple of different languages. Along with, we can see the one-dimensional array laid out with 5 elements in it, and then a two-dimensional array with 2 rows and 5 columns. So what's the definition of an array? Well, we've got basically a contiguous array of memory. That is one chunk of memory. That can either be on the stack or it can be in the heap. It doesn't really matter where it is. It is broken down into equal-sized elements. And each of those elements are indexed by contiguous integers. All 3 of these things are important for defining an array. Here, in this particular example, we have an array whose indices are from 1 to 7. In many languages, the same indices for this particular array would be from 0 to 6. So that would be 0-based indexing. But 1-based indexing is also possible in some languages, and other languages allow you to actually specify what the initial index is. What's so special about arrays? Well, the key point about an array is we have random access. That is, we have constant time access to any particular element in an array. Constant time access to read, constant time access to write. How does that actually work? Well, basically what that means is we can just do arithmetic to figure out the address of a particular array element. So the first thing we need to do is start with the address of the array. So we take the address of the array, and then we multiply that by, first, the element size. So this is where the key part that every element was the same size matters. So that allows us to just do a simple multiplication. Rather than if each of the array elements were of different sizes, we'd have to sum them together. And if we had to sum together n items, that would be order n time. So we take our array address, we add to it the element size times I, which is the index that's of interest, minus the first index. Okay? If we're doing 0-based indexing, that first index isn't really necessary. I like this example because it really shows the more general case where we do have a first index. So let's say, for instance, we're looking at the address for index 4. We would take 4 minus the first index, which is 1, which would give us 3, multiply that by whatever our element size is, and then add that to our array address. Now, of course, we don't have to do this work. The compiler or interpreter does this work for us. But we can see how it is that it works in constant time. Many languages also support multi-dimensional arrays. If not, you can actually kind of roll your own through an example I'll show you here where you do your own arithmetic. So here let's say that the top left element is at index 1, 1. And here's the index 3, 4. So this means we're in row 3, column 4. How do we find the address of that element? Well, first off, what we need to do is skip the rows the full rows that we're not using. So that is, we need to skip 2 rows, or skip 3, which is the row index, minus 1, which is the initial row index. So that gives us 2 times 6, or 12 elements we're skipping for those rows, okay, in order to get to row 3. Then we've got to skip the elements before 3, 4 in the same row. So there are 3 of them. How do we get that? We take the column index, which is 4, and subtract it from the initial column index, which is 1. So this basically gives us 15. 6 for the first row, 6 for the second row, and then 3 for the third row before this particular element. We take that 15 and multiply it by our element size, and then add it to our array address. And that will give us the address of our element 3, 4. Now we make kind of a supposition here, and that was that the way this was laid out is we laid out all the elements of the first row, followed by all the elements of the second row, and so on. That's called row major ordering, or row major indexing. And what we do here is basically we lay out 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and then right after that in memory, 2, 1, 2, 3, 2, 4, 2, 5, 2, 6. So the column index is changing most rapidly as we're looking at successive elements, and that's an indication that it's row major indexing. We could lay out arrays differently, and some languages or compilers actually do that, where they would lay out each column in order. So you'd have the first column, then the second column, then the third column. And so that then, the successive elements would be 1, 1, 2, 1, 3, 1, followed by 1, 2, 2, 2, 3, 2, and so on. So there we see that the row index is changing most rapidly. And this is called column major ordering. How long does it take to perform operations? We already said to read any element is order 1, and to write any element is order 1. That is a standard feature of arrays. What happens if we want to add an element at the end of an array? So let's say we have allocated 7 elements for an array. We're only using 4 of them. Okay, so we have kept track that we're using 4, and we want to add a 5th element. And again, there's room for 7. Then all we need to do is just add it. So, and then update the number of elements that are in use. That's an order 1 operation. If we want to remove the last element as well, that's an order 1 operation because we just update the number of elements that are in use. And so that's an order 1 operation. Where it gets to be expensive is if we want to, for instance, remove the first element. So we remove the 5 here, and what we've got to do then, we don't want to have holes left in it, so we need to move the 8 down, move the 3 down, move the 12 down. That's an order n operation. Same thing would happen if we wanted to insert at the beginning. So we would need to move the 12, move the 3, and move the 8 to make space for our new element. So that also would be order n. And if we want to add or remove somewhere in the middle, again, that's order n operation. If we want to add exactly in the middle, we have to move in over 2 items, which is order n. Same thing for removal. So arrays are great if you want to add or remove at the end, but it's expensive if you want to add or remove in the middle or at the beginning. However, remember our huge advantage for arrays is that we have this constant time access to elements to either read or write them. In summary then, array consists of a contiguous area of memory, because if it were non-contiguous, then we couldn't just do this simple arithmetic to figure out where we're going. We have to have equal size elements, again, so our arithmetic works, and indexed by contiguous integers, again, so our arithmetic works. We have constant time access to the element, constant time to add or remove at the end, and linear time to add and remove at any arbitrary location. In our next video, we're going to talk about linked lists. Now let's talk about linked lists. So linked lists, it's named kind of like links in a chain, right? So we've got a head pointer that points to a node that then has some data and points to another node, and eventually points to one that doesn't point any farther. So here in our top diagram, we show head points to the node containing 7, points to the node containing 10, points to the node containing 4, points to the node containing 13, doesn't point anywhere. How this actually works is that a node contains a key, which in this case is these integers, and a next pointer. The diagram below shows more detail of what's going on. So head is a pointer that points to a node, and that node contains 2 elements, the value 7, and then a pointer that points off to the next node that contains a key 10, and a pointer that points off to the next node 4, points off to the next node 13. 13's next pointer is just nil. What are the operations that can be done on a linked list? Okay, there are several of them. And the names of these sometimes are different in different environments and different libraries, but normally the operations provided are roughly these. So we can add an element to the front of the list, and that we're calling push front. So it takes a key, adds it to the front of the list. We can return the front element of the list, we're calling that top front, or we can remove the front element of the list, called pop front. These same things that we can do at the front of the list, we can also do at the end of the list. With push back, later on in a later module we'll actually use the word append for that, or top back, or pop back. These seem uniform in there, but there is a difference in that the runtimes are going to be different between those, and we're going to talk about that. You can find whether an element is in the list, and that's as simple as just running yourself down the list looking to find a matching key. You can erase an element, and then again, run yourself down the list till you find a matching key, and then remove that element. So these latter ones are both order n time. Is the list empty or not? That's as simple as checking, is the head equal to nil? We can add a particular key. If we want to splice in a key into a list, we can actually add in a key either before a given node or after a given node. So let's look at the times for some common operations. We've got here our list with 4 elements in it, 7, 10, 4, and 13. Now we go ahead and push an element to the front. So we push 26 to the front of the list. So the first thing we do, create a node that contains the 26 as its key. And then we update our next pointer of that node to point to the head, okay, which is the 7 element. And then update the head pointer to point to our new node. And that's it, we're done. So it's order 1. Allocate, update one pointer, update another pointer, constant time. If we want to pop the front element, it's clearly finding the front element is very cheap here, right? We can just look at the first element and return it. So top front is order 1. Pop front is also, turns out, going to be order 1. First thing we're going to do, update the head pointer. Then remove the node. That's order 1 operation. If we want to push in the back, okay, and we don't have a tail pointer, we're going to talk about a tail pointer in a moment, then it's going to be a fairly expensive operation. We're going to have to start at the head and walk our way down the list until we get to the end and add a node there. So that's going to be order n time. Similarly, if we want to top back or pop back, we're going to also have to start at the head, walk our way down into the last element. Those are all going to be order n time. If we add a tail pointer, some of these have become simpler. Okay, so we're going to have both a head pointer that points to the head element and a tail pointer that points to the tail element. So that way getting the first element is cheap, getting the last element is cheap. Let's look at what happens when we try and insert when we have a tail. We allocate a node, put in our new key, and we then update the next pointer of the current tail to point to this new tail, and then update the tail pointer itself. Order 1 operation. Retrieving the last element, so a top back, is also an order 1 operation. We just go to the tail, find the element, return the key. If we want to pop the back, however, that's a little bit of an expensive operation. Okay? We are going to need to update the tail to point from 8 to 13. So we're at 8 right now, we want to go to 13. The problem is, how do we get to 13? Okay? We don't have a pointer from 8 to 13. We have a pointer from 13 to 8. And that pointer doesn't help us going back. So what we've got to do is, again, start at the head, walk our way down until we find the 13 node that then points to the current tail. And then update our tail pointer to point to that. And then update that next pointer to be nil. So that's going to be, and then we can remove that old node. So that's going to be an order n operation, because we've got to walk all the way down there. Okay? Because even though we have the tail pointer, we don't have the next to the tail pointer. We don't have the next to last element. The head is different. Because our pointers point this way, if we have the head, it's also cheap to get the second element, right? And one more to get the third element. But the tail pointer doesn't help us get to the next to the last element. Let's look at some of the code for this. So for push front, we have a singly linked list. We're going to allocate a new node, set its key, set its next to point to the old head, and then we'll update the current head pointer. If the tail is equal to nil, that meant that before the insertion, the head and the tail were nil. It was an empty list. So we've got to update the tail to now point to the same thing the head points to. Popping the front? Well, if we're asked to pop the front on an empty list, that's an error. So that's the first check we do here. And then we just update the head to point now to the head's next. And just in case that there was only one element in the list, and now there are no elements, we check if our new head is nil, and if so, update our tail to also be nil. Pushing in the back, allocate a new node, set its key, set its next pointer, and then check the current tail. But if the current tail is nil, again, it's an empty list, update the head and the tail to point to that new node. Otherwise, update the old tails next to point to our new node, and then update the tail to point to that new node. Popping the back, more difficult, right? If it's an empty list and we're trying to pop, that's an error. If the head is equal to the tail, that means we have one element, so we need to just update the head and the tail to nil. Otherwise, we've got to start at the head and start working our way down, trying to find the next to last element. When we exit the while loop, P will be the next to last element, and we then update its next pointer to nil and set our tail equal to that Adding after a node, fairly simple in a singly linked list. Allocate a new node, set its next pointer to whatever node we're adding after, to its next. So we sort of splice in, and then we need to update the node pointer, the one we're adding after, so that it points now to our new node. Okay? And just in case that node we're adding after was the tail, we've got to now update the tail to that new one. Adding before, we have the same problem we had in terms of pop back, in that we don't have a link back to the previous element. So we have no way of updating its next pointer other than going back to the beginning of the head and moving our way down until we find out. So add before would be an order in operation. So let's summarize what the costs of things are. Push front, order 1. Top front, pop front, all order 1. Pushing the back, order n, unless we have a tail pointer, in which case it's order 1. Top back, order n, again, unless we have a tail pointer, in which case it's order 1. Popping the back, order in operation, with or without a tail. Finding a key is order n. We just walk our way through the list trying to find a particular element. Erasing, also order n. Checking whether it's empty or not is as simple as checking whether the head is nil. Adding before, order n, because finding the previous element takes order n, because we've got to walk away from the head to find it. Add after, constant time. There is a way to make popping the back and adding before cheap. Right? Our problem was that although we had a way to get from a previous element to the next element, we had no way to get back. And what a doubly linked list says is, well, let's go ahead and add a way to get back. So we'll have 2 pointers, forward and back pointers. That's the bidirectional arrow we're showing here conceptually. And the way we would actually implement this is with a node that adds an extra pointer. So we'd have not only a next pointer, we'd have a previous pointer. So this shows, for example, that the 10 element has a next pointer that points to 4, but a previous pointer that points to 7. So at any node, we can either go forward or we can go backwards. So that means if we're trying to pop the back, that's going to work pretty well. What we're going to do is update the tail pointer to point to the previous element, because again, we could get there in order 1 operation, and then update its next pointer to be nil, and then finally remove the node. So that's order 1. So if we have a doubly linked list, it's slightly more complicated, our code, because we've got to make sure to manage both prev pointers as well as next pointers. So if we're pushing something in the back, we'll allocate a new node. If the tail is nil, which means it's empty, then we just have a single node whose prev and next pointers are both nil, and the head and tail both point to it. Otherwise, we need to update the tail's next pointer to this new node, because we're pushing at the end, and then go update the prev pointer of this new node to point to the old tail, and then finally update the tail to this new node. Okay. Popping the back, also pretty straightforward. We're going to again check to see whether this is first an empty list, in which case it's an error, a list with only 1 element, in which case it's simple. Otherwise, we're going to go ahead and update our tail to be the prev tail, and then update the next of that node to be nil. Adding after, fairly simple. Again, we just need to maintain the prev pointer. But adding before also now works, in the sense that we can allocate our node, our new node, and its prev pointer will be the prev pointer of the existing node we're adding before. Okay, so we splice it in that way, and then we'll update the next pointer of that previous node to point to our new node. And finally, just in case we were adding before the head, we need to update the head. So in a singly linked list, we saw the costs of things. The working with the front of the list was cheap. Working with the back of the list with no tail was all linear time. If we added a tail, it was easy to push something at the end, easy to retrieve something at the end, but hard to remove something at the end. By switching to a doubly linked list, removing from the end the pop back becomes now an order 1 operation, as does adding before, which used to be a linear time operation. One thing to point out as we contrast arrays versus linked lists. So in arrays, we have random access in the sense that it's constant time to access any element. That makes things like a binary search very simple, where we start searching in the middle and then tell if we have a sorted array, and then can decide which side of the array we're on and then go to one side or the other. For a linked list, that doesn't work. Finding the middle element is an expensive operation because you've got to start either at the head or the tail and work your way into the middle. So that's an order in operation to get any particular element. Big difference in between that and an array. However, linked lists are constant time to insert at or remove from the front. Unlike arrays, right? We saw with arrays, if you want to insert from the front or remove from the front, it's going to take you order n time because you may have to move a bunch of elements. If you have a tail and doubly linked, it's also constant time to work at the end of the list. So you can get, add, and remove from there. It's linear time to find an arbitrary element. The list elements are not contiguous as they are in an array. You have separately allocated locations of memory, and then there are pointers between them. And then with a doubly linked list, it's also constant time to insert between nodes or to remove a node. So now we're going to start talking about two very important data structures, stacks and queues. In this video, we're going to talk about stacks. So what is a stack? It's an abstract data type, and here are the operations we have. We can push a key. So we've got a collection of values, and we can push it. We can find the most recently added key with top, and we can pop, which removes and returns the most recently added. So the way to think of it is as if you have a stack of books. You can put a book on top of the stack, or you can take a book from the top of the stack. But you can't take the element at the bottom of the stack of books without taking off all of the previous elements. So it's really pretty simple. You can push items on, you can find where the top one is, you can pop off the top one, and you can intermingle these operations. Okay? The last one you can find is it empty? So do we have an empty stack? This turns out to be really useful for lots and lots of things where you need to keep track of what has happened in this particular order. Let's look at an example. So let's say we've got a balanced brackets problem. So here we have a string, and it has left parens, right parens, left square brackets, and right square brackets. And we want to return whether or not that string of parentheses and square brackets, whether they're balanced. Okay, balanced meaning there's a matching left paren for every right paren, and they're in the right order, and they don't cross over. Let's look at some examples of balanced. So the first string here, left paren, square bracket, matching square bracket, matching right paren, square bracket, matching square bracket, right paren, left paren, matching paren. Balanced. The second one, also balanced. The unbalanced one, for example here, we have a left paren with no matching right paren, assuming that the two parens on the right side are matching themselves. The square brackets match, but then we've got an unmatched right bracket. Or in the last case, we've got a square left bracket and a square right bracket, but the problem is they're in the wrong order. It's a square right bracket followed by the square left bracket. Okay, so how do we keep track of that? And the problem is, in some cases, we have to kind of keep track of a lot of information. So for instance, in the second example here, we've got our opening left paren doesn't get matched for the right paren for quite a while. There's a lot of intervening stuff. And we have to sort of keep track that we've got a left paren whose right paren we need to match, even as all this other stuff happens. And it turns out a stack is a good way to keep track of that. So here's what we'll do. We'll create a stack, and then we'll go through every character in the string. If we have an opening paren or an opening square bracket, we'll go ahead and push it on the stack. So the stack is going to represent the parens that are still open, the parens and brackets which have yet to be matched, and the order in which they need to be matched. So the outermost ones will be at the bottom of the stack, and the last one we saw, the innermost one, will be at the top of the stack. Then, if it's not one of these opening ones, then if our stack is empty, that's a problem, because basically we've got a closing paren or bracket, and there's no matching element. So if the stack is empty, no, we're not balanced. Otherwise, we'll pop the top element off, and then we'll check and see, does it match that element from the stack? Does it match the character we've got? So if the top was a left paren, did we just read a right paren? If so, great. They match, and now those two match. The next one we need to match is still the newly top one on the stack. Or similarly, if we have a square bracket on the stack and a square bracket we read, those match as well. If they don't match, then we've got a problem, right? If we've got a right paren on the stack and a left paren on the stack and a right bracket that we just read, those don't match, for example. So then we return false. Once we've run through all of the strings, we're matched, right? Well, no, not necessarily. Imagine we had the string left paren, left paren, left paren. We'd go through, we'd push a left paren, we'd push a left paren, we'd push a left paren, and then we'd be done. We wouldn't have returned false. But it's no good because we didn't actually match what's on the stack. So once we go through all of the characters in the string, then we've got to actually check and make sure, is our stack empty? Did we successfully match everything? This is only one example of the use of stacks. Stacks are used in lots of other places. They're used for compilers. They're used in a lot of algorithms that you'll be seeing throughout this course. So how do you actually implement a stack? Well, let's look. You can implement a stack with an array fairly easily. So allocate an array of some maximum stack size. Right? So in this case, we decided it's 5, just for the sake of example. And we're going to keep a variable, which is the number of elements that are actually in the stack. When we push, so in this case, we're going to push A, we're going to go ahead and put it at the end of the array we've got so far. So for whatever elements we have, we'll append it to those. So in this case, we'll put it at the beginning of the array because we haven't used any elements. And we'll keep track. The number of elements is 1. Okay. We push B, we'll put it at the next spot. And now our number of elements is 2. Fairly straightforward, right? We're just appending to the array. And these are clearly order 1 operations. What's the top element? Well, that's really simple. If the number of elements is 2, that means we need the second element from the array, which in this case is B. Again, a constant time operation. We push C, our number of elements is 3. And now let's say we pop. Well, what do? We need to go get the third element, which is C, and erase it, and then adjust num element so it's now 2. Now we can push an element, push another element, push a fifth element, and now if we try to push again, that's an error, right? Because we don't have any more space, so that wouldn't be allowed. Is it empty? No. How do we know? Because the number of elements is greater than 0. Again, an order 1 operation. And now we can start popping, which will be returning the appropriate element of the array based on the num elements value, and keep popping until we get down to no elements. Okay? If we're at no elements and we ask it's empty, yes, that's true. We can also implement a stack with a linked list. So one disadvantage we saw, one limitation of the array is that we have a maximum size based on the array we initially allocated. Okay? But all the operations are order 1, which is good. The other potential problem is that we have potentially wasted space. So if we allocated a very large array, okay, to allow a possibly large stack, but we didn't actually use much of it, all the rest of it is wasted. If we have a linked list, what we do then is every element in the list, of course, will represent a particular element in the stack. And so we'll push A. And then if we push B, we're going to go ahead and push B at the front. So basically pushes will turn into push front. If we want to get the top element, just get the head element. Okay, so top will really just be top front. We can keep pushing at the front, or popping. All of those are order 1 operations. We can keep pushing, and the nice thing about this is there is no a priori limit as to the number of elements you can add. As long as you have available memory, you can keep adding. There's an overhead though, right? In the array, we have each element size is just big enough to store our key. Here, we've got the overhead of storing a pointer as well. On the other hand, there's no wasted space in terms of allocated space that isn't actually being used. So we keep pushing. Is it empty? No, because the head is not nil. Okay. And then we can go ahead and pop. So if we had a linked list, it's very simple to implement the linked list operations in terms of the linked list operations push becomes push front, top becomes top front, and pop, which is supposed to both return and pop the top element, can become a combination of a top front followed by a pop front. Empty is just empty. Okay, we keep popping, and then eventually we pop the last element, and now if we ask whether it's empty, the answer will be true. Okay, so that's our stack implementation. Stacks can be implemented with either arrays or linked lists. I've talked a little bit about the pros and cons of each of those. The linked list has a fixed amount of overhead. That is, for every element you are pushing, you have an additional pointer. For arrays, you have potentially space that you've over-allocated basically to allow for a stack to grow to maximum size. For arrays, stacks do have a maximum size. For linked lists, they don't. Each stack operation is constant time for either one of these implementations. Sometimes we know stacks as LIFO queues. LIFO meaning last in, first out. The last one that was inserted is the first one that comes out. This reminds me sometimes of also what's known as GIGO, garbage in, garbage out. That if you input garbage into a system, you get garbage out. But this, of course, is different. So that is stacks. In the next video, we're going to go ahead and look at queues. Thanks. Now let's talk about queues. So a queue has some similarity with stack, but it's in a fundamental way different. So it's an abstract data type, and these are the operations that it has. You can enqueue a key, and it adds the key to the collection. And then when you dequeue, that gives you back a key and removes it from the queue. It removes and returns the least recently added key, rather than, in the case of a stack, the most recently added key. So that's the fundamental difference. If you think about queues as like queuing up in line or waiting in line, this is a first come, first serve situation. So the longer you've been waiting in line, so the longest person waiting in line is the next person to be served. If that makes sense. So you can imagine if you had a grocery store that had a stack that it used for serving people, people would be pretty annoyed, right? Because the person who just arrived, you've been waiting in line 10 minutes, a person just arrives, they get served before you do. That would not make you happy. So queues are very useful, for instance, for things like servers, okay, where you've got a bunch of operations coming in and you want to service the one that's been waiting the longest. The other operation is you can find out whether a queue is empty or not. Okay? So these are often called FIFO, first in, first out, and this distinguishes them from stacks, which are LIFO, last in, first out. Okay? First in, first out, or first come, first serve. Same thing. How can you implement a queue? Well, one way is with a linked list, where you have a head and a tail pointer. So let's say we start out with an empty linked list. We can go ahead and enqueue, and what we're going to do basically in an enqueue is we are going to push to the back of the linked list. So that's how we'll implement enqueue. So here we enqueue A, it's now at the back of the linked list. If we enqueue B, it's going to be then added again at the end of the linked list. Is it empty? No. How do we know it's not empty? Well, the simplest thing is we would just call to the underlying list implementation and say, hey list, are you empty? It would say no. And so empty for the queue is no. We know it's really happening just by checking whether the head is nil or not. If we enqueue C then, again it goes to the tail of the list. And if I now dequeue, which one is going to be removed? Again, this is not a stack. In a stack, C would be removed. In our case, A is going to be removed because it's been there longest. That's just an implementation of popping from the front. Okay. So that would return A. We can now do some more enqueuing, enqueue D, enqueue E, enqueue F. And now if we start dequeuing, we dequeue from the front. So dequeuing B, dequeuing C, dequeuing D, dequeuing E, and finally dequeuing F. If we ask whether the queue is empty now, the answer is yes. Again, because the head is nil. So enqueue uses list's pushback call, and dequeue uses both the list's top front to get the front element, as well as pop front to remove that front element. And empty just uses the list's empty method. What about with an array? We could think of doing something similar. That is, we could add at the end and then pop from the front. But you can imagine, so we said basically if we said the front of the array is the beginning of the queue, then enqueuing is easy, but dequeuing would be an expensive order n operation. And we want enqueuing to be order 1. We can do that in a fashion I'll show you right now, which is basically keeping track of sort of the array as a circular array. So we're going to go ahead and enqueue A, and we have a write index. So the write index tells us where the next enqueue operation should happen, and the read tells us where the next dequeue operation should happen. So we enqueue A, we enqueue B, and now update our write index. If we ask whether we're empty, no, we're not empty because read is not equal to write. That is, we have something to dequeue that has been enqueued. Okay. So empty would be false. We enqueue C. If we dequeue, again, we're going to dequeue A, so we dequeue from the read index. So we basically read what's at the read index and then increment the read index. If we now dequeue again, we read what's at the read index, which is B, and we increment the read index. Now we'll do some more enqueuing. Notice at this point when we enqueue D, the write index is 4. That's the next place we're going to enqueue to. So we enqueue E, which will have us write to the index 4, and then the write index wraps back around to the initial element. And here it's important to note we're using zero-based indexing of this array, right, because of the fact that the first element is 0. We enqueue again, enqueue F, and now if we try and enqueue G, it's not going to allow us to do that. So that will be an error. The reason it would be an error is if we did enqueue G, the read and the write index would both be 2. And it would be hard to distinguish read and write index to 2 because the queue is full, or read and write index both 2 because the queue is empty. So therefore, we have a buffer of at least one element that can't be written to, okay, to make sure read and write are separate and distinct if the queue is not empty. Now we'll dequeue, so we'll dequeue C, basically reading from the read index and updating it, dequeue D, read from the read index and update it, dequeue E, and here again the read index wraps around back to 0. And now finally we do our final dequeue, and now the read and write index are both 1, which means if we ask whether the queue is empty, the answer is yes, it is empty. So what we see here is that the cost for doing a dequeue and an enqueue, as well of course as empty, are all order 1 operations with this array. So we can use either a linked list, although we have to have a tail pointer so that pushback is cheap, or an array. Each of the operations is order 1. One distinction between the array and the linked list implementation is that in the array implementation, we have a maximum size that the queue can grow to, so it's bounded. Okay? Maybe you want that, in which case it's fine, but if you don't know a priori how long the queue you need is going to be, an array is a bad choice. And any amount that is unused is wasted space. In a queue that's implemented with a linked list, it can get arbitrarily large as long as there's available memory. The downside is every element you have to pay for another pointer. In this lecture, we're going to talk about trees. Let's look at some example trees. So here we have a sentence, I ate the cake. And we're going to look at a syntax tree for that, which shows the structure of the sentence. This is similar to sentence diagramming that you may have done in grade school. So we have at the top of the tree the S for sentence, and then children a noun phrase and a verb phrase. The child of the noun phrase is the word I from the sentence, and the child of the verb phrase is a verb and a noun phrase, where the verb is ate and the noun phrase is a determiner and a noun, the and cake. So along the bottom of the tree, we have the words from the sentence, I ate the cake, and the rest of the tree reflects the structure of that sentence. We can look here at a syntax tree for an expression. So 2 sine of 3z minus 7. We can break that up and show the structure. So at the top level, we have a multiplication. That's really the last thing that's done, multiplying the 2 and the sine. Within the sine, what we're applying the sine to is 3z minus 7. So we have the minus that's happening last with a 7, and then this 3z, 3 times z. So this shows again the structure of the expression and the order in which you might evaluate it. So from the bottom you would first do 3 times z, and then you would subtract 7 from that, you'd apply the sign to that, and then you multiply that by 2. Trees are also used to reflect hierarchy. So this reflects hierarchy of geography, where we have at the left-hand side the top level of the hierarchy, the world, and then below that, entities in the world. United States, all sorts of other things, United Kingdom, and then below that, various subcomponents of the geography. So we've got, for the case of United States, states, and then within those states, cities. Another example of a hierarchy is the animal kingdom. This is part of it where we've got animals, and then below that, different types of animals. So invertebrates, reptiles, mammals, and so on. And then within each of these, we have various subcategorizations. So this shows this entire hierarchy. We also use trees in computer science for code. So in order to represent code, we will do that with an abstract syntax tree. So our code here is a while loop. While x is less than 0, x is x plus 2, f of x. So we reflect that at the top, we have while, which is our while loop, and the children of the while loop are the condition that needs to be met for the while loop to continue, and then the statement to execute. So the condition is x less than 0, so a comparison operation, the variable x and the constant 0. And then the statement to execute, well, it's actually multiple statements, so we have a block. And in those blocks, we have 2 different statements, an assignment statement and a procedure call. The assignment statement, the left child is the variable we're assigning to, which is x, and the right child is an expression, in this case, x plus 2. The procedure call, the left child is the name of the procedure, and subsequent children are the arguments to that procedure. In our case, we just have one argument, x. So binary search trees are a very common type of a tree used in computer science. The binary search tree is defined by the fact it's binary, so that means it has at most 2 children at each node. And we have the property that at the root node, the value of that root node is greater than or equal to all of the nodes in the left child. And it's less than the nodes in the right child. So here, less than and greater than, we're talking about alphabetically. So less is greater than Alex, Kathy, and Frank, but is less than Nancy, Sam, Violet, Tony, and Wendy. And then that same thing is true for every node in the tree has this same thing. For instance, Violet is greater than or equal to Tony and less than or equal to, strictly less than Wendy. The binary search tree allows you to search quickly. For instance, if we wanted to search in this tree for Tony, we could start at less. Notice that we are greater than less, so therefore we're going to go right. We're greater than Sam, so we'll go right. We're less than Violet, so we'll go left, and then we find Tony. And we do that in just 4 comparisons. It's a lot like a binary search in a sorted array. So we have all these examples of trees. What's the actual definition of a tree? Well, a tree is, this is a recursive definition. A tree is either empty, or it's a node that has a key, and then has a list of child trees. So if we go back to our example here, less is a node that has the key less and 2 child trees, the Kathy child tree and the Sam child tree. The Kathy child tree is a node with a key Kathy and 2 child trees, the Alex child tree and the Frank child tree. Let's look at the Frank child tree. It's a node with a key Frank and 2. Well, does it have any child trees? No, it has no child trees. Okay. So let's look at some other examples. An empty tree, well, we don't really have a good representation for that. It's just empty. A tree with 1 node is the Fred tree, and it has no children. A tree with 2 nodes is a Fred with a single child, Sally, that it itself has no children. In computer science, commonly trees grow down, so parents are above their children. So that's why we have Fred above Sally. So let's look at some other terminology for trees. So here we have a tree Fred is the root of the tree, so it's the top node in the tree. And here, the children of Fred are Kate, Sally, and Jim. We're actually showing that with arrows. Commonly, when you show trees, you don't actually show the arrows. We just assume that if a node is above another node, that it's a parent of that node. A child has a line down directly from a parent, so Kate is a parent of Sam, and Sam is a child of Kate. An ancestor is a parent or a parent's parent, and so on. So Sam's ancestors are Kate and Fred. Hugh's ancestors are also Kate and Fred. Sally's ancestors are just Fred. The descendant is the inverse of the ancestor, so it's the child or child of child and so on. So the descendants of Fred are all of the other nodes, since it's the root: Sam, Hugh, Kate, Sally, and Jim. The descendants of Kate would just be Sam and Hugh. Sibling, two nodes sharing the same parent. So Kate, Sally, and Jim are all siblings. Sam and Hugh are also siblings. A leaf is a node that has no children. So that's Sam, Hugh, Sally, and Jim. An interior node are all nodes that aren't leaves. So this is Kate and Fred. Another way to describe it is all nodes that do have children. The level, 1 plus the number of edges between the root and the node. So let's think about that. Fred, how many edges there between the root and the Fred node? Well, since the Fred node is the root, there are no edges. So its level would be 1. Kate has 1 edge between Fred and Kate, so its level would be 2, along with its siblings, Sally and Jim. And Sam and Hugh are level 3. The height, the maximum depth of the subtree node in the farthest leaf. So here we want to look, for instance, if we want to look at the height of Fred, we want to look at what is its farthest down descendant. Okay. And so its farthest down descendant would either be Sam or Hugh. Its height would be 3. So the leaf heights are 1. Kate has height 2, Fred has height 3. We also have the idea of a forest, extending this tree metaphor. So it's a collection of trees. So we have here 2 trees with a root Kate and a root Sally, and those form a forest. So a node has a key, children, which is a list of children nodes, and then it may or may not have a parent. The most common representation probably of trees is really without the parent, but it's possible to also have parent pointers, and that can be useful as a way to traverse from anywhere in a tree to anywhere else by going up and then down, following parent nodes and then child nodes. On rare occasions, you could have a tree that's represented just with parent pointers. Okay, but that's unusual because a lot of times, kind of the way you get access to a tree is via its root, and you want to go down from there. There are other, less commonly used representations of trees as well. We're not going to get into here. Binary trees are very commonly used. So a binary tree has at most 2 children. Rather than having then this general list of children, for a binary tree we normally have an explicit left and right child, either of which can be nil. As with a normal tree, the general form of a tree, you may or may not have a parent pointer. Let's look at a couple of procedures operating on trees. Since trees are recursively defined, it's very common to write routines that operate on trees that are themselves recursive. So for instance, if we want to calculate the height of a tree, that is the height of a root node, we can go ahead and recursively do that going through the tree. So we can say, for instance, if we have a nil tree, then its height is a 0. Otherwise, we're 1 plus the maximum of the left child tree and the right child tree. So if we look at a leaf, for example, that height would be 1 because the height of the left child is nil, is 0, and the height of the nil right child is also 0. So the max of that is 0, 1 plus 0 is 0. We could also look at calculating the size of a tree, that is the number of nodes. Again, if we have a nil tree, we have 0 nodes. Otherwise, we have the number of nodes in the left child plus 1 for ourselves plus the number of nodes in the right child. So 1 plus the size of the left tree plus the size of the right tree. In the next video, we're going to look at different ways to traverse a tree. In this video, we're going to continue talking about trees, and in particular, look at walking a tree or visiting the elements of a tree or traversing the elements of a tree. So often we want to go through the nodes of a tree in a particular order. We talked earlier when we were looking at the syntax tree of an expression, how we could evaluate the expression by working our way up from the leaves. So that'd be one way of walking through a tree in a particular order so we could evaluate. Or another example might be printing the nodes of a tree. If we had a binary search tree, we might want to get the elements of a tree in sorted order. There are two main ways to traverse a tree. One is depth first. So there, we completely traverse one subtree before we go on to a sibling subtree. Alternatively, in breadth first search, we traverse all the nodes at one level before we go to the next level. So in that case, we would traverse all of our siblings before we visited any of the children of any of the siblings. We'll see some code examples of these. In depth first search, so we're going to look here at a in-order traversal. And that's really defined best for a binary tree. So this is in-order traversal is what we might use to print all the nodes of a binary search tree in alphabetical order. So we're going to have a recursive implementation where if we have a nil tree, we do nothing. Otherwise, we traverse the left subtree and then do whatever we're going to do to the key, visit it. In this case, we're going to print it. But often there's just some operation you want to carry out, and then traverse the right subtree. So let's look at an example of this. We've got our binary search tree, and we're going to look at how these nodes get printed out if we do an in-order traversal. So to begin with, we go to the less node. And from there, since it's not nil, we're going to do an in-order traversal of its left child, which is Kathy. Similarly, now we're going to do an in-order traversal of its left child, which is Alex. Okay. We do an in-order traversal of its left child, which is nil, so it does nothing. So we come back to Alex and then print out Alex, and then traverse its right subtree, which is nil and does nothing. We come back to Alex, and then we're finished with Alex, and we'll go back to Kathy. So we have successfully completed Kathy's left subtree, so did an in-order traversal of that. So now we're going to print Kathy, and then do an in-order traversal of its right subtree, which is Frank. So we go into Frank. Similarly, now we're going to print out Frank. We finish with Frank and go back to Kathy. And now we've completed Kathy totally. So we go back to Les. We completed Les's left subtree, so we're now going to print Les, and then traverse Les's right subtree. So that is Sam. Traverse its left subtree, which is Nancy, print it out. Go back to Sam. We've completed Sam's left subtree, so we print Sam. And then go ahead and do Sam's right subtree, which is Violet, which will end up printing Tony, Violet, and then Wendy. We're completed with Wendy. We go back to Violet. We've completed her right subtree. So we go back to Sam, completed his right subtree, go back to Les, completed his right subtree, and we're done. So we see we get the elements out in sorted order. And again, we do the left child, and then the node, and then the right child. And by our definition of a binary search tree, that then gives us to them in order, because we know all the elements in the left child are in fact less than or equal to the nodes itself. The next depth first traversal is a pre-order traversal. Now, the in-order traversal really is only defined for a binary tree, because we talk about doing the left child and then the node and then the right child. And so it's not clear if you had, let's say, 3 children, where it is you'd actually put the node itself. So you might do the first child and then print the node, and then second and third child, or first child and then second child and print the node and then third child. It's kind of undefined there, so not well defined. However, these next two, the pre-order and post-order traversal, are well defined, not just for binary trees, but for general arbitrary number of children trees. So here the pre-order traversal says, we're going to go ahead, first if it's nil, we return. We print the key first, that is, we visit the node itself and then its children. So we're going to, in this case, go ahead and go to the less tree and then print out its key, and then go to its children. So we're going to first go to its left child, which is Kathy. And for Kathy, we then print Kathy, and then go to its left child, which is Alex, print Alex. We go back to Kathy, and we've finished its left child, so we now need to go to its right child, which is Frank. We finished Frank, we finished Kathy, we go back up to Les. We've already printed Les. We've already visited or traversed Les's left child. Now we need to traverse Les's right child. So that'll be Sam, which we'll print out, and then we'll go to Nancy, which we'll print out. We'll go back up to Sam and then to Violet, and we will print Violet, and then print Violet's children, which will be Tony and Wendy. And then return back up the tree. A post-order traversal is like a pre-order traversal, except instead of printing the node itself first, which is the pre, we print it last, which is the post. So all we've really done is moved where this print statement is. And here then, what's the last of these nodes that's going to be printed? Well, it's actually going to be Les, because we're not going to be able to print Les until we've finished completely dealing with Les's left subtree and right subtree. So we'll visit Les, and then visit Kathy, and then Alex, and then we'll actually print out Alex. Once we're done with Alex, we'll go back up to Kathy and down to Frank, and then print out Frank. And then once we're done with both Alex and Frank, we can then print Kathy. We go back up to Les, and we now need to go deal with Les's right child, which is Sam. In order to deal with Sam, we go to Nancy, print Nancy, go back up to Sam and down to Violet, and deal with the Violet tree, which will print out Tony, and then Wendy, and then Violet. And on our way back up, then, when we get to Sam, we have finished its children, so we can print out Sam. When we get up to Les, we finished its children, so we can print out Les. One thing to note about the recursive traversal is we do have, sort of under the covers, a stack that's being used, because in our recursive call, every time we make a call back to a procedure, we are invoking another frame on the stack. So we are saving implicitly our information of where we are on the stack. Breadth first, we're going to actually use a queue instead of a stack. So in the breadth first, or we're going to call it level traversal here, we're going to go ahead and instantiate a queue, and on the queue, first put the root of the tree. So we put that in the queue, and then while the queue is not empty, we're going to dequeue, so pull a node off, deal with that by printing it, and then if it's got a left child, enqueue the left child. If it's got a right child, enqueue the right child. And so this will have the effect of going through and processing the elements in level order. We'll see the example here, and we're going to show the queue. So here, let's say we're just before the while loop, the queue contains Les, and we're going to now dequeue Les from the queue, output it by printing it, and then enqueue Les's children, which are Kathy and Sam. Now we visit those in order. So first we're going to dequeue Kathy, print it out, and then enqueue its children. Remember, when we're enqueuing, we go at the end of the line, so Alex and Frank go after Sam. So now we're going to dequeue Sam, print it, and then enqueue its children, Nancy and Violet. So we can see what we've done then is we first printed Les, that's level 1, and then we printed the elements at level 2, which are Kathy and Sam. And now we're going to go on to the elements at level 3. So notice all the elements in level 2, level 3, Alex, Frank, Nancy, and Violet, are in the queue already. And they're going to all be processed before any of the level 4 nodes are processed. So even though they'll be pushed in the queue, since the level 3 nodes got there first, they're going to all be processed before we process any level 4 ones. So here we dequeue Alex, print it out, and we're done. Dequeue Frank, print it out, we're done with Frank. Dequeue Nancy, print it out, and we're done with Nancy. And Violet, we print it out, but then also enqueue Tony and Wendy, and then dequeue those and print them out. So this is a breadth first search with an explicit queue. You can do depth first searches rather than recursively, iteratively, but you will need an additional data structure, which is a stack, in order to keep track of the work still to be done. So in summary, trees are used for lots of different things in computer science. Okay? We've seen that trees have a key and normally have children, although there are alternative representations of trees. the tree walks that are normally done, or the traversals, are DFS, depth first search, and BFS, breadth first search. There are different types of depth first search traversals: pre-order, in-order, and post-order. When you work with a tree, it's common to use recursive algorithms, although note that we didn't for the breadth first search, where we needed to go through the elements of the tree in kind of a non-recursive order. And finally, in computer science, trees grow down. So in this lecture, we're going to talk about dynamic arrays and amortized analysis. In this video, we're going to talk about dynamic arrays. So the problem with static arrays is, well, they're static. Once you've declared them, they don't change size, and you have to determine that size at compile time. So one solution is what are called dynamically allocated arrays. There, you can actually allocate the array, determining the size of that array at runtime. So that gets allocated from dynamic memory. So that's an advantage. The problem is, what if you don't know the maximum size at the time you're allocating the array? Okay, simple example, you're reading a bunch of numbers, you need to put them in an array, but you don't know how many numbers there'll be. You just know that there'll be some mark at the end that says we're done with the numbers. So how big do you make it? Do you make it 1,000 big? But then what if there are 2,000 elements? Make it 10,000 big? But what if there are 20,000 elements? So a solution to this, there's a saying that says all problems in computer science can be solved by another level of indirection. And that's the idea here. We use a level of indirection. Rather than directly storing a reference to the either static or dynamically allocated array, we're going to store a pointer to our dynamically allocated array. And that allows us then to update that pointer. So if we start adding more and more elements, when we add too many, we can go ahead and allocate a new array, copy over the old elements, get rid of the old array, and then update our pointer to that new array. So these are called dynamic arrays, or sometimes they're called resizable arrays. And this is distinct from dynamically allocated arrays, where we allocate an array, but once it's allocated, it doesn't change size. So a dynamic array is an abstract data type, and basically you want it to look kind of like an array. So it has the following operations at a minimum. It has get operation that takes an index and returns you the element of that index, and a set operation that sets an element at a particular index to a particular value. Both of those operations have to be constant time, because that's kind of what it means to be an array, is that we have random access with constant time to the elements. We can push back, so that adds a new element to the array at the end of the array. We can remove an element, okay, at a particular index, and that'll shuffle down all the succeeding ones. And finally, we can find out how many elements are in the array. How do we implement this? Well, we're going to store array, ARR, which is our dynamically allocated array. We're going to store capacity, which is the size of that dynamically allocated array, okay, how large it is. And then size is the number of elements that we're currently using in the array. Let's look at an example. So let's say our dynamically allocated array has a capacity of 2, but we're not using any elements in it yet, so it's of size 0. And ARR then points to that dynamically allocated array. If we do a pushback of A, that's going to go ahead and put A into the array and update the size. If we now push B, it's going to put B into the array and update the size. Notice now the size is equal to the capacity, which means this dynamically allocated array is full. So if we get asked to do another pushback, we have got to go allocate a new dynamically allocated array. We're going to make that larger, in this case it's of size 4, and then we copy over each of the elements from the old array to the new array. Once we've copied them over, we can go ahead and update our array pointer to point to this new dynamically allocated array, and then dispose of the old array. At this point now, we finally have our new dynamically allocated array that has room to push another element. So we push in C. We push in D, there's room, we put it in, update the size. And now if we try and push another element, again, we have a problem. We're too big. We're going to allocate a new array. In this case, we're going to make it of size 8. We'll talk about how you determine that size somewhat later. And then copy over A, B, C, and D, update the array pointer, deallocate the old array, and now we have room we can push in E. So that's how dynamic arrays work. Let's look at some of the implementations of the particular API methods. Get is fairly simple. So we just check and see. We're going to assume for the sake of argument that we are doing zero-based indexing here. Okay? So if we want to get index I, we first check and make sure, is I in a range? That is it non-negative, and is it within the range 0 to size -1? That is, if it's less than 0 or it's greater than or equal to size, it's out of range. That'll be an error. If we're in range, then we just return index I from the dynamically allocated array. Set is very similar. Check to make sure our index is in bounds, and then if it is, update index I of the array to val. Pushback is a little more complicated. So let's actually skip the if statement for now and just say, let's say that there is empty space in our dynamic array. In that case, we just set array at size to val and then increment size. If, however, we're full, we're not going to do that yet. If size is equal to capacity, then we go ahead and allocate a new array. We're going to make it twice the capacity. And then we go through a for loop, copying over every one of the elements from the existing array to the new array. We free up the old array and then set array to the new array. At that point then, we've got space, and we go ahead and set the size element and then increment size. Remove is fairly simple. Check that our index is in bounds, and then go ahead through a loop, basically copying over successive elements and then decrementing the size. The size is simple. We'll just return the size. There are common implementations for these dynamic arrays. In C++, the vector class is an example of a dynamic array. And there, notice that it uses C++ operator overloading, so you can use the standard array syntax of left brackets to either read from or write to an element. Java has an array list, Python has the list, and there is no static arrays in Python. All of them are dynamic. What's the runtime? We saw get and set are order 1, as they should be. Pushback is order n, although we're going to see that that's only the worst case. And most of the time, actually, when you call pushback, it's not having to do the expensive operation. That is, the size is not equal to capacity. For now, though, we're going to just say that it's order n, and we'll look at a more detailed analysis when we get into aggregated analysis in our next video. Removing is order n, because we've got to move all those elements. Size is order 1. So in summary, let's see. Unlike static arrays, dynamic arrays are dynamic. That is, they can be resized. Appending a new element to a dynamic array is often constant time, but it can take order n. We're going to look at a more nuanced analysis in the next video. And some space is wasted. In our case, if we're resizing by a factor of 2, at most half the space is wasted. If we were making our new array 3 times as big, then we could waste 2/3 of our space. If we're only making it 1.5 as big, then we would waste less space. It's worth noting dynamic arrays can also be resized smaller. That's possible too. It's worth thinking about what if we resized our array to a smaller dynamic array as soon as we got under 1/2 utilization. And it turns out we can come up with a sequence of operations where we have that gets to be quite expensive. In the next video, we're going to talk about amortized analysis. And in particular, we're going to look at one method called the aggregate method. So we'll discuss now what amortized analysis is and look at a particular method for doing such analysis. Sometimes we're looking at an individual worst case, and that may be too severe. In particular, we may want to know the total worst case for a sequence of operations, and it may be that some of those operations are cheap, while only certain of them are expensive. So if we look at the worst case operation for any one and multiply that by the total, it may be overstating the total cost. As an example, for a dynamic array, we only resize every so often. Most of the time we're doing a constant time operation of just adding an element. It's only when we fully reach the capacity that we have to resize. So the question is, what's the total cost if you have to insert a bunch of items? All right. So here's the definition of amortized cost. If we have a sequence of n operations, The amortized cost is the cost of those inner operations divided by n. Okay, this is similar in spirit to, let's say you buy a car for, I don't know, $6,000, okay? And you figure it's going to last you 5 years. Now, you have two possibilities. One, you pay the $6,000, and then 5 years later, you have to pony up another $6,000. Another option would be to put aside money every month, right? So 5 years is 60 months. So if you put away $100 a month, once the 5 years is over, then when it's time to buy a new car for $6,000, you'll have $6,000 in your bank account. And so there, that amortized cost of the monthly cost is $100 a month. Whereas the worst case monthly cost is actually $6,000. It's zero for 59 months, and then it's $6,000 after 1 month. So you can see that that amortized cost gives you a more balanced understanding. If you really want to know what's the most I spend in every month, the answer, yes, is $6,000. But if you want to know sort of on average what am I spending, $100 is a more reasonable number. So that's why we do this amortized analysis, to get a more nuanced picture of what it looks like for a succession of operations. So let's look at the aggregate method of doing amortized analysis. And the aggregate method really says, let's look at the definition of what an amortized cost is and use that to directly calculate it. So we're going to look at the example of a dynamic array, and we're going to do n calls to pushback. We're going to start with an empty array and n times call pushback. And then we'll find out what the amortized cost is of a single call to pushback. We know the worst case time is order n. So let's define C sub I as the cost of the ith insertion. So we're interested in C1 to Cn. So Ci is, clearly it's 1, because we have got to and what we're going to count for a second here is writing into the array. So the cost is 1 because we have to write in this ith element that we're adding, okay? Regardless of whether or not we need to resize. If we need to resize, first question is, when do we need to resize? We need to resize if our capacity is used up. That is, if the size is equal to the capacity. Well, when does that happen? That happens if the previous insertion filled it up, that is, made it a full power of 2, because in our case, we're always doubling the size. So that says on the ith insertion, we're going to have to resize if the ith minus 1 filled it up. That is, the I minus 1 is a power of 2. And if we don't have to resize, there's no additional cost. It's just 0. So the total amortized cost is really the sum of the n actual costs divided by n. So that's a summation from I equals 1 to n of C sub I. And again, C sub I is the cost of that ith insertion. Well, that's equal to n because every C sub I has a cost of 1. So we sum that n times, that's n, plus then the summation from, what's this? This looks a little complicated. So j equals 1 to the floor of log base 2 of n minus 1 of 2 to the j. That just really says the power of 2's all the way up to n minus 1. Okay, so I'll give an example. If n is 100, the power of 2's are going to be 1, 2, 4, 8, 16, 32, and 64. Okay, and it's the summation of all of those. Well, that summation is just order n. Where basically take powers of 2 up to, but not including n, and that is going to be no more than 2n. So we've got n plus something no more than 2n, that's clearly order n divided by n, and that's just order of 1. So what we've determined then is that we have a amortized cost for each insertion of order 1. Our worst case cost is still order n. So if we want to know how long it's going to take, in the worst case for any particular insertion, it's order n, but our amortized cost is order 1. In the next video, we're going to look at an alternative way to do this amortized analysis. In this video, we're going to talk about a second way to do amortized analysis, what we call the banker's method. The idea here is that we're going to charge extra for each cheap operation. So it's sort of like we're taking the example where we looked at saving money for a car. We're going to actually take that $100 and put it in the bank. And then we save those charges somewhere. In the case of the bank, we put it in the bank. In our case, we're going to conceptually save it in our data structure. Okay? We're not actually changing our code. This is strictly an analysis, but we're conceptually thinking about putting our saved extra costs as sort of tokens in our data structure that later on we'll be able to use to pay for the expensive operations. Does it make more sense as we see an example? So it's kind of like an amortizing loan, or this case I talked about where we're saving $100 a month towards a $6,000 car because we know our current car is gonna run out. Let's look at this same example where we have a dynamic array and we have n calls to pushback starting with an empty array. Okay? The idea is we're going to charge 3 for every insertion. So every pushback, we're going to charge 3. 1 is the raw cost for actually moving in this new item into the array, and the other 2 are going to be saved. So if we need to do a resize, in order to pay for moving the elements, we're going to use tokens we've already saved in order to pay for the moving. And then we're going to place 1 token, once we've actually added our item, 1 token on the item we added, and then 1 token on an item prior to this in the array. Okay? It'll be easier when we look at a particular example. So let's look at an example. We have an empty array. Okay, and we're going to start with size 0, capacity 0. We push back A. What happens? Well, we have to allocate our array of size 1 and point to it, and then we put A into the array. And now we're going to put a little token on A. And this token is what we're going to use to pay later on to moving A. In this particular example, for the very first element, there's no other element to put a token on. So we're just kind of waste that third token. We push in B. Okay. There's no space for B, so we've got to allocate a larger array and then move A. How are we going to pay for that moving A? Well, with the token that's already on A. So we prepaid this moving A. Okay? When we actually initially put A into the array, we put a token on it that would pay for moving it into a new array. So that's how we pay for moving A. And then we update the array, delete the old one, and now we actually put B in. So we put B in, that's a cost of 1. We still have 2 more tokens to pay. So we're going to put 1 on B, and we're going to put 1 capacity over 2, that is 1 element earlier. So we're going to put 1 on B. So we've spent 3 now, 1 for real, and 2 as deferred payment that we're going to use later in the form of these tokens. Remember, these tokens are not actually stored in the data structure. There's nothing actually in the array. This is just something we're using for mental accounting in order to do our analysis. When you push in C, we're going to allocate a new array. We copy over A, and we pay for that with our prepaid token. We copy over B, paying for that with our prepaid token. And now we push in C. That's 1. The second payment we have to make is we put a token on C, and then we put a token on A. 4 divided by 2, that is the capacity divided by 2, are 2 elements prior. We push in D, we don't have to do any resizing, finally. Okay, so we just put in D, and that's cost of 1. Second, put a token on D. Third, put a token capacity over 2, or 2 elements prior to that. So notice, what we've got now is a full array, and everything has tokens on it, which means when we need to resize, we have prepaid for all of that movement. So we push in E, allocate a new array, and now we use those prepaid tokens to pay for moving A, B, C, and D. Get rid of the old array, and now push in E. And again, put a token on E, and a token on A. So what we've got here then is order 1 amortized cost for each pushback. In particular, we have a cost of 3, right? So we've clearly seen. So let's look back at how we did this. For this dynamic array, we decided we had to charge 3. And other data structures with other operations, we may have to charge a different amount, right? We have to figure out what will be sufficient. In our case, 3 was sufficient, and we decided that we would go ahead and store these tokens on the elements that needed to be moved. So it's a very physical way to keep track of the saved work that we have done, or the prepaid work that we have done. So we charge 3. 1 is the raw cost for the insertion. If we need to resize, we've arranged things such that whenever the array gets full, we've actually, in order for the array to have been full, we had to have done enough pushbacks such that every element got a token on it. All the new ones that we added since the previous resize, plus every time we added one of those new ones, we prepaid for a prior element as well. So we pay our 1 insertion, we pay 1 for the element we're adding now, and we pay 1 for sort of a buddy element earlier. The next video, we're going to look at a third way of doing amortized analysis, which is the physicist method. Now let's talk about the final way to do amortized analysis, which is the physicist method. The idea of the physicist method is to define a potential function, which is a function that takes a state of a data structure and maps it to an integer, which is its potential. This is similar in spirit to what you may have learned in high school physics, the idea of potential energy. For instance, if you have a ball and you take it up to the top of a hill, you've increased its potential energy. If you then let the ball roll down the hill, its potential energy decreases and gets converted into kinetic energy, which increases. We do the same sort of thing for our data structure, storing in it the potential to do future work. A couple rules about the potential function. First, phi of h sub 0. So phi is the potential function. H sub 0 is time 0 of the data structure h. So that means the initial state of the data structure. And that has to have a potential of 0. Second rule is that potential is never negative. So at any point in time, phi of h sub t is greater than or equal to 0. All right. So once we've defined a potential function, we can then say what amortized cost is. The amortized cost of an operation t is c sub t, the true cost, plus the change in potential between before doing the operation and after doing the operation. So before doing the operation, we have phi of h sub t minus 1. After, we have phi of h sub t. So it's c sub t plus phi of h sub t minus phi of h sub t minus 1. What we need to do is choose a function phi such that if the actual cost is small, then we want the potential to increase so that we're saving up some potential for doing later work. And if c sub t is large, then we want the potential to decrease in a way to sort of pay for that work. So the cost of n operations is the sum of the true costs, which is the summation from I equals 1 to n of c sub I. And what we want to do is relate the sum of the true costs to the sum of the amortized costs. So the sum of the amortized costs is the summation from I equals 1 to n of the definition of an amortized cost, which is c sub I plus phi of h sub I minus phi of h sub I minus 1. Well, we could just rewrite that. So removing the summation as c sub 1 plus phi of h sub 1 minus phi of h sub 0 plus c sub 2 plus phi of h sub 2 minus phi of h sub 1 and so on. What's important to note is that we have a phi of h sub 1 in the first line and a minus phi of h sub 1 in the second line. So those two cancel out. Similarly, we'll have a phi of h sub 2 in the second line, and we have a phi of h sub 3 when we look at the amortized cost at time 3. And that goes on until at time n minus 1, we would have a phi of h sub n minus 1 positive and a negative phi of h sub n minus 1 negative. So we have all these cancellations, and all we're left with is the very first term, phi of h sub 0, negative phi of h sub 0, and the very last term in the last line, which is phi of h sub n. So this really just equals phi of h sub n minus phi of h sub 0, because all the other phis cancel, plus the summation from I equals 1 to n of c sub I. That is the true cost. Since phi of h sub n is non-negative and phi of h sub 0 is 0, this value is greater than or equal to just the summation of the true costs. What that means then is we've come up with a lower bound on the amortized sum of the amortized costs, which is the sum of the true costs. So therefore, if we want to look at a cost of an entire sequence of operations, we know it's at least the sum of the true costs. So let's look at applying this physicist method to the dynamic array. So we're going to look at n calls to pushback. Phi of h, so at any given time the data structure is going to be 2 times the size minus the capacity. So as the size increases, the potential is going to be increasing for a given fixed capacity. Phi of h sub 0, so we want to make sure that our phi function satisfies our requirements. So first, phi of h sub 0 is 2 times 0 minus 0, assuming we have an initial array of size 0, and that's just 0. Also, phi of h sub I is 2 times size minus capacity. We know the size is at least capacity over 2, so therefore 2 times size minus capacity is greater than 0. Now let's look at our amortized cost. So we're going to assume we don't have to do a resize, and let's look at the amortized cost. So we add a particular element I, and the amortized cost is the cost of insertion plus phi of h sub I minus phi of h sub I minus 1. So the cost of insertion is just going to be 1 because we're adding an element and we don't have to do any moving of elements. Phi of h sub I is 2 times size of I minus the capacity of I, and phi of h sub I minus 1 is 2 times size I minus 1 minus capacity I minus 1. Well, what do we know? Since we're not resizing, the capacities don't change. So the capacities cancel themselves out. And so we are left with 2 times the difference in sizes. But what's the difference in size? The difference in size is just 1 because we added 1 element. So this is just 1 plus 2 times 1, or 3. It's no accident that this 3 is the same value that we saw when we used the Banker's method. And then let's look at the cost when we have to do a resize. So we're going to define here K is size sub I minus 1, which is the same thing as capacity sub I minus 1. Why is it the same? Because we're about to do a resize. So that means that after the previous operation, we must have made the dynamic array full. And then phi of h sub I minus 1 is just 2 times the old size minus the old capacity, and that's just 2 times k minus k, or k. Phi of h sub I is 2 times size sub I minus capacity of I, and that's 2 times k plus 1, because the size sub I is just 1 more than size of I minus 1, minus 2k. Why 2k? Because we double the capacity each time. So that's just equal to 2. So the amortized cost of adding the element is c sub I plus phi of h sub I minus phi of h sub I minus 1, which is just size of I, because that's the number of elements we have to move size of I minus 1 elements and then add the 1 new element. So that's size of I. So we have size sub I plus 2 minus k, which is just k plus 1 plus 2 minus k, which is 3. So what we have seen now is that the amortized cost using the physicist method of adding elements is 3. Let's go back to the dynamic array. So are there alternatives to doubling the array size? Right? We doubled each time. What happens if we didn't double? Well, we could use some different growth factor. So for instance, we could use 2.5. So grow the array by more than 2, or grow the array by less than 2. As long as we use some constant multiplicative factor, we'd be fine. The question is, can we use a constant amount? Can we add by a particular amount, like let's say 10 each time? And the answer is really no. And the reason is, as the array got bigger and bigger, and we have to resize every 10 times, we just don't have enough time to accumulate work in order to actually do the movement. Let's look at it another way. So let's look at an aggregate method. Let's say c sub I is the cost of the ith insertion. Okay? We're going to find that as 1 for putting in the ith element, plus either I minus 1 if the I minus 1th insertion makes the dynamic array full. So that is if I minus 1 is a multiple of 10 and it's 0 otherwise. By the definition of our aggregate method, we're just the sum of the total costs divided by n. And that's n plus, again, that's the 1 summed n times is just n, plus the summation from 1 to n minus 1 over 10 of 10j. That is just the multiples of 10 all the way up to but not including n. So 10, 20, 30, 40, and so on. All that divided by n. Well, we can pull the 10 out of that summation. So it's just 10 times the summation j equals 1 to n minus 1 over 10 of j. So that's just numbers 1, 2, 3, 4, so on, all the way up to n minus 1 over 10. That is order n squared, that summation. So we've got n plus 10 times the order of n squared over n, which is just order of n squared over n, which is order n. So this shows that if we use a constant amount to grow the dynamic array each time, that we end up with an amortized cost for pushback of order n rather than order 1. So it's extremely important to use a constant factor. So in summary, we can calculate the amortized cost in the context of a sequence of operations. Rather than looking at a single operation in its worst case, we look at a totality of a sequence of operations. We have three ways to do the analysis: the aggregate method, where we just do the brute force sum based on the definition of the amortized cost. We can use the banker's method, where we actually use tokens and we're saving them conceptually in the data structure, or the physicist method, where we define a potential function and look at the change in that potential. Nothing changes in the code. We're only doing runtime analysis. So the code doesn't actually store any tokens at all. It's an important thing to remember. That is dynamic arrays and amortized analysis.
Hello everybody, welcome back. Today we're going to be talking about priority queues. This popular data structure has built-in implementations in many programming languages, for example in C++, Java, and Python. And in this lesson we will learn what is going on inside these implementations. We will see beautiful combinatorial ideas that allow to store the contents of a priority queue in a complete binary tree, which is in turn stored just as an array. This gives an implementation which is both time and space efficient. Also, it can be implemented just in a few lines of code. A priority queue data structure is a generalization of the standard queue data structure. Recall that the queue data structure supports the following two main operations. So we have a queue, and when a new element arrives, we put it to the end of this queue by calling the method pushback. And when we need to process the next element, we extract it from the beginning of the queue by calling the method popFront. In the priority queue data structure, there is no such thing as the beginning or the end of a queue. Instead, we have just a bag of elements, but each element is assigned a priority. When a new element arrives, we just put it inside this bag by calling the method insert. However, when we need to process the next element from this bag, we call the method extractMax, which is supposed to find an element inside this bag whose priority is currently maximum. A typical use case for priority queues is the following. Assume that we have a machine and we would like to use this machine for processing jobs. It takes time to process a job, and when we are processing the current job, a new job may arrive. So we would like to be able to quickly perform the following operations. First of all, when new job arrives, we would like to insert it to the pool of available jobs quickly, right? And when we are done with the current job, we would like to be able to quickly find the next job, that is, the job with the maximum priority, right? Okay, and now we are ready to state the definition of priority queue formally. Formally, a priority queue is an abstract data type which supports the two main operations, insert and extract max. Consider a toy example. We have a priority queue which is initially empty. We then insert element 5 in it, we then insert 7, then insert 1, and then insert 4. So we put these elements in random places inside this box on the left, just to emphasize once again that there is no such thing as the beginning or the end of a priority queue. So it is not important how the elements are stored inside the priority queue. What is important for us now is that if we call extract max for this priority queue, then an element with currently highest priority should be extracted. In our toy example, it is 7. So if we call extract max for this priority queue, then 7 is taken out of the priority queue. Then, well, let's insert 3 into our priority queue, and now let's call extract max. The currently highest priority is 5, so we extract 5. Then we extract max once again, and now it is 4. Okay? Some additional operations that we might expect from a particular implementation of a priority queue data structure are the following. So first of all, we might want to remove an element. Not to extract an element with the maximum priority, but to remove a particular element given by an iterator, for example. Also, we might want to find the maximum priority without extracting an element with the maximum priority. So getMax is an operation which is responsible for this. And also, we might want to change the priority of a given element. To increase or to decrease its priority. So change priority is operation responsible for this. Let us conclude this introductory video by mentioning a few examples of famous algorithms that use priority queues essentially. Dijkstra algorithm uses priority queues to find efficiently the shortest path from point A to point B on a map or in a graph. Prim's algorithm uses priority queues to find an optimum spanning tree in a graph. This might be useful, for example, in the following case. Assume that you have a set of computers and you would like to connect them in a network by putting wires between some pairs of them. And you would like to minimize the total price or the total length of all the wires. Huffman algorithm computes an optimum prefix-free encoding of a string or a file. It is used, for example, in MP3 audio format encoding algorithms. Finally, heap sort algorithm uses priority queues to efficiently sort the n given object. So it is comparison-based algorithm. Its running time is n log n asymptotically in the worst case. And another advantage of this algorithm is that it is in place. It uses no extra memory for sorting the input data. So we will go through all these algorithms in this specialization. And the heap sort algorithm will be even covered in this lesson, in the forthcoming videos. As usual, before going into the details of efficient implementation, let's check what is wrong with naive implementations. For example, what if we store everything, the contents of a priority queue, just in an unsorted array or in an unsorted list? In this example on the slide, we use a doubly linked list. Well, in this case, inserting a new element is very easy. We just append the new element to the end of our array or list. For example, as follows. So if our new element is 7, we can just put it to the next available cell in our array, or we can just append it to the end of the list. So we put 7 to the end. We say that the previous element of 7 is 2 and that there is no next element, right? So it is easy and it takes constant time. Okay, now what about extracting the maximum element in this case? Well, unfortunately, we need to scan the whole array to find the maximum element. And we need to scan the whole list to find the maximum element, which gives us a linear running time. That is big O of n, right? In our previous naive implementation using an unsorted array or list, the running time of the extract max operation is linear. Well, a reasonable approach to try to improve this is to keep the contents of our array, for example, array, sorted. Well, what are the advantages of this approach? Well, of course, in this case, extract max is very easy. So the maximum element is just the last element of our array, right? Which means that the running time of extract max in this case is just constant. However, the disadvantage is that now the insertion operation takes linear time. And this is why. Well, to find the right position for the new element, we can use the binary search. Well, this is actually good. Well, it can be done in logarithmic time. For example, if we need to insert 7 in our priority queue, then in logarithmic time we will find out that it should be inserted between 3 and 9 in this toy example. However, unfortunately, after finding this right position, we need to shift everything to the right of this position by 1. Right, just to create a vacant position for 7. For this, we need to first shift 16 to this cell. Then we move 10 to this cell. Then we move 9 to this cell, and finally we put 7 into this cell, and we get a sorted array. So in the worst case, we need to shift a linear number of cells, or a linear number of elements, which gives us a linear running time for the insertion operation. As we've just seen, inserting an element into a sorted array is expensive because to insert an element into the middle, we need to shift all elements to the right of this to the right of this position by 1. So this makes the running time of the insertion procedure linear. However, if we use a doubly linked list, then inserting into the middle of this list is actually constant time operation. So let's try to use a sorted list. Well, the first advantage is that the extract max operation still takes constant time. Well, this is just because, well, the maximum element in our list is just the last element, right? So for this reason, we have a constant time for extract max. Also, another advantage is that inserting in the middle of this list actually takes a constant amount of work, not a linear. And this is why. Well, again, let's try to insert 7 into our list. Well, this can be done as follows. We know that inserting 7 should be done between 3 and 9, so we do just the following. We remove this pointer and this pointer, and we say that now the next element after 3 is 7, and the previous element before 7 is 3, and also the next element after 7 is 9, and the previous element before 9 is 7. So inserting an element just involves changing 4 pointers, right? So it is a constant time operation. However, everything is not so easy, unfortunately. And this is because just finding the right position for inserting this new element takes a linear amount of work. And this is in particular because we cannot use binary search for lists. I mean, given the first element of this list and the last element of this list, we cannot find the position of the middle element of this list because this is not an array. We cannot just compute the middle index in this array. So for this reason, just finding the right position for the new element, I mean to keep the list sorted, takes already a linear amount of work. And for this reason, inserting into a sorted list still takes a linear amount of work. Well, to conclude, if you implement a priority queue using a list or an array, sorted or not, then one of the operations, insert and extract max, takes a linear amount of work. In the next video, we will show a data structure called binary heap, which allows to implement a priority queue so that both these operations can be performed in logarithmic amount of work. Hello. In this lesson, we will consider binary heaps in full detail. A binary heap is one of the most common ways of implementing a priority queue. So just by definition, a max binary heap is a binary tree. That is a tree where each node has either 0, 1, or 2 children, where the following property is satisfied for each node. The value of the node is at least the value of all its children. Or put it otherwise, if you take any edge in this tree, then the value of its top end is at least the value of its bottom end. Okay, so this is an example of a binary max heap, and it can be easily checked that this property is satisfied on all the edges of this tree. On the other hand, this is an example of a binary tree which is not a binary max heap. And this is why. Here we have 5 edges where the property is violated. For example, we see that on this top edge, well, it's the value of its top end is 10, while the value of its bottom end is 25. And there are 4 other edges where the property is violated. Let's see how basic operations work with binary max heaps. What is particularly easy for binary max heaps is finding the maximum value without extracting it. I mean, it is easy to implement get max operation. Well, recall that the main property of the binary max heap tree is the following. For each edge, its top value is greater or equal than its bottom value. This means that if we go from bottom to top in our tree, then the values can only increase. This in particular means that the maximum value is stored at the root of our tree. So just to implement getMax, we just return the value at the root of our tree. And this takes us just a constant time, of course. Now let's see how inserting a new element into the max binary heap works. So first of all, a new element should be attached somewhere to our tree. We cannot attach it to the root in this case, for example, because the root already has 2 children. Therefore, we just attach it, well, to some leaf. Let's select, for example, the leaf 7 and attach a new node to it. The new node, in this case, has value 32. Well, it is still a binary tree, right? Because 7, before attaching 7 had 0 children, now it has just 1 child. So it is still a binary tree. However, the heap property might potentially be violated. And it is violated actually in this case, right? Which is shown by this red edge. So for this red edge, the value of its parent, which is 7, is less than the value of its child, which is 32. So we need to fix it somehow. So to fix it, we just allow the new element to shift up. So this new element has value 32, which is really relatively large with respect to all other elements in this tree. So we need to move it somewhere closer to the root, right? So the process of moving it closer to the root is called shifting up. So the first thing to do is that we need to fix this problematic edge. To fix it, we perform the following simple operation. We just swap the corresponding 2 elements. In this case, we swap 7 and 32. After the swap, there is no problem on this edge. However, it might be the case that the new element 32 is still smaller, is still greater than its parent. And this is the case in our toy example. So the parent of 32 is now 29, which is smaller than 32. So we still need to fix this red problem. And we just repeat this process. We again swap the new element with its parent, right? So we swap it, and now we see that the property is satisfied for all, that the heap property is satisfied for all edges in this binary tree. So what we've just done is that we let the new element to shift up. And what is important to note here is that we maintained the following invariant, that the heap property at any point of time of shifting the new element up, the heap property is violated on at most one edge of our binary tree. So if we see that there is a problematic edge, we just swap its 2 elements, right? And each time during this process, the problematic node gets closer to the root. This in particular implies that the number of swaps required is at most the height of this tree, which in turn means that the running time of insertion procedure as well as the running time of the shifting up procedure in this case is big O of the tree height. Now let's see how the extract max procedure works for binary max heaps. First of all, recall that we already know that the maximum value is stored at the root of the tree. However, we cannot just take and detach the root node because it will leave 2 subtrees. right? So we need to somehow preserve the structure of the tree. What is easy to detach from a binary tree is any leaf. So let's do the following. Let's select any leaf of our tree and let's replace the root with this leaf. So in this case, this produces the following tree. This potentially might violate the heap property, and in this case, this does violate the property. So the new root 12 is less than both its children, so the property is violated on two edges. So 12 is relatively small number in this case, so we need to move it down to the leaves, right? So for this we will implement a new procedure which is called sift down. Okay, so 12 for this, well, similarly to sift up, we are going to replace the new element with one of its children. In this case, we have a choice actually. We can replace it either with its left child or with its right child. By thinking a little bit, we realize that it will make more sense to replace it with the left child in this case, because the left child is larger than the right child. Because after this, after we replace 12 with 29, the right problematic edge will be fixed automatically, right? So this is how we are going to perform the sift down procedure. Once again, we select the largest of two child and we replace the problematic node with this larger child. As you can see, the right problematic edge is fixed automatically. The left edge is also fixed just because we swapped two elements. However, the new problematic node 12 might introduce new problems, right, closer to the bottom of the tree. Now we see that there is still a problematic edge. So in this case, we have just one edge, so 12 is smaller than 14, but it is greater than 7. So we are safe in the right subtree. In this case, we just swap 14 with 12, and after that we just get a tree where the property is satisfied on all edges. So once again, we maintain the following invariant. At each point of time, we have just one problematic node, and we always swap the problematic node with the larger one of its children, so that to fix both problematic edges, right? And the problematic node always gets closer to the leaves, which means that the total running time of the extract max and as well as the sift down procedures is proportional to the tree height. Now, when we have implemented both procedures, sifting up and sifting down, it is not so difficult to implement also the change priority procedure. So assume that we have an element for which we would like to change its priority. This means that we are going either to decrease its priority or to increase its priority. Well, to fix the potential problems that might be introduced by changing its priority, we're going to call either sifting up or sifting down. Well, let me illustrate this again on a toy example. Assume that we are going to change the priority of this leaf 12. So we've just changed it, we just increased the priority of this element to 35. In this case, we potentially introduced some problems and we need to fix them. Well, we see that 35 is a relatively large number, which means that we need to sift it up. So we need to move it closer to the root. So to do this, we just call sift up procedure, which repeatedly swaps the problematic node with each parent. So in this case, this will produce the following sequence of swaps. First, we swap 35 with 18. This gives us the following picture. We see that there is still a problem. So 35 is still larger than its parent. So we swap it again. Now we see that 35 is smaller than its parent, and actually the heap property is satisfied for all edges. Once again, what is important in this case is that at each point of time, the heap property is violated on at most one edge of our tree. So, and since our problematic node always gets closer to the root at each step, I mean after each swap, we conclude that the running time of change priority procedure is also at most big O of the tree height. There is an elegant way of removing an element from the binary max heap. Namely, it can be done just by calling two procedures that we already have. So assume that we have a particular element that we are going to remove. So the first step to do is we just change its priority to plus infinity. That is to a number which is definitely larger than all the elements in our binary max heap. When we call it, the change priority procedure will shift this element to the top of our tree, namely to the root of our tree. Then to remove this element, it is enough to call the extract max procedure, right? So in this particular example, it will work as follows. So assume that we're going to remove the element 18, which is highlighted here on the slide. So we first change its priority to infinity. Then the change priority procedure calls shift up procedure. This procedure realizes that the property is violated on this edge and swaps these two elements. Then it swaps the next two elements, and at this point, well, the node that we are going to remove is at the root. Well, to remove this node, we just call the extract max procedure. So recall that extract max, the first step of extract max is to replace the root node with any leaf. So let's select, for example, 11. So we replace the root with 11. Then we need to call shift down. Well, just to let this new root to go closer to the leaves. Well, in this case, 11 will be replaced first by 42. Then there is still a problem on the edge from 11 to 18. So we swap 11 with 18, and finally we swap 11 with 12. Well, once again, since everything boils down just to two procedures, first is change priority and the second one is extracting max, and they both work in time proportional to the tree height, so we conclude that the running time of the remove procedure is also at most big O of the tree height. So to summarize, we were able to implement all max binary heap operations in time proportional to the tree height. And the get max procedure even works in constant time in our current implementation. So we definitely would like to keep our trees shallow, and this will be the subject of our next video. Our goal in this video is to design a way of keeping the height of our binary max heap shallow. Well, what is a natural approach to create a tree out of n given nodes whose height is as small as possible? Well, it is natural to require that all the levels are fully packed, right? This leads us to a notion of a complete binary tree. By definition, a binary tree is called complete if all its levels are filled completely, except possibly the last one, where we require additionally that all the nodes at this last level are in leftmost positions. Let me illustrate this with a few small examples. So this is a complete binary tree. This is also a complete binary tree. And this is also a complete binary tree. This is a binary complete tree too. And this is our first example of a binary tree which is not complete. Well, it is not complete because on the last level, the two nodes shown here are not in the leftmost positions. This is also not a complete binary tree. This binary tree is also not complete because, well, this child is missing here, right? And this is also an example of a binary tree which is not complete. The first advantage of complete binary trees is straightforward, and it is exactly what we need actually. Namely, the height of any complete binary tree within nodes is big O of log n. Intuitively, this is clear. A complete binary tree within nodes has the minimum possible height over all binary trees within nodes. Well, just because all the levels of this tree, except possibly the last one, are fully packed. Still, let me give you a formal proof. Well, for this, consider our binary tree and let me our complete binary tree, and let me show a small example. So assume that this is our complete binary tree. So in this case, n is equal to 10, and the number of levels L is equal to 4. Well, let's first do the following thing. Let's complete the last level. And let's denote the resulting number of nodes by n prime. In this case, in particular, the number of nodes in the new tree is equal to 15. Well, the first thing to note is that n prime is at most 2n. Well, this is just because in such a tree where all levels, including the last one, are fully packed, the number of nodes on each level is equal to the number of nodes on all the previous levels minus 1. Okay, so for example, here the number of levels on the last level is 8, and the number of nodes on all previous levels is 7. So we added at most 7 vertices. Now, when we have such a tree where all the levels are packed completely, it is easy to relate the number of levels with the number of vertices, namely with the number of nodes. Namely, n prime is equal to 2 to the L minus 1. This allows us to conclude that L is equal to binary logarithm of n prime plus 1. Now, recall that n prime is at most 2n, which allows us to write that L is at most binary logarithm of 2n plus 1, which is of course big O of just log n. The second advantage of complete binary trees is not so straightforward, but fortunately it is still easy to describe. To explain it, let's consider again a toy example. I mean a complete binary tree shown here on the slide. Let's enumerate all its nodes going from top to down and on each level from left to right. So this way the root receives number 1, to its children receive numbers 2 and 3, and so on. So it turns out that such a numbering allows for each vertex number I, for example, to be specific, to compute the number of its parent and the numbers of its children using the following simple formulas. Once again, if we have a node number I, then its parent has number I divided by 2 and rounded down, while its two children have numbers 2i and 2i plus 1. To give a specific example, assume that I is equal to 4. Which means that we are speaking about this node. Then, to find out the number of its parent, we need to divide I by 2. This gives us 2, and indeed vertex number 2 is a parent of vertex number 4. While to find out the numbers of two children of this node, we need to multiply I by 2. This gives us this node, and multiply I by 2 and add 1, and this gives us this node. And these two nodes are indeed children of vertex number 4, right? And this is very convenient. This allows us to store the whole complete binary tree just in an array. So we do not need to store any links for each vertex to its parent and to its two children. So these links can be computed just on the fly. Again, to give a concrete example, assume that we are talking about vertex number 3. So in this case, I is equal to 3. To find out the number of its parent, we just divide I by 2 and round down. So this gives us vertex number 1, and indeed vertex number 1 is the parent of the vertex number 3. And to find out the numbers of its two children, we just multiply I by 2 and also multiply I by 2 and add 1. This gives us, in this case, vertices number 6 and vertex number 7. So, and we know its indices in the array. Okay, we've just discussed two advantages of complete binary trees. And it would be too optimistic to expect that these advantages come to us at no cost. So we need to pay something. And our cost is that we need to keep the tree complete, right? We need to ensure that at each point of time, our binary tree is complete. Well, to ensure this, let's just ask ourselves what operations change the shape of our tree. Essentially, these are only two operations, namely insert and extract max. So two operations, sift up and sift down, they actually do not change the shape of the tree. They just swap some two elements inside the tree. Another operation which actually changes the shape is remove an element. However, it does so by calling the extract max procedure. So in the next on the next slide, we will explain how to modify our insert and extract max operations so that they preserve completeness of our tree. To keep a tree complete, when we insert something into a complete binary tree, we just insert the new element as the leaf to the leftmost vacant position on the last level. Well, an example is given here. So we insert element 30 just to the right of the last element on the last level. Okay, then we need to let this new element sift up, so we perform a number of swaps. So 30 is swapped with 14, then still there is a problem, so 30 is greater than 29, so we swap it again. Okay, now the property of the heap is satisfied for all the edges. Well, when we need to extract the maximum value, recall that we first replace the root by some leaf. Well, in this case, to keep the tree complete, let's just select the last leaf at the last level. In this case, it is 14. So we replace 42 with 14, and then again perform a number of swaps required to satisfy the property of the heap. Okay, so in this case, 14 is swapped with 30, and then 14 is swapped with 29. This gives us a correct heap whose underlying tree is a complete binary tree. Well, so far so good. We now know how to maintain the tree complete and how to store it in an array. In the next video, we will show the full pseudocode of the binary max heap data structure. In this video, we provide the full pseudocode of the binary max heap data structure. Okay, we will maintain the following three variables. Age is an array where our heap will stay. Max size is the size of this array, and at the same time, it is the maximum number of nodes in our heap. And size is the actual size of our heap. So size is always at most max size. So let me give you an example. In this case, we're given a heap of size 9, and it is stored in the first 9 cells of our array age, whose size is 13. In particular, you may notice that there are some values here, and it is actually some garbage. We just don't care about any values that stay to the right of the position number 9. So our heap occupies the first 9 positions in the array. Also, let me emphasize once again that we store just the array age and also variables size and max size. So this tree is given to us implicitly. Namely, for any node we can compute the value, the number of its parent and the number of its two children. And we can compute it and access the corresponding value in this array. For example, if we have node number 3, then we can compute the index of its left child, which is 2 multiplied by 3. So the value of its right child is 18. These are implementations showing how to find, given a node I, the index of a parent of I and two children of I. So they just implement our formulas in a straightforward way. To sift element I up, we do the following. While this element is not the root, namely I is greater than 1, and while the value of this node is greater than the value of its parent, we do the following. We swap this element with his parent. So this is done in this line. And then we proceed with this new element. I mean, we assign I to be equal to parent of I, and go back to this while loop. And we do this until the property is satisfied. To shift an element number I down, we first need to select the direction of shifting. Namely, if element number I is smaller than one or two of its children, we first need to select the largest one of its two children. Right? So this is done here. So initially we assign to the variable max index the value of I. Then we compute the index of the left child of the node number I. Then in the next if loop, we first check whether I indeed has a left child. This is done in the following check. We check whether L is at most size, namely whether L is the index which is in our heap. Okay? Then if h of L is greater than h of max index, we assign max index to be equal to L. Okay? Then we do the same with the right child. We first compute its index, then we check whether this index is indeed in our heap, then we check whether the value in this node is greater than the value of our currently maximum index, and if it is, then we update the value of max index. And finally, if the node I is not the largest one among itself and to its children, namely if I is not equal to max index, then we do the following. We swap element number I with element number max index. It is done here. And then we continue shifting down the just swapped element. Okay, so this is done recursively. However, it is not so difficult to avoid using recursion here, just by introducing a new while loop. To insert a new element with priority p in our binary max heap, we do the following. We first check whether we still have room for a new element, namely whether size is equal to max size. If it is equal, then we just return an error. Otherwise, we do the following. We increase size by 1, then we assign h of size to be equal to p. At this point, we add a new leaf in our implicit tree to the last level, to the leftmost position on the last level. And finally, we call shift up to shift this element up if needed. To extract the maximum value from our binary max heap, we first store the value of the root of our tree in the variable result. So result is assigned to be equal h of 1. Then we replace the root by the last leaf, I mean by the rightmost leaf on the last level. So this is done by assigning h of 1 to be equal to h of size. Okay? Then we decrease the value of size by 1 just to show that the last leaf is not in our tree anymore. And finally, we call shift down for the root because it was replaced by the last leaf, which is potentially quite small and needs to be shifted down. And the last instruction in our pseudocode is we return the result. I mean the value which was initially in the root of our tree. Removing an element. So as we've discussed already, this actually boils down to calling two procedures that we already have. Once again, to remove element number I, we do the following. First, we change its priority to be equal to infinity. So we assign h of I infinity, plus infinity. Then we shift up this node. So this will move this node to the root of our tree. And then we just call extract max procedure, which will remove the root from this tree and make necessary changes in the tree to restore its shape. Finally, to change the priority of a given node I to the given value p, we do the following. We first assign h of I to p. Okay? Then we check whether the new priority increased is greater than the old priority or is smaller. If it is greater, then potentially we need to shift up the new node, so we just call shift up. If the new priority is smaller, then we call shift down for this node. Time to summarize. In this sequence of videos, we considered the binary max heap data structure, which is a popular way of implementing the priority queue data type. The considered implementation is quite fast. All operations work in logarithmic time, and getMax procedure works even in constant time. It is also space efficient. In this data structure, we store a tree, but this tree is stored implicitly. Namely, for each node, we do not store a connection or a link to its parent and its two children. Instead, we compute the index of the corresponding nodes on the fly. Well, in this case, we store just n given cells in an array, nothing more. Okay, another advantage of this data structure, of this implementation, is that it is really easy to code. As you've seen, the pseudocode of each operation is just few lines of code. Well, in the next video, we will show how to use binary heap to sort data efficiently. In this video, we will use binary heaps to design the heap sort algorithm, which is a fast and space-efficient sorting algorithm. In fact, using priority queues or using binary heaps, it is not so difficult to come up with an algorithm that sorts the given array in time big O of n log n. Indeed, given an array A of size n, we do the following. First, just create an empty priority queue. Then insert all the elements from our array into our priority queue. Then extract the maximum one by one from the given array. Namely, we first extract the maximum, so this is the maximum of our array, so put it to the last position. Then extract the next maximum and put it to the left of the last position, and so on. This clearly gives us a sorted array, right? So we know that if we use binary heaps as an implementation for priority queue, then all operations work in logarithmic time. So this gives us an algorithm with the running time big O of n log n. And recall that this is asymptotically optimal for algorithms that are comparison based. And this algorithm is clearly comparison based, right? Also note that this is a natural generalization of selection sort algorithm. Recall that in selection sort algorithm we proceed as follows. Given an array, we first scan the whole array to find the maximum value. So then we pick this maximum value and swap it with the last element. Then we forget about this last element and we consider only n-1 first elements. Again, by scanning this array, we find the maximum value and we swap it with the last element in this region, and so on. So here in the heap sort algorithm, instead of finding the maximum value at each iteration naively, we use a smart data structure, namely a binary heap, right? So the only disadvantage of our current algorithm is that it uses additional space. So it uses additional space to store a priority queue, okay? So in this lesson, we will show how to avoid this disadvantage. Namely, given an array A, we will first permute its elements somehow so that the resulting array is actually a binary heap. So it satisfies a binary heap property. And then we will sort this array again just by calling extract max n times or n-1 times. Building a heap out of a given array turns out to be surprisingly simple. Namely, given an array A of size n, we do the following. We first assign the value of n to the variable size, just to indicate that we have a heap of size n. Then we do the following. For each I going down from n over 2, rounded down to 1, we just sieve down the ith element. Let me explain it on a small picture. Why are we doing this? So consider the following heap that we actually, let me remind you, we do not store it explicitly. We have just an array, in this case of size 15. So this is the first node, the second one, the third one, 4, 5, 6, 7. So if we just consider the corresponding array of size 15 and imagine this complete binary tree, then the heap property might potentially be violated on many edges. However, in this tree we have 15 nodes, so we have 15 subtrees. And for these subtrees, I mean rooted at the leaves of this tree, the heap property is satisfied for an obvious reason. There are no edges in these subtrees. So the first node where the property might be violated is node number 7. So potentially there might be a problem in this subtree. To fix this problem, we just call sift down for node number 7. Okay? After this call, this small subtree must be a heap. Right? Then we do the same for node number 6. After this call, there are no problems in the subtree rooted at node number 6. Then we do the same for I equal to 5 and for I equal to 4. Then we proceed to node number 3. Note that at this point everything is fine in this subtree and in this subtree. Right? We already fixed everything in these two subtrees. So to satisfy the heap property in the subtree rooted at the node 3, it is enough to call sift down for node number 3. Okay? Then we proceed to node number 2, and again after calling sift down to node number 2, we fix the heap property in this subtree, and so on. So in this example, actually the last thing that needs to be done is to call sift down for node number 1. When we are done with this, we are sure that what we have in array A is actually a heap. So it corresponds to a complete binary tree where the heap property is satisfied on every edge. Let me repeat slowly what have just happened. So to turn a given array into a heap, we start repairing the heap properties in larger and larger subtrees. So we start from the leaves and go to the root. Initially, so our induction base is that the heap property is satisfied at all the leaves, I mean in all subtrees rooted at the leaves, for an obvious reason. Any subtree rooted at a leaf has just one node, so the property cannot be violated. Right? Then we gradually go up and we fix the heap property by sifting down the current vertex. And finally, when we reach a root, the property is satisfied in the wall subtree. Right? So this is just a link for an online visualization. You can download the slides and play with this visualization if something is unclear to you in this process. Let me now mention that the running time of this procedure is n log n, again for an obvious reason. So we use a binary max heap to implement the sift down procedure. So we call sift down roughly n over 2 times, and each call is just log n, right? So we have n log n running time. We already have everything to present the in-place heap sort algorithm. Given an array A of size n, we first build heap out of it. Namely, we permute its elements so that the resulting array corresponds to a complete binary tree which satisfies the heap property on every edge. So we do this just by calling build heap procedure. In particular, this build heap procedure assigns the value n to the variable size. Then we repeat the following process n-1 times. So we first recall that just after calling to build heap, the first element of our array is the maximum element, right? So we would like to put it to the last position of our array. So we just swap a1 with a of n, and currently a of n is equal to a of size. Okay, so we swap it, then we forget about the last element, so we decrease size by 1. So we say that now our heap occupies the first n-1 elements. And since we swapped the last element with the first element, we potentially need to sift down the first element. So we just call sift down for the element number 1. And we proceed in a similar fashion. I mean, now the heap occupies n-1, the first n-1 positions, so the largest element among the first n minus 1 element is the first element, so we swap it with element number n minus 1. We forget about the element n minus 1 by reducing the size by 1, and then we sieve down the first element. Okay, so we repeat this procedure n minus 1 times, each time finding the currently largest element. So once again, this is an improvement of a selection sort algorithm, and this is an in-place algorithm. So once again, let me state some properties of the resulting algorithm, which is called heap sort. It is in place. It doesn't need any additional memory. Everything is happening inside the given array A. So this is an advantage of this algorithm. Another advantage is that its running time is n log n. It is asymptotically optimal. So this makes it a good alternative to the quicksort algorithm. So in practice, quicksort is usually faster. It is still faster. However, the heap sort algorithm has worst case running time n log n, while the quicksort algorithm has average case running time n log n. For this reason, a popular approach in practice is the following. It is called intrasort algorithm. You first run quicksort algorithm. If it turns out to be slow, I mean, if the recursion depth exceeds c log n for some constant c, then you stop the current call to quicksort algorithm and switch to heap sort algorithm, which is guaranteed to have running time n log n. So in this case, in this implementation, your algorithm usually, in most cases, it works like quicksort algorithm. And even in these unfortunate cases where it works in larger, where quicksort has running time larger than n log n, you stop it at the right point of time and switch to heap sort. So this gives you an algorithm which in many cases behaves like quicksort algorithm, and it has worst case running time at most big O of n log n. In this video, we are going to refine our analysis of the build heap procedure. Recall that we estimated the running time of the build heap procedure as n log n because it consists actually of roughly n over 2 calls to sieve down procedure, whose running time is log n. So we get n over 2 multiplied by log n, which is of course big O of n log n. Note, however, the following thing. If we call sieve down for a node which is already quite close to the leaves, then the running time of sifting it down is much less than log n, right? Because it is already close to the root. So the number of swaps till it goes to the leaves cannot be like larger than the height of the corresponding subtree. Okay? Note also the following thing. We actually, in our tree, we actually have many nodes that are close to the root. So we have just one node, which is exactly the root, whose height is log n. We have two nodes whose height is log n minus 1. We have 4 nodes whose height is log n minus 2, and so on. And we have roughly n over 4 nodes whose height is just 1. Okay? So it raises the question whether our estimate of the running time of build heap procedure was too pessimistic. We will see on the next slide. Let's just estimate the running time of the build heap procedure a little bit more accurately. Okay, so this is our heap shown schematically. So this is the last level, which is probably not completely filled, but all the leaves on the last level are in leftmost position. So on the very top level, we have just one node, and sifting down this node costs logarithmic time, right? At the same time, on the last level, we have at most n over 2 nodes, and sifting them down makes at most one swap. Actually, we do not need even one swap, just 0 swaps, but let's be just generous enough and let's allow one swap. On the next level, we have at most n over 4 nodes, and sifting down for them costs at most 2 swaps, and so on. So if we just compute the sum of everything, so we have n over 2 nodes for which the cost of the swap of the sieve down procedure is 1. We have n over 4 nodes on the next level for which shifting them down makes at most 2 swaps. On the next level we have n over 8 nodes, for which shifting them down costs at most 3 swaps, and so on. So now let's do the following. Let's just upper bound the sum by the following sum. First of all, let's take the multiplier n out of this sum. So which is left? What is left here is the following: 1 over 2 plus 2 over 4 plus 3 over 8 plus 4 over 16 plus 5 over 32, and so on. Right? So this can be upper bounded by the following sum. So this is just a sum from I equal to 1 to infinity of the following fraction, I divided by 2 to the I. Once again, in our case, in the running time of build heap, this sum is finite, right? So the maximum value of I is log n. We do not have any nodes on height larger than log n. So, but we just upper bound it by an infinite sum, where we consider just all possible values of I. And even for this sum, we will show that the value of this sum is equal to 2, right? Which gives us that the running time of the build heap procedure is actually at most 2n. To estimate the required sum, we start with a simpler and more well-known sum. So this is given by the following picture, and the sum is given here. So 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 and so on, it is equal to 1. And this can be proved geometrically as follows. Consider a segment of length 1. Now, above this segment, let's draw a segment of size 1 over 2, of length 1 over 2. Okay, this is half of our initial segment. What remains is also a segment of size 1/2. So when we add a segment of size 1 over 4 here, we actually get 2 times closer to this vertical line, right? When we add the next one, 1 over 8, we get again 2 times closer than we were before adding this segment to this vertical line. When we add 1 over 16, again our current distance to the vertical line is 1 over 16, and so on. So if we go to infinity, we get infinitely closer to this vertical line, which means that this sum is equal to 1. Now, what about the sum that we need to estimate? Well, to estimate it, let's first do the following strange thing. Let's consider all the segments shown above, and let's adjust them by their right end. So consider the segment 1, shown here. Now consider the segment of length 1 over 2, the segment of length 1 over 4, segment of length 1 over 8, and so on. So we continue this process to infinity, and we know that the sum of the lengths of all these segments is equal to 2, of course. Now, why we are doing this? So, well, for the following reason. First, consider the following vertical lines. What we need to estimate is the following sum: 1 over 2 plus 2 over 4 plus 3 over 8 plus 4 over 16, and so on. Let's see. So this is a segment of size 1 over 2. Okay. This is 2 segments of size 1 over 4. Okay. So this is 3 segments of size 1 over 8, of length 1 over 8, and so on. So if we put another vertical line, we will get 4 segments of size 1 over 16, and so on. So if we do this to infinity, we will cover all our segments that are shown here, which proves that this sum is equal to 2, which in turn proves that the running time of our build heap procedure is actually just linear. It is bounded above by 2n. Our new estimate for the running time of the build heap procedure does not actually improve the running time of the heap sort algorithm. Because the heap sort algorithm first builds a heap, and now we know that it can be done in a linear time, but then we need to extract max n-1 times. And so we still have n log n time, and actually we cannot do better than n log n. Asymptotically, we already know this, because it is a comparison-based algorithm. However, this helps to solve a different problem faster than naively. So assume that we're given an array and we're given a parameter k, which is an integer between 1 and n. And what we would like to do is not to sort the given array, but to find the k largest elements in this array. Or put it otherwise, we need to output the last k elements from the sorted version of our array. So using the new estimate for the build heap procedure, we can actually solve this problem in linear time when k is not too large. For example, when k is at most big O of n divided by log n. For example, if you have an array of size n and you would like just to find square root of n largest elements, then you can solve this just in linear time. So you do not need to sort the whole array in time n log n to solve this problem. So linear time is enough to solve it. And this is how it can be done. Given an array A of size n and parameter k, you just build a heap out of a given array. And then you extract the maximum value k times, right? So easy. The running time of this procedure is the following. First, you need to build a heap. So you spend a linear amount of work for this. Then you need to extract max k times. For this you spend k multiplied by log n. So if k is indeed smaller than n divided by log n, so let me write it. So if k is smaller than n divided by log n, then this is at most n. So the whole running time is at most linear. So to conclude, what we've presented here is a heap sort algorithm, which actually sorts a given array in place without using any additional memory and in optimal time n log n. We also discussed that to build a heap out of a given array, it actually enough to spend a linear amount of work. We conclude the whole lesson by a few remarks. First of all, for implementing a binary heap in an array, we can as well use zero-based arrays. In this case, the formulas for computing the parent and the index of the parent and two children of a given node are changed as follows. So the parent of I is given by the number I-1 divided by 2 and rounded down. The left child is given by the number 2i plus 1, and the right child is given by 2i plus 2. The next remark is that you can implement a binary mean heap in exactly the same way. A binary mean heap is a heap where at each edge the value of a parent is at most the value of the child. Okay, so this is useful for the case when at each iteration or just in your priority queue you need to extract an element not with maximum priority but with minimum priority. The final remark is that binary heaps can be easily generalized to d-array heap. In such a heap, each node has at most d children. And we require, well, to call a d-array heap complete, we again require that all the levels are completely filled, except for possibly the last one, where all the nodes are in leftmost position. Okay, so the height of this tree is in this case log base d of n, not a binary log of n. This in particular means that the running time of the sift tab procedure is at most big O of log base d of n, right? Just because the height of the tree is at most log base d of n. And the element just goes down, just goes up. If needed, we swap an element with its parent. However, the running time of sift down procedure increases to d multiplied by log base d of n. This is because when we go down, we always need to find a direction where to go, in which of these subtrees to go. And this is because when we need to replace, to swap a node with one of its children, we first need to select which one of these D children is the largest one. Right? So for this reason, the running time of sift down procedure in this case is big O of D multiplied by log base D of n. Okay, time to conclude. In this sequence of lessons, we started by introducing the abstract data type called priority queues. This abstract data type supports the following two main operations: insert an element and extract an element with the highest priority. These priority queues find a lot of applications. We will see many algorithms that use efficiently this data type. Then we explained that if implemented naively using an array or a list, sorted or not, one of these two operations will take a linear amount of work in the worst case. Then we presented binary heaps. So this is a way of implement priority queues that gives a worst case running time big O of log n for all operations. And also, finally, we explained that this also can be made space efficient. Namely, a binary heap is a tree. However, to store this tree, we do not need to store connections to a parent and to two children. It is enough to store everything in an array. Again, this makes binary heaps both time and space efficient. Hello and welcome to the next lesson of the data structures class. It is devoted to disjoint sets. As a first motivating example, consider the following maze shown on the slide. It is basically just a grid of cells with walls between some pairs of adjacent cells. A natural question for such a maze is, given 2 points, given 2 cells in this maze, whether there is a path between them. For example, for these 2 points, for these 2 cells shown on this slide, there is a path, and it is not too difficult to construct it. Let's do this together. So this is, we can go as follows. And there is actually another path here. We can also go this way. Right? On the other hand, there is no path between these 2 points shown on the slide, and to show this, we might want to construct just a set of full points that are reachable from B. Let's again do this. So let's just mark all the points that are reachable from B. So it is not difficult to see that we marked just every single point which is reachable from B, and we now see that A does not belong to this set, which actually justifies that A is not reachable from B in this case. The maze problem can be easily solved with the help of disjoint set data structure, which supports the following 3 operations. The first operation is called make set. It takes one argument x, and it creates just a set of size 1 containing this element x. The second operation is called find. It takes an argument x and returns an ID of the set that contains this element x. Well, we expect this ID to satisfy the following 2 natural properties. If x and y, if 2 elements x and y lie in the same set, then we expect the operation find to return the same ID, both for x and y. Well, just because x and y lie in the same set, and find returns some identifier of this set, right? If, on the other hand, x and y lie in different sets, then find of x should not be equal to find of y, right? The last operation is called union, and it takes 2 arguments, x and y, and then it considers 2 sets containing x and y, and it merges them. In particular, if we first call union of x and y, and right after this we call to find of x and find of y, then these 2 calls to to find operation should return exactly the same identifier, just because X and Y after the call to union lie in the same merged set. Recall that our maze example, to show that a particular point B is not reachable from a particular point A, we did the following. We first constructed the region of all cells reachable from this point B in our maze. We then just checked that point A does not belong to this region. So this was a justification of the fact that A is not reachable from B in our maze. And in fact, any maze can be partitioned into disjoint regions, where in each region, between any two cells, there is a path, right? And using the disjoint sets data structure, it is easy to partition any maze into such disjoint regions. We can do this by preprocessing the maze as follows. We first call make set for all cells C in our maze. This creates a separate region for each cell. So initially we have as many regions as there are cells in our maze. Then we do the following. We go through all possible cells in our maze. So when a cell C is fixed, we also go through all possible neighbors of this cell in our maze. We say that N is a neighbor of C if N is an adjacent cell of C and there is no wall between them. So at this point, C belongs to some region and N belongs to some region. And we've just discovered the fact that there is a path between C and N, which means that actually any cell from this region is reachable from any cell from this region, right? To reflect this fact, we just call union of C and N. This creates a separate set for these two regions. This merges these two regions. Right? So after the call to this preprocessing procedure, each region in this maze receives a unique ID. Right? So then to check whether a particular cell is reachable from some other cell, we just need to check whether the find operation returns the same for them or not. To give another example of using the disjoint sets data structure, assume that we are building a network. Initially, we have 4 machines. We call make set of 1 for the first machine, make set of 2 for the second machine, and so on. So to reflect the fact that initially each machine lies in a separate set. In particular, if we now check whether find of 1 is equal to find of 2, then it is false, just because 1 and 2 lie in different sets. Now let's add a wire between the third machine and the fourth machine. To notify our data structure that now 3 and 4 belong to the same set, we call union of 3 and 4. Okay? Now let's introduce the fifth machine. So we do this by calling make set of 5. Then let's add another wire between the second machine and the third machine. To notify our data structure about this event, we call union of 3 and 2. If we now call find of 1 and find of 2, these two calls should return different values, because 2 and 1, machines 2 and 1, still belong to different sets. Okay? Now we add a wire between the machines 1 and 4. And now, yes, to notify our data structure about this event, we call union of 1 and 4. And now, if we check whether find of 1 is equal to find of 2, it should return true, just because now 1 and 2 lie in the same set that contains machine 1, 2, 3, and 4. Later in this specialization, we will learn the Kruskal algorithm, which builds a network of a given set of machines in an optimal way and uses the disjoint set data structure essentially. Now, when we've seen a few examples of using the disjoint set data structure and when we formally defined it, let's start to think about possible ways of implementing it. As usual, we will start with a few naive implementations that will turn out to be slow on one hand, but on the other hand, they will help us to come up with an efficient implementation. First of all, let us simplify our life by assuming that our n objects are just integers from 1 to n. This in particular will allow us to use these objects as indices in arrays. Okay, so our sets are just sets of integers, and we need to come up with a notion of an ID, of a unique ID for each set. So let's use the smallest element in each set as its ID. In particular, since our objects are integers, for each element we can store the ID of the set this element belongs to in the array called smallest. For example, if we have the following three sets, then in the first set the ID, namely the smallest element, is 2, in the second set the smallest element and the only element is 5, in the third set the smallest element is 1. And this information is stored in the array called smallest of size 9. The operations make set and find can be implemented in just one line of code in this case. Namely, to create a singleton set consisting of just element I, we set smallest of I to be equal to I, right? To find the ID of the set containing the element I, we just return the value of smallest of I. The running time of both these operations is constant. Everything is not so easy with the union operation, unfortunately. So to merge two sets containing elements I and j, we do the following. First, we find out the ID of the set containing the element I. We do this by calling find of I, and we store the result in the variable I ID. Then we do the same for the element j. We call find of j, and we store the result in ID in the variable j ID. Then we check whether I ID is equal to j ID. And if they are equal, this means that I and j already lie in the same set, which means that nothing needs to be done, which means in turn that we can just return. If I ID and j ID are different, we do the following. Well, we need to merge two sets. The smallest element in this set is I ID. The smallest element in this set is j ID, which means that the smallest element in the merged set should be just the minimum among I ID and j ID. We store this minimum in the variable m. Then we need to scan all the objects, all our n objects, and update the ID of each and update the value of the smallest array for each object for which the ID is IID or JID. So this is done in the loop here, where k ranges from 1 to n. So we check whether smallest of k is equal to IID or JID, and if it is equal, then we update it to be equal to m. The running time of this operation is linear, of course, just because essentially what we have here is a single loop that goes over all n objects. The bottleneck of our current implementation is the union operation, whose running time is linear, as opposed to the finite make set operations, whose running time is just constant. So we definitely need another data structure for storing sets, which allows for more efficient merging. And one such data structure is a linked list. So let's try to use the following idea. Let's represent each set just as a linked list, and let's use the tail of a list as the ID of the corresponding set. Let me illustrate this with a toy example. In this case, we have two sets. Each one of them is organized as a linked list, and we treat the tail of a list as the ID of the corresponding set. For example, in this case, 7 is the ID of the first set, and 8 is the ID of the second set. Note that to find the ID of the set that contains the element 3, for example, we just follow the pointers till we reach the tail of the corresponding list. So in this case, ID is well defined. What is also nice is that in this case we can merge two sets very efficiently. Actually, since they are organized as lists, we just need to append one list to the end to the other list, and this requires changing just one pointer. What is very nice in this case is just the ID of the merged set is updated automatically, right? So after the merging, the head of the resulting list is 8. So the ID is updated for all the elements of two sets automatically. As we've just discussed, there are at least two advantages of the current implementation where we store each set as a linked list. First of all, the running time of the union operation is, in this case, is just constant. This is because to merge two linked lists, we just append one of them to the other one. And for this we need just to change one pointer. Another advantage is that we have a well-defined ID in this case. Namely, if two elements lie in the same set, then find will return the same tail element from the corresponding list, right? And also, if two elements lie in different sets, then the tails of the corresponding two lists are different. And this is exactly what we want. There are, however, also two disadvantages. The first disadvantage is that now the running time of the find operation is linear in the worst case. This is because to find the tail of the corresponding list, I mean, given an element, we would like to find the corresponding tail of a list. For this, we need to follow the pointers till we reach the tail of this list. For this, we might need potentially to traverse a linear number of elements, because the list might contain a linear number of elements. So in the worst case, the running time of find operation is linear, which is not so good. The second disadvantage is that actually implementing union operation is not so in constant time, is not so easy as it was shown on our previous toy example. Namely, we assumed implicitly in this example that when given two elements x and y, we can find the beginning of the list containing x and the end of the list containing y in constant time. So to be able to do this, we might need to store some additional information. And this in turn will require us to update this information when we merge two elements. So once again, this means that to implement union procedure in constant time, we need to store some additional information, but not just pointers from a particular element to the next element. In search of an inspiration for improving our current implementation, let's review our previous toy example. So we've discussed that merging these two sets shown on the slide as follows is good because it requires just constant time and it updates the ID of the resulting set automatically. On the other hand, it is bad because it creates a long list. This in particular requires find of 9 to traverse the whole list, and this makes find operation a linear time operation, right? So let's try to think about a different way of merging these two lists. For example, what about the following one? In this case, first of all, the resulting structure is not a list, which is strange, right? However, it is still constant time, right? And it also 7 can still be considered as the ID of the resulting set, because 7 is reachable from any other element, right? However, so what about this structure? It is not a list, but it is a tree, right? So it is a tree whose root is 7 and that has 2 branches, right? In the next video, we will develop this idea to get a very efficient implementation of the disjoint sets data structure. Namely, we will represent each set as a tree, and we will show that in this case, the running time, the amortized running time of each operation is nearly constant. Hi! In the previous video, we considered a few naive implementations of the disjoint sets data structure. In one of them, we represented each set as a linked list. Let me give you a small example. So these 4 elements are organized into a linked list, and we treat the tail of this element, of this list, so this last element, as the ID of the corresponding set. And this is a well-defined ID because it is unique. It is unique for any list, and it can be easily reached from any other element in the corresponding set. So if we need to find the ID of the set that contains this element, we just follow the next pointers shown here till we reach the tail of this list. Another advantage is that merging two sets is very easy in this case. So assume that this is our first set, and the second set looks as follows. Then to merge these two sets, we just append one of the lists to the other one, like this. The first advantage of this merging is that it is clearly constant time. We just change one pointer. Another advantage is that it updates the ID of the resulting merged list automatically. Now we treat this element as the ID of the resulting list. Right? It still can be reached from any other element of this list just by following these pointers. The main disadvantage of this approach is that over time lists get longer and longer, which in turn implies that the find operation gets slower and slower. Well, we then discussed another possibility to merge two lists. Namely, we can do the following. Again, consider the same two lists. And now assume that instead of just appending one list to the other one, we do the following strange thing. We just change this pointer as follows. Well, as you see, what we get is not actually a list, right? However, it is a tree. It is a tree whose root is this element and that has two branches. So we do not get a long list, but instead we get a tree. And in this tree, we can still treat this last element, this root element, as the ID of the corresponding set, because it is unique for this tree, and also it can be reached from any other element. So in this lesson, we are going to further develop this idea. By doing this, we will eventually get a very efficient implementation of the disjoint sets data structure. The general setting is the following. Each set is going to be represented as a rooted tree. We will treat the root of each tree as the ID of the corresponding set. For each element, we will need to know its parent, and this will be stored in the array parent of size n. Namely, parent of I will be equal to j if element j is the parent of I, or in case I is the root, then parent of I will be equal to I. So this is a toy example. Here we have three trees, and there are three roots, 5, 6, and 4. And these three trees are stored in the array parent as follows. For example, to indicate that 4 is the root, we store 4 in the 4th cell of this array. To indicate that 9 is the parent of 7, we put 9 into the 7th cell. Recall that make set of I creates a singleton set consisting of just a single element I. To do this, we just assign parent of I to be equal to I. This creates a tree whose only element is I, and this is the root of this tree. So for this reason, we assign parent of I to be equal to I. The running time of this operation is, of course, constant. To find the root of the tree that contains a given element I, we just follow the parent links from the node I till we reach the root. This can be done as follows. While I is not equal to parent of I, namely while I is not the root of the corresponding tree, we go from I, we replace I by its parent. So each time we go closer to the root, and eventually we will reach root, and at this point we return the resulting element. The running time of this operation is, of course, at most the height of the corresponding tree. Now we need to design a way of merging two trees. And there is a very natural idea for doing this. We have two trees. Let's just take one of them and camp under the root of the other one. Let me illustrate it with a small example. Assume that this is our first tree. It contains just 3 nodes, and this is the root of this tree, so it points to itself. And this is our second tree. This is the root, so it points to itself again. To merge these two trees, we just change one pointer. Namely, we say that now this node is not the root anymore, but its parent is this node. Right? So we hang the left tree under the root of the right tree. Once again, this node is not the root anymore, while this node is the root of the resulting tree. And at this point, there is a natural question. We can hang the left tree under the root of the right tree, but also vice versa, we can hang the right tree under the root of the left tree. So which one to choose? And after thinking a little bit, we realize that it makes sense to hang a tree whose height is smaller under the root of the tree whose height is larger. And the reason for this is that we would like to keep our trees shallow. And in turn, the reason for this is that the height of the trees in our forest influences the running time of the find operation. Namely, the worst case running time of the find operation is actually at most the maximal height of a tree in our forest. To give a specific example, let's consider the following two trees shown on the slide. In this case, we have a tree of height 1 and a tree of height 2. Assume that we call union of 3 and 8. In this case, we need to merge these two trees, and as we've discussed already, there are two possibilities for doing this. Either we hang the left tree under the root of the right tree, or vice versa, we hang the right tree under the root of the left tree. The results of these two cases are shown here on the slide. And you see that in the left case, the height of the tree increased. And this is not something that we want, right? Because, as we've discussed, the height of this tree influences the worst case running time of the find operation. So this illustrates that to keep our trees shallow, when merging the two trees, we would like to hang a tree whose height is smaller under the root of the tree whose height is larger. Okay, when merging two trees, we're going to hang a shorter one under the root of a taller one. This means that when merging two trees, we need a way to quickly find the height of both trees. Instead of just computing them, we're going to keep the height of each possible subtree in our forest in a separate array called rank. Namely, rank of I is equal to the height of the subtree rooted at I. Okay? The reason we call it rank will become clear a little bit later. Let me also mention that this way of merging two trees based on their heights is called the union by rank heuristic. To keep the rank, we need a small addition to our make set implementation. Namely, when creating a singleton set, we also set rank of I to be equal to 0. This reflects the fact that it is currently just a root containing one node, just a tree containing one node, that is a tree of height 0. We do not need to change find. So the find operation doesn't need to change rank, and it also doesn't use rank in any way. To merge two trees containing the given two elements I and j, we do the following. We first find the roots of the corresponding two trees by calling the find operation 2 times. We store these roots in variables iid and jid. We then check whether iid is equal to jid. If they are equal, this means that I and j, elements I and j, already lie in the same set. So we just return in this case. So this is done in the following if loop. We then check whether the height of the tree containing element I is larger than the height of the tree containing element j. If it is larger, then we hang the tree with the root jid under the root of element iid. This is done as follows. Parent of jid is set to iid. Otherwise, we do the opposite thing. We just assign parent of iid to be equal to jid. The last thing is that we need to check whether the height of the corresponding two trees are just equal. Let me illustrate this again with a small example. Assume that we are merging the following two trees. In this case, the height of these two elements and this element is 0, and the height of this element is 1. So in this case, roots are equal. The ranks of the corresponding roots are equal. To merge these two trees, we do the following. We just hang the left tree under the root of the right tree. As you can see, in this case, the height of the resulting tree actually increases. And this is the only case when the union operation increases the height of this tree. So in this case, initially, the longest path contained just one edge. In this case, we got a path that contains two edges. So we need to update this ring. And this is done in the last check. So if initially the ranks of our two trees that are going to be merged are equal, we hang one of them under the root of the other one and increase the rank of the resulting tree by 1. Let's consider a small example. In this case, we have 6 elements. Let's call make set for each of these elements. This fills our data structure as follows. So currently, each element is its own parent, right? So its current set is just a singleton set. Also, the height of each subtree in our data structure is currently equal to 0. Now let's call union of 2 and 4. In this case, the rank of the subtree rooted at 2 is equal to 0. The height of the subtree rooted at 4 is equal to 0. So it doesn't mean which one to hang under the root of the other one. So let's hang 2 under 4. This changes the data structure as follows. Now the parent of 2 is 4, and the rank of the subtree rooted at 4 is equal to 1. Okay, now let's call union of 5 and 2. In this case, the height of the tree that contains the element number 2 is equal to 1, right? While the height of the tree that contains element number 5 is equal to 0. So in this case, we are going to hang 5 under 4. We do this as follows. So this changes the data structure this changes only this cell. So now 4 is the parent of 5, and it doesn't change any rank in our subtree, in our forest. Okay, now let's call union of 3 and 1. This is done as follows. Now 1 has rank 1, and now the parent of 3 is equal to 1. Okay, now let's call union of 2 and 3, and again, in this case, 2 lies in a set in the tree whose root is 4, and currently the rank of 4 is equal to 1. Also 3 lies in a set whose root is 1, and currently rank of 1 is equal to 1. Which means that after merging these two trees, we will get a tree of height 2. So we do this as follows. Now 1 is the root of the resulting tree, and its rank is equal to 2. Finally, we call union of 2 and 6, and this will just attach 6 to 1. As follows. In our current implementation, we maintain the following important invariant. At any point of time and for any node I, rank of I is equal to the height of the subtree rooted at this node I. Right? We will use this invariant to prove the following lemma. The height of any tree in our forest is at most binary logarithm of n. This will immediately imply that the running time of all operations with our data structure is at most logarithmic, right? To prove this lemma, we will prove another lemma shown here on the slide. We're going to prove that if we have a tree in our forest whose height is k, then this tree contains at least 2 to the k nodes. This will imply the first lemma as follows. Assume that some tree has height at more strictly greater than binary logarithm of n. Using the second lemma, it will be possible to show then that this tree contains more than n nodes, right? Which would lead to a contradiction with the fact that we only have n objects in our data structure. Here we are going to prove the second lemma by induction on K. Recall that we prove that any tree of height k in our forest contains at least 2 to the k nodes. We're going to prove this by induction on K. When k is equal to 0, this means that we have a tree just of height 0, which means that it contains just one node. So in this case, the statement clearly holds. Now, to prove the induction step, let's recall that the only way to get a tree of height k is to merge two trees whose height is equal to k minus 1. I mean to merge both trees such that the height of the first tree is equal to k minus 1 and the height of the second tree is equal to k minus 1. By the induction hypothesis, both of these two trees contain at least 2 to the k minus 1 nodes, which means that our resulting tree contains at least 2 to the k minus 1 plus 2 to the k minus 1 nodes, which is exactly equal to 2 to the k, right? Which means that the lemma is proved. To conclude, the running time of both union and find operations in our current implementation is at most logarithmic. Why so? Well, just because we keep our trees shallow. So the height of any tree in our forest is at most logarithmic. This immediately implies that the running time of any find operation is also big O of logarithm of n. Recall also that the union operation consists of two calls to the find operation and also a few constant time operations, which means also that the running time of union is also big O of log n. In the next video, we will see another beautiful heuristic, which will just decrease the running time of both these operations to nearly a constant. To build our intuition about the second heuristic for the disjoint sets data structure, let's again consider a toy example, shown here on the slide. Assume that we call find of 6. This will traverse the following path from 6 to the root of this tree. So let's note that in this case we find the root of the tree that contains element 6. But we also find the root of the tree that contains element 12 and contains element 3. In general, by traversing this path, we find the root for all the elements on this path. Right? So why lose this information? Let's just store it somehow. And one way to do this is, for example, to reattach all these nodes directly to the root. We can do this as follows. So now, as you can see, the parent of element 12, for example, is 5. And also the parent of element 6 is also 5. We've just attached them directly to the root. And this can only save us space in the future, right? Save us time, I'm sorry, in the future, for future calls of find operation. So this heuristic is called path compression. Implementing this heuristic, path compression heuristic, turns out to be surprisingly simple. It is actually only 3 lines of code. Here we do the following. We first check whether I is equal to parent of I. If it is equal, then it is the root, then we will just return the result. If it is not the root, if I is not the root, we do the following. We call find recursively for the parent of the node I. This is done here. So we call find for the parent of the node I. It will return the root of the corresponding tree. And then we set parent of I to be equal to the returned root. That is, we attach the node number I directly to the root. And we do this recursively for all the elements on this path. Finally, we return the new parent of I, which is now just the root of the corresponding tree. Before stating an upper bound on the running time of operations of our current implementations, we need to introduce the so-called iterated logarithm function, which is also denoted by log star of n. So by definition, the iterated logarithm of n is the number of times the binary logarithm should be applied to n before we get a number which is at most 1. Let me illustrate this with an example. So for n equal to 1, the binary logarithm of n is equal to 0. We do not need to apply binary logarithm to get a number which is at most 1, because n is already at most 1 in this case. For n equal to 2, we need to apply binary logarithm once to get a number which is at most 1. Namely, if we apply binary logarithm to 2, we just get the number 1. Okay? For n equal to 3 and 4, the binary logarithm is equal to 2, and so on. And for example, for the number shown here, 2 to the 6, 5, 5, 3, 6, if we apply binary logarithm once, then just by definition of binary logarithm, we get this number, just 6, 5, 5, 3, 6, which is 2 to 16. Okay, so if we apply the binary logarithm once again, we get 16. 16 is 2 to the 4. If we apply the binary logarithm once again, we get 4. If we apply it again, we get 2. And if we apply it finally once again, we get 1. And at this point, we stop. So we applied the binary logarithm 5 times to get a number which is at most 1, which ensures that for this number 2 to the 6, 5, 5, 3, 6, the log star is equal to 5. Okay? So, and this shows that for any practical value of n, the log star function is at most 5, because this number is extremely huge. We will never see any value of n which is greater than this number in practical value. We will never get an input, a sequence that consists of so many elements, for example. So theoretically speaking, the log star function is not bounded. It is not constant. So there are extremely huge numbers for which log star is equal to 10 or 20 or 30 or 100 and so on. However, for all practical values of n, log star of n is at most 5. We are now ready to state an upper bound. Assume that we use both union by rank heuristic and path compression heuristic. And assume that we make m operations with our data structure, of which n are calls to the make set operation. Namely, we have n objects and we make m operations with them. Then the total running time of all these calls is big O of m multiplied by log star of n. Put it otherwise, the amortized running time of a single operation is big O of log star of n. And recall that for all practical values of n, log star of n is at most 5, which means that we have a constant average time for a single operation for all practical values of n. So once again, log star, theoretically speaking, log star function is not bounded. However, it is at most 5 for all practical values of n, which makes our data structure very efficient in practice. We will prove this upper bound in the next video. Our goal in this video is to show that if we use both path compression and union by rank heuristics, then the average running time of a single operation is upper bounded by big O of log star of n. Before going into the details of the proof, let's realize a few important facts. First of all, note that since we are now using path compression, it is no longer the case that the rank of node I is equal to the height of the tree rooted at vertex I. However, it is still true that the rank is an upper bound on the corresponding height. Let me illustrate this with a toy example. So assume that we have a tree like this. So this is the root, say vertex 5. Here we have vertex 2. Here we have node 3 and node, say, 6. Assume that currently the rank of this node is 2, this is 0, this is 1, and this is also 0. And now we call find of 6. This will reattach 6 to the current root of this tree. So what we get is the following: 5, 1 and also 6 now stays here, right? So we see that the height of these three is equal to 1. However, the rank of the root is still equal to 2. Recall that find doesn't use and doesn't change any rank values. Also, for this node 3, its height, the height of the tree rooted at element 3 is equal to 0. However, the rank is equal to 1. Well, intuitively it is clear. Path compression can only decrease the height. So for this reason, rank is no longer equal to the height of the corresponding tree. However, the height is at most the rank. Okay? Another important thing is the following. It is still true that for any root node I of rank k, the corresponding subtree contains at least 2 to the k elements. And this can be seen by realizing that the path compression does not affect any root nodes. I mean, if we have a root node whose height is k, then no matter how many times and for which nodes in this subtree we call find with path compression, all these nodes are still in this subtree, rooted at this node, exactly because this node is still a root. So any node from this subtree cannot be reattached to some other vertex in some other subtree. This node is still a root. So once again, if we have a node who is still a root and whose rank is k, then the corresponding subtree contains at least 2 to the k elements, 2 to the k nodes. On this slide, we discuss a few more important properties. The first one of them says that we have in our forest at most n divided by 2 to the k nodes of rank k. Why is that? Well, recall that if we create a new node of rank k, then it was created by merging two nodes of rank k minus 1. Okay? So we know that currently this node is a root. At the same time, we note that the corresponding subtree contains at least 2 to the k nodes. If we have another node of rank k, then it also contains at least 2 to the k nodes. Which means that if we have too many such nodes, I mean too many nodes of rank k, by saying too many I mean that its number is greater than n divided by 2 to the k, then overall we have more than n elements, which is a contradiction, right? The second property is that when we go up, the rank strictly increases. Well, this was clear if we do not use path compression. I mean, if rank is equal to the height of the corresponding subtree, then this is completely clear. Let me recall that if we have, for example, a tree of height 2, then the height of this tree is 2, the height of this subtree is 1, the height of this subtree is 0. And let's say this is element 5, this is 4, this is 8. Now we have path compression, so we need to check what happens when we compress some path. If we call find of 5, for example, then 5 will be reattached to the current root. But it will still be true that the rank of the parent, so let me fix this, this is node 8, that the rank of the parent is strictly greater than the rank of a child. The last property says that when a node becomes an internal node, it will be an internal node forever, right? It will not have a chance to become a root. And this is just because the find operation doesn't change any roots in our forest, while union operation takes two roots and makes one of them a child of the other one. So it takes two roots and leaves only one root. Okay? So once again, when a vertex becomes an internal vertex, a non-root vertex, it will be a non-root vertex forever. we now start to estimate the running time of M operations. First of all, note that the union operation boils down to two calls to find operation and also to some constant time operations. Namely, when we have two roots that were found by two calls to the find operation, we need to hang one of them below the other one, which is a constant time operation. We just need to change one parent value. And also, possibly, we need to change the rank value. Okay? So for this reason, when estimating the total running time, we will just assume that we have M calls to find operation. Further note that each find operation traverses some path from a node to the root of the corresponding tree. So we traverse some number of edges. So the total running time of all the find operations, of all the calls to the find operation, is just the total number of edges traversed. So this is what is written here. We just need to count the number of edges from a parent I, from a node I to its parent J, traversed in all these calls. For technical reasons, we will split this number into three terms. In the first term, we will account all the edges that lead from a vertex, from a node, to the root of the corresponding tree. So the first term includes all the edges that lead from a node to another node, which is the root in this case. The second term includes all the remaining edges where we go from I to J, such that the log star of rank of A is strictly smaller than log star of rank of J. Okay? And the remaining term accounts for everything else, namely for all the edges where we go from I to J, such that J is not the root, and that log star of rank of I is equal to log star of rank of J. We're going to show separately for each of these terms that it is upper bounded by big O of M multiplied by log star of M. Let me show this on a small example, as usual. Assume that we have such a path, that we are going to traverse a path from the node at the bottom to the root of the corresponding tree. So the numbers shown here indicate the ranks of the corresponding nodes. Then these two nodes, these two edges, will be accounted in the first term, just because these two nodes lead from a node to the root of these two edges lead from a node to the root of the corresponding tree. Well, this edge, for example, will be accounted in the last term, because the rank of this node is 17 and the rank of this node is 21, and log star of these numbers are equal. At the same time, here we have 14, the rank 14, and here we have rank 17, and the log star of these two numbers are different. For this reason, this edge will be accounted in the second term. Okay, so on the next sequence of slides, we are going to estimate separately each of these three terms. And for each of them, we are going to show that it is at most big O of M multiplied by log star of N. The first term is easy to estimate. Recall that in this term, we account for all the edges traversed by find operation, where we go from node I to its parent J, such that J is the root. Clearly, for each call to find operation, there are at most two such edges, right? Which means that we have an upper bound big O of M. In the second term, we need to estimate the total number of edges traversed during all M calls to the find operations, such that we go from node I to its parent J, such that J is not the root, and also log star of rank of I is strictly less than log star of rank of J. We're going to prove here that it is upper bounded by big O of M multiplied by log star of N. And this is just because when we go up from some node to the root, to the root of the corresponding tree, the rank always increase. However, the rank of the root is at most log n, which means that during one call to find procedure, the log star of rank can only increase log star of n times. Okay? This is just because we have an upper bound for the rank of the root. Okay? It is upper bounded by log n, which means that there are only log star of n different values, different possibilities for log star of rank of all the nodes on this path, which means that it can only increase at most log star of n times. And we have at most m calls to find operations, which gives us an upper bound m multiplied by log star of n. Now it remains to estimate the last term, where we account for all the edges traversed during m calls to the find operations, where we go from node I to node j to its parent j, such that j is not the root, first of all, and then the log star of rank of I is equal to log star of rank of j. What we're going to show is that the total number of such edges is upper bounded by big O of n multiplied by log star of n. Note that this is even better than what we need. What we need is a weaker upper bound, which is m log star of n. Recall that we know that m is greater than n just because m is the total number of operations, while n is the number of calls to make said operations. To estimate the required term, consider a particular node I and assume for concreteness that its rank lies in an interval from k plus 1 to 2 to the k. Recall that this was the form of an interval for which the log star function is the same, is fixed. Okay? Now let's compute the total number of nodes whose rank lies in such an interval. So we know that the total number of nodes whose rank is equal to k plus 1 is at most n divided by 2 to the k plus 1. The total number of nodes whose rank equals to k plus 2 is at most n divided by 2 to k plus 2, and so on. So the total number of nodes whose rank lies in this interval is at most n divided by 2 to the k. Okay? The next observation is that each time when we call find of I, it is adopted by a new parent. And since it is new, so at this point we know that we have a node I and its parent j is not the root. Yes, this is essential. Which means that when we go up, we find another root when we call find of I. And at this point we will reattach node I to this new root. And this new root has strictly larger rank. And this in turn means that after at most 2 to the k calls to find of I, find I will be adopted by a new parent whose rank for sure does not lie in this interval, just because the length of this interval is at most 2 to the k. So if we increase the rank of the parent of I at least 2 to the k times, it will be greater than 2 to the k for sure, right? We now have everything to conclude this proof, to conclude estimating the required term. Recall that we are estimating the total number of edges traversed during m calls to find, where we go from a node I to its parent j, such that log star of rank of A is equal to log star of rank of j. So we've just proved that there are at most n divided by 2 to the k nodes whose rank lies in the interval from k plus 1 to 2 to the k. We then explained why any such node whose rank lies in such an interval contributes at most 2 to the k to the term that we are currently estimating. This means that just all the nodes from whose rank lies in such an interval contributes at most big O of n to this term, right? Now it remains to note that the total number of different intervals is at most log star of n, which means that the total contribution of all such nodes I to the estimated term is at most big O of n multiplied by log star of n. We now conclude the whole lesson. So in this lesson we consider it an implementation of the disjoint set data structure where each set is represented by a tree. And for this reason we have a forest of trees. The ID of each set is just the root of the corresponding tree. We've then considered two heuristics. The first one is called union by rank. It says that when merging two trees, it makes sense to attach a shorter one to the root of a taller one. Okay? This helps to keep trees in our forest shallow. And for this, we keep the rank of each subtree rooted at a particular node in a separate array called rank. We then discussed another heuristic, which is called path compression. The idea is the following. When we traverse a path from a node to the root of the corresponding tree, we may want to reattach all the nodes found on this path directly to the root, because this potentially will save us time for further find operations. Right? We then proved that the resulting implementation turns out to be extremely efficient. Namely, the amortized running time of each operation is big O of log star of n. And log star of n is an extremely slowly growing function. In particular, log star of n is at most 5 for all practical values of n.
Hi! In this module, we will study hashing and hash tables. Hashing is a powerful technique with a wide range of applications. In this video, we will learn about some examples of those applications, just to have a taste of it. The first example that comes to mind is, of course, programming languages. In most of the programming languages, there are built-in data types or data structures in the standard library that are based on hash tables. For example, dict or dictionary in Python or hashmap in Java. Another case is keywords of the language itself. When you need to highlight them in the text editor, or when the compiler needs to separate keywords from other identifiers in the program to compile it, it needs to store all the keywords in a set, and that set is usually implemented using a hash table. Another example is file systems. When you interact with a file system as a user, you see the file name, maybe the path to the file, but to actually store the correspondence between the file name and path and the physical location of that file on the disk, system uses a map, and that map is usually implemented as a hash table. Another example is password verification. When you use some web service and you log into that and you type your password, actually if it is a good service, it won't send your password in clear text through the network to the server to check if that's the correct password or not, because that message could be intercepted and then someone will know your password. Instead, a hash value of your password is computed on your client side and then sent to the server, and then server compares that hash value with the hash value of the stored password, and if those coincide, you get authenticated. Special cryptographic hash functions are used for that. It means that it is very hard to try and find another string which has the same hash value as your password. So you are secure. Nobody can actually construct a different string which has the same hash value as your password and then log in as you in the system, even if he intercepted the message with the hash value of your password going to the server. Another example is storage optimization for online cloud storages such as Dropbox, Google Drive or Yandex.Disk. Those use a huge amount of space to store all the user files, and that can actually be optimized using hashing. We will discuss this example further in the lectures of this module. Hi! In this video, we will introduce a problem about a web service and IP addresses of its clients. We will use this problem to illustrate different approaches throughout the whole lesson. Suppose you have a web service with many clients who access your service through the internet from different computers. In the internet, there is a system which assigns a unique address to each computer in the network, just like every house in the city has its own address. Those addresses of computers are called IP addresses, or just IPs. Every IP address looks like this: 4 integers separated by dots. Every of the 4 integers is from 0 to 255, so that it can be stored in 8 bits of memory. And the whole IP address can be stored in 32 bits of memory, as the standard integer type in C++ or Java. So there are 2 to the power of 32 different IP addresses, which is roughly 4 billion. Recently, the internet became so big that 4 billion is no longer enough for all the computers in the network. That's why people designed the new address system called IPv6, and the number of addresses there is 2 to the power of 128, which is a number with 39 digits, and it will be sufficient for a long time. In this problem, we will start talking about old system called IPv4, which is still in use and which contains only 2 to the power of 32 different IP addresses. When somebody accesses your web service, you know from which IP address did he or she access it, and you store this information in a special file called access log. You want to analyze all that activity, for example, to defend yourself from attacks. An adversary can try to kill your service by sending lots and lots of requests from his computer to your service so that it doesn't survive the load and fails. This is called denial of service attack. And you want to be able to quickly notice the pattern that there is an unusual high number of requests from the same IP address during some period of time, for example, the last hour. And to do that, you want to analyze your access log. You can think of your access log as of a simple text file with many lines, and in each line you have date and time of the access and the IP address from which the client accessed your service. And you want to be able to quickly answer the queries like, did anybody access my service from this particular IP address during the last hour? And how many times did he access my service? And how many different IPs were used to access this service during the last hour? To answer those questions, we will need to do some log processing. But of course, we don't want to process whole 1 hour of logs each time we want to answer such a simple question, because 1 hour of logs can easily contain dozens of thousands or hundreds of thousands or even millions of lines, depending on the load on your web service. We want to do that much faster. So, to do that, we will keep count. For each IP address, we will keep a counter that says how many times exactly that IP address appears in the last 1 hour of the access log, or how many times during the last hour clients accessed your service from that particular IP address. And we'll store it in some data structure C, which is basically some data structure to store the mapping from IP addresses to counters. We don't know yet how to implement that data structure C. We will discuss that further. We will update the counters corresponding to IP addresses every second. For example, if now is 1 hour 45 minutes and 13 seconds from the start of the day, and we will ignore the date field in the access log for the sake of simplicity, then we need to increment the counters corresponding to the IP addresses in the last 2 lines of the log, because those are new lines. We also need to remember to decrement the counters corresponding to the IP addresses in the old lines of the log. For that, we will look at the lines exactly 1 hour ago in the log, because the lines which are older than that, for them we've already decremented the counters on the previous seconds. And the lines which are more recent than that, we still don't need to decrement the counters because the IPs in those lines are still in the 1 hour window ending in the current second. So we will decrement the counters corresponding to the lines which are 1 hour ago from the current moment. Now let's look at the pseudocode. In the main loop we have the following variables. Log represents the access log. We will think of it as an array of log lines. Each log line has 2 fields, time and IP address. C is some mapping from IPs to counters. We still don't know how to implement that, but we suppose that we have some data structure for that. I is an index in the log which points to the first unprocessed log line. So when a new second starts, we will need to start incrementing counters corresponding to lines starting from I and further in the log. J is the first or the oldest line in the current 1 hour window, so that when the next second starts, we will need to decrement counters for some of the lines starting from line number J. We initialize I and j with 0 and c with an empty mapping, because there is nothing to store in the start. And then each second we call procedure update access list, and we pass there the access log to read data from. We also pass I and j, which we will use inside and also update, and we pass data structure c, which is our goal to update it. So now let's look at the pseudocode for update access list. It consists of two parts. First part deals with the new lines, and the second part deals with the old lines. New lines start from line number I, which is the first unprocessed line. We look at this line and we increase the counter corresponding to the IP in this line using our data structure C. And then we go on to the next line. We proceed with this while the time written in the log line I is still less than or equal to the time when update access list was launched. And then we stop processing new lines and we move on to old lines. How to determine that the line is old enough to decrement the counter? We compute the time now, which we assume is computed in seconds. So then we need to subtract exactly 1 hour from that, and that is 3600 seconds. And if the time written in line j is less than or equal to that, we need to decrement the corresponding counter. So we start with line number j, which is the first line in our 1 hour window. We check that it is old enough to decrement the counter. We decrement the counter if that's the case, and then we move on to the next line. And in the end, when we stop in this while loop, j will point again to the first or oldest line in the current 1 hour window. So we've implemented the updating procedure correctly. Now how to answer the question whether this particular IP was or was not used to access our service during the last hour. That is really easy. If the counter corresponding to that IP is more than 0, then this IP was used during the last hour. Otherwise, the counter will be 0. So we've implemented all the procedures necessary to answer the questions, but for one small detail. We don't know how to implement data structure C, and we will discuss that in the next lectures. Hi, in this video we will talk about direct addressing, which is the first step on the way to hashing. Remember this pseudocode from the last video. We implemented procedure update access list using a data structure C, which stores a counter for any IP address. Now the question is how to implement the data structure C itself. The idea here is that there are 2 to the power 32 different IP addresses according to IPv4 format, and we can actually convert each IP to a 32-bit integer, and it will be a one-to-one correspondence between all possible IPs and all numbers between 0 and 2 to the power 32 minus 1. Thus, we can create an array A of size exactly 2 to the power 32 with indices from 0 to 2 to the power 32 minus 1. And then for each IP there will be exactly one position in this array corresponding to this IP. And then we will be able to use the corresponding entry in array A instead of the counter for this IP. Now, how do we actually convert IP addresses to integers? If you look at this picture, you will see that any IP address actually consists of 4 integer numbers, which are all at most 255, and each of them corresponds to 8 bits or 1 byte in the total 4-byte or 32-bit integer number. Basically, if you just concatenate all the 8 bits corresponding to first number with 8 bits corresponding to the second number and to the third number and to the fourth number, you will get 32 bits. And if you then convert this string of 32 bits into the decimal form, you will get an integer number in the form which we are used to. For example, if you take a very simple IP address, 0.0.0.1, it will convert to integer 1, because all the higher bits are zeros, and in the lowest byte, the only bit set is the lowest bit, and that corresponds to number 1. If we convert the number on the picture to the decimal form, we will get 288,679,4753. Now, what do you think will be the integer number corresponding to this IP? And the correct answer is 116.889.3508. Now, here is the formula in the code to convert an IP address to an integer number. Why is that? Well, the lowest 8 bits are in the fourth number of the IP address, so we use them without changing. The next 8 bits are in the third number of IP, but to use them we need to move them to the left by 8 positions in the binary form. And to do that we need to multiply the corresponding integer number by 2 to the power of 8. The next 8 bits are in the second number of the IP. And to use them we need to move them to the left by 16 positions in the binary form. To do that we multiply the corresponding integer number by 2 to the power of 16, and so on. This gives us a one-to-one correspondence between IP address and integer number. Now we can rewrite the code for update access list using array A instead of mysterious data structure C. And the only thing that changes is the incrementing and decrementing the counters. So when we need to increment a counter corresponding to the IP in the ith line, we first convert this IP to integer number from 0 to 2 to the power of 32 minus 1. And then we increase the entry of the integer array A at this index. Note that each IP is converted to its own integer number, so there will be no collisions between different IP numbers when we try to increment a counter for one IP number and by chance increment the counter corresponding to another IP address. All IP addresses are uniquely mapped into integers from 0 to 2 to the power of 32 minus 1. We do the same thing when we need to decrement the counter. So basically, in the position in array A corresponding to any IP address, we will store the counter which measures how many times this particular IP was accessed during the last hour. Now, how to answer the question whether this IP was or was not used during the last hour to access your services? This is very easy. We first convert the IP to the corresponding position in the array A, and then we look at the counter that's position. If the IP was used, then the counter will be more than 0, otherwise it will be exactly 0. So now let's look at the asymptotics of this implementation. Update access list is as fast as we can do. It is constant time per log line, because for each log line we only look at some position in the array and increment it, and also increment some counter, or decrement some counter. Accessed last hour is also constant time, because the only thing we do is we look at some position in the array, which is a constant time operation, and compare it with 0. But there is a drawback. Even if during the last hour, for example in the night, there were only 5 or 10 or 100 IPs from which your clients used your service, you will still need 2 to the power 32 memory cells to store that information. And in general, if you have, for example, new IP protocol, IPv6, it already contains 2 to the power of 128 different IP addresses. And if you create an array of that size, it won't fit in memory in your computer. In the general case, we need big O of big N memory, where big N is the size of our universe. The universe is the set of all objects that we might possibly want to store in our data structure. It doesn't mean that every one of them will be stored in our data structure. But if we at least at some point might want to store it, we have to count it. So for example, if some of the IP addresses never access your service, you will still have to have a cell in your array for this particular IP in the direct addressing method. So this method only works when the universe is somewhat small, and we need to invent something else to work with the universes which are bigger than that or even infinite, such as, for example, the universe of all possible words, all possible strings, or all possible files on your computer. And we will talk in the next videos about that. Hi, in this video we will study another approach to the IP addresses problem. In the last video, we understood that the direct addressing scheme sometimes requires too much memory. And why is that? Because it tries to store something for each possible IP address, while we're only interested in the active IP addresses, those from which at least some user has accessed our service during the last hour. So the first idea for improvement of the memory consumption is let's just store the active IPs and nothing else. Another idea is that if our array-based approach from the last video has failed, then let's try to use list instead of an array. So let's store all the IP addresses which are active in a list, sorted by the time of access, so that the first element in the list corresponds to the oldest access time during the last hour, and the last element in the list corresponds to the latest, newest access from some IP address to our service. Let's jump from here right into the pseudocode because it's pretty simple. We again have our procedure update access list, which takes in the log file log. It also takes in I, which is the index of the first log line which hasn't been processed yet. And also it has input L, which is the list. And instead of some abstract data structure C from the few first videos, and instead of the array A from the direct addressing scheme, we put parameter L, which is a list, into this procedure. And this is the list with the active IP addresses. So our code has two parts. First deals with new lines and second deals with the old lines. We just go starting from the first unprocessed line, and if we need to add it to our list because it was processed during the last hour, we just append it to the end of the list. And now again, the last element of the list corresponds to the latest, newest access from some IP address. And note that in our list, we will store not just the IP address, but both IP address and the time of the access. And then we will go to the next element in the log file and go while we still have some log lines which we need to add to the end of our list. And in the second part, we just look at the oldest event during the last hour, which is corresponding to the first element of the list. And if that is actually before the start of the last hour, then we need to remove it from the list. And so we just do lpop. And we do that while the head of the list is still too old. And when we stop, it means that all the elements in the list are actually with time during the last hour. Why is that? Because the list is always kept in the order by increasing time of access. When we add new log lines to the list, we add only those which have time even more than the last element of the list currently. And when we remove something from the list, we remove the oldest entries. So all the entries are always sorted, and as soon as we removed everything from the start which is too old, all the entries in the list are not too old. They are made during the last hour. So this is pretty simple, and now we need to answer questions like whether my IP address was used during the last hour to access the service and how many times. To answer the first one, we just need to find out whether there is an element in our list with the given IP address. And that is done by procedure find by IP, which is different from the standard find procedure of the list by the fact that we search not by the whole object, which is a log line which contains both IP address and time, but we search just by the first field, by the IP address. So our list contains tuples of IP addresses and times of access, and we only look by IP address. But the implementation will be the same. We'll just go from the head of the list to the end of the list and compare the IP field of the log lines with the IP address given as the input. And if it coincides, we return this element. Otherwise, we return that there is nothing with this IP address in the list, and we return some special null value. So then in the access last hour, just compare the result with null. If it's not null, then this IP address is in the list, otherwise it's not. And to count the number of times our service was accessed from a particular IP address, just need to count the number of log lines in the list which have the same IP address. And that can be done by procedure count IP of the list, which again differs from the standard count procedure in the list by the fact that it counts by the first field, not by the whole object, which is a log line, but it just goes from head to the end of the list, compares the IP field with the given IP, and if they coincide, it increases the counter by 1 and returns the counter in the end. So this is all the implementation. Now let's analyze it. Let n be the number of currently active IPs. Then the memory consumption is big O of n, because we only store the active IP addresses and the corresponding times of access, but the times of access only add constant memory per active IP, so it's all in all linear in the number of active IPs, which is much better than the direct addressing scheme, because it required amount of memory proportional to the number of all possible IP addresses. And here we only require amount of memory proportional to the number of currently active IP addresses. What about running time? We know that the standard lists procedures such as append, stop, and pop all work in constant time, and that's why the update access list works in constant time per log line. Of course, any particular call to update access list could take more than a constant number of operations if we need to add more new lines to the end of the list or remove many old lines from the start of the list. But for each log line, we will only append it at most once, and we will only remove it from the beginning at most once. So it's constant time per log line plus constant time per each call of update access list, just to check whether we need to append something and whether we need to remove something from the beginning. But this amount of operations can be controlled by how often do we actually call update access list. What about answering the questions? We know that find by IP and count IP have to go through the whole list in the worst case, and actually count IP has to go through the whole list all the time to find out how many log lines have the same IP as the given one. And so access last hour and access count last hour are both linear in the number of active IPs. And that is actually no good, because even without introducing any additional data structures, we could just take the log file, take the last line in it before the current time and go back from it and just look through each log line and compare its IP address with the IP address in the question and count how many times it occurs during the last hour, and just stop as soon as we go through the border of the last hour. And that will take the same time without any additional data structures. So this solution is not more clever than the trivial approach. So we failed somewhat with direct addressing scheme, and we failed with this list-based approach. Is it overall a failure? Well, no. In the next videos we'll combine the ideas from direct addressing scheme with the list-based approach, and we'll come up with a solution which is both good in terms of memory consumption and is much faster than the trivial approach in terms of the running time. Hi! In this video you will learn what a hash function is, how could we apply it to solve our problem with IP addresses, and why it is not straightforward to make it all work. Remember that direct addressing approach worked particularly fast, but it used a lot of memory. That's because it encoded IP with numbers, and those numbers were sometimes huge, so we had to create an array of size 2 to the power 32 just to store all those numbers. What if we could encode our IP addresses with smaller numbers, for example numbers from 0 to 999? We will still need the codes for different IP addresses which are active currently to be different, because we want a separate counter for each IP in our solution. Let's define a hash function. So if we have some universe of objects S, for example set of all IP addresses, or set of all files on your computer, or set of all words or keywords in a programming language, so that is our universe, and we call it a set S. And now we want to encode each object from that universe with a small number from 0 to m-1, where m is a positive integer number. Well, any function which encodes some object from S as a number from 0 to m-1 is called a hash function. And m is called the cardinality of hash function h. So what are the desirable properties of the hash function in our problem? First, h should be fast to compute, because we need to encode some object for each query. Second, we want different values for different objects, because we want a separate counter for each IP address in our problem, for example. and also we want to use direct addressing scheme because it was very fast. But we want to use a direct addressing scheme with a small amount of memory, and it is only logical to use in this case direct addressing scheme with big O of m memories. Just create an array A of size m and then encode each IP with some value from 0 to m-1 and store the corresponding counter in the cell of this array. The problem is that we want small cardinality m, and it won't work if m is smaller than the number of different objects in the universe. Because if we have, for example, 25 objects in the universe and m is only 10, then at least 2 objects will have the same code from 0 to 9, because there are only 10 different codes and there are 25 different objects. So that won't work for all possible universes and for small m. In this situation, when the values of the hash function are the same but the objects which are being encoded are different, is called a collision. So collisions cause us problems. Because of collisions we cannot just directly apply the scheme called direct addressing with big O of m memory. And in the next lecture we will see how to overcome this problem. In this video we will study chaining, which is one of the most frequently used techniques for using hashing to store mappings from one type of objects to another type of objects. So let us define a map. We often want to store mapping from some objects to some other objects, for example, a mapping from IP addresses to integer numbers, or from file names to the physical location of those files on the disk, from student ID to the name of the student, or from contact name in your phone book to the contact phone number. The general definition of a map from set of objects S to the set of values V is a data structure which has 3 methods. HasKey, which tells us whether there is an entry in the map corresponding to object O from set S. Method Get, which returns to us the value corresponding to the object O if there is one. If there is no such value, it returns a special value telling us that there is no entry corresponding to this object O in the map. And the last method is set, the most important method, which sets the value corresponding to object O to V. Here objects O are all from the set S and values V are from the set big V. We want to implement a map using hash function and some combination of ideas from direct addressing and list-based solution from one of the previous videos. So what we'll do is called chaining. We will create an array of size m, where m is the cardinality of the hash function, and in this case let m be 8. This won't be an array of integers though, this will be an array of lists. So in each cell of this array we will store a list, and this will be a list of pairs, and each pair will consist of an object O and a value V corresponding to this object. Let's look at an example. For example, our objects are IP addresses and values are the corresponding counters, as in our initial problem about web service and IP addresses of its clients. Now we're processing the log and we see an IP address starting with 173, and it so happens that the value of hash function on this IP address is 4. Then we look at the cell 4, the list there is now empty, but we append the pair of our IP address and the corresponding counter 1 to this list. The value is 1 because this is the first time that we encountered this IP. Now we look at the next IP in the log. It starts with 69 and the hash value for this IP is 1. So we look at the cell number 1 and we append the pair of this IP address and the corresponding counter 1 to the list. Again, the counter is 1 because this is the first time we see this IP address. Now we look at the next IP address in the log and we see that it again starts with 173 and actually it coincides with the first IP that we've already seen. And the hash value is again 4, because hash function is deterministic. It always returns the same number for same object. So we look at the cell number 4, we look through the whole list, and we find out that there is already a pair containing this IP address as the key. So instead of appending this IP address again to the list, we will increase the value of the counter by 1, because this is the second time we've seen our IP address. Of course, in the interface of a general map, there is no method for incrementing a counter. There is a method set. So we will need to first use method get to get the value corresponding to this IP address. We will get 1. We will then increase it by 1 ourselves, get 2, and then we will call set for this IP address and value 2. And it will just rewrite the value from 1 to 2 in this list element. Then we look at the next line in our log, and we see that this is an IP starting from 91, and it so happens that the hash value for this IP address again is 4, although this is a different IP address. And that has to happen at some point, because there are many different IP addresses and only 8 entries in our array. So what do? We look at the cell number 4. There is a non-empty list there. We go through the whole list, but we see that our new IP address starting from 91 is not in the list. So we add our new IP address to the end of this list, along with the corresponding counter of 1. And these two IP addresses in the list for cell number 4 already make a chain together. And if we go further and further through the log and we add some IP addresses to this map, some of the chains will become longer. If we at some point will need to remove some IP address from the list, we can do that and the chain can become shorter. But anyway, you see the general structure, that a chain may be empty, maybe non-empty, starts in any cell of the array. The array size is m, which is equal to the cardinality of the hash function, and for each such cell we store a list with all the IP addresses which occurred before and which have hash value the same as the number of this cell. How to implement this in code? Let us assume that we have a hash function h from the set of all possible objects s to the set of numbers from 0 to m-1, and let us denote by O and O prime objects from set S, and by V and V prime values from set big V. And let us have an array A, which consists of m lists, where m is the cardinality of the hash function, and those lists we'll call also chains, and those chains consist of pairs of objects O and values V. Now let us implement the first method, hasKey, which should return whether there is an entry in our table or in our map for the object O. First, we compute the value of hash function on the object O. We look at the corresponding cell in the array A and we take the list L from there. Then we go through this list, and when we go through it, we look at pairs O prime, V prime that are elements of this list. If for some pair O prime is the same as the object O for which we are looking, we return true, because it means that there is an entry in our map corresponding to the object O. If we don't find any corresponding pair in the list, we return false, because that means there is no such object and there is no key corresponding to this object in our map, because it only could be in the list corresponding to the cell with number h of O, and we didn't find it there. Next, let's implement method get, which should return the value corresponding to object O, if there is one, otherwise return some special value telling us that there is no entry corresponding to object O. Again, we start with computing value of hash function on object O, and looking at the cell number h of O in the array A, and take the list which is stored in that cell. Then we again go through all the pairs in that list L, pairs O prime, V prime, and if for some of the pairs O prime is the same as the object O for which we are looking, then we return the corresponding value v prime as the value corresponding to that object O. If we go through the whole list and we don't find corresponding pair, we return special value NA, which means that there is no value corresponding to object O in our map. Why is that? Because if there was some value, it has to be in the list corresponding to the cell number H of O, because that's the way we store our chains. And if we didn't find it there, then there is no entry corresponding to the object O. Now the last, most interesting method, set, which accepts two arguments, object O and the value v, which we need to set corresponding to this object. We need to either rewrite this value if there was already an entry corresponding to the object O with different value, or we need to create a new value in the map corresponding to the object O if it didn't happen to be in the map before. We again start with computing the hash function on the object O and looking at the corresponding cell in the array A, and we take the list which is stored there. Now we go through all the pairs P in that list L, and each pair P contains two fields. First field is P.O, which is the object of that pair, and P.V, which is the value of that pair. If for some pair we see that the object of that pair is the same as object O, for which we need to set the value v, then we just assign the value to the P.V, the new value. We rewrite the old value with the new value for that object O. And then we return, we exit from the function, because we've already done everything we need. If we go through the whole list and we don't find any pair corresponding to our object O, it means that there was no entry in our map corresponding to the object O previously, and it means that we need to add a new pair to our list. And we just append a new pair containing object O and value v to the list L corresponding to the cell number H of O. Now let's look at the asymptotics of the chaining scheme. The first lemma says that if C is the length of the longest chain in A, then the running time of all three methods is theta of C+1. First, if we look at the list corresponding to some object O, the list in the cell number H of O, then the length of this list can be C. This can be the longest list itself. And if object O is not in this list and we call some of the methods for this object, we will need to scan the full list. So we'll need to scan all C items in this list. Also, if C is 0, so that our map is empty, our array A is comprised of M empty lists, we still need constant time to check that. So that's why C+1 and not just C. Another lemma is talking about memory consumption. So let n be the number of different keys that we store in the map, and m is the cardinality of the hash function. Then the memory consumption is theta of n plus m. That is very easy to prove. First, we need to store n pairs of objects and corresponding values in the map. That's where we get theta of n. And we get additional theta of m to store the array of m lists. Although those lists can be empty, we'll still need to use some memory to store the pointers to the heads of those lists. And that's why memory consumption is theta of n plus m. Hi! In this video, we will finally start talking about hash tables. We will define what a hash table is and what we can do with it. In the last video, we've introduced the notion of map, and now we will introduce a very similar and natural notion of a set. By definition, a set is a data structure which has at least three methods: to add an object to the set, to remove an object from the set, and to find out whether a given object is already in the set or not. One of the examples we already know very well: set of all IPs through which clients accessed your service during the last hour. This is an example with which we've worked for the last few videos. Another example would be to store the set of all students currently on campus. And another one is to store all the keywords of a given programming language so that we can quickly highlight them in the text editor which you use to code. There are two ways to implement a set. One of them is when you already have an implementation of a map, you can base your implementation of set on the map. Basically, you can set a map from all the objects S that you need to store in a set to the set of values V which only contains two values, true and false. If the object is in the set, then the corresponding value to this object will be true. If the object is not in the set, it is either not in the map or the corresponding value to it in the map is false. But that is not a very efficient way, because we will have to store twice as much objects and values as we need. And also, when we remove objects from the set, it will be hard to remove them from the map. We will probably have to store them with value false. So there is a better way. We can again use chaining, but instead of storing pairs of objects and corresponding values in the chains, we will just store objects themselves. Let's see how can we implement that in pseudocode. Again, we have a hash function from all the objects S to the set of integer numbers from 0 to m-1. We denote by O and O prime objects from the set S, and we initialize array A with an array of size m, which consists of lists or chains, and each chain consists of objects O. Initially, all the chains are empty. When we need to find an object in such a set, we first compute the hash value of our object. We look at the corresponding cell in the array A, we take the list of objects from there, and then we go through the whole list and try to find object O there. If we find it, we return true, otherwise we return false, because our object O can be only in the list corresponding to the cell in the array A, number h of O. To implement add, we again compute value of hash function on object O. We take the list corresponding to this cell, and we go through this list. If we find our object O in this list, then we don't need to do anything because our object O is already in the set. Otherwise, we append our object to the list corresponding to cell number h of O. To remove object from the set, we first try to find it in the set. If it's not in the set initially, we don't need to do anything. Otherwise, we again compute the hash value of our object, take the corresponding list, and erase our object from that list. So, now we are ready to say what is a hash table. A hash table is any implementation of a set or a map which is using hashing, hash functions. It can even not use chaining. There are different ways to use hash functions to store a set or a map in memory. But chaining is one of the most frequently used methods to implement a hash table. We have a few examples of hash tables already implemented in built-in or standard library types in programming languages. For example, set is implemented as unordered set in C++, as hash set in Java, as set in Python, and map is implemented as unordered map in C++, as hash map in Java, and as dict or dictionary in Python. Why those types are called unordered in C++, we will learn in one of the next modules about data structures. For now, you just know that hash tables are already implemented in the main languages we use for this specialization. In conclusion, we've learned what is chaining, we've learned what is a hash table, and now we know that chaining is a technique that can be used to implement a hash table. We know that the memory consumption for the chaining technique is big O of n plus m, where n is the number of objects currently stored in the hash table, and m is the cardinality of the hash function. We also know that the operations with such a hash table implemented using chaining work in time c+1, where c is the length of the longest chain. Now the question is how to make both m and c small. Why do we need that? Because we want both small memory consumption and fast operations. For example, if m is very big, then we can use direct addressing or something like that, but for some universes, some sets of objects, we will use too much memory, or we will have just too much overhead on top of our O of n memory, which is needed to store n objects anyway. If m is small but c is big, well, that won't differ much from the list-based approach, where we used only O of n memory to store the list, to store only the active IPs, but then we have to spend O of n time to actually look through all that list every time we want to make a query. So we want both m be relatively small and c. How can we do that? Well, we can do that based on a clever selection of a hash function, and we will discuss this topic in the next lessons. Hi! In the previous lesson, you've learned what is a hash function, what is a hash table, and how to use those to implement data structures for storing sets of objects and mappings from one type of objects to another one. However, the speed of this data structure depends a lot on the choice of a hash function, and in this lesson we will learn how to choose a good hash function. We will learn how to implement an efficient contacts book, and you will also learn how is hashing of string objects in Java implemented. We will start with the phone book problem. When you use your phone, you want to be able to quickly look up a phone number of a person by name to be able to call him, and to determine who is calling you and to see not their phone number but their name if it's in your contact book. So you need a data structure that is able to efficiently add and delete contacts from your phone book, to look up phone number by name, and to do the reverse, look up the name given the phone number. To do that, we will need two mappings, one from phone numbers to names and another one back from names to phone numbers. We will implement both those maps as hash tables. And we will start from the mapping from phone numbers to names. One approach that we know from the previous lesson is direct addressing. First, we will need to convert phone numbers to integers, and that is very easy to do. We will implement a simple function called int, as an integer, that just deletes all characters of the phone number other than digits, and then you are left with some integer number, like in this example. Then we'll create an array called name, which will contain 10 to the power of L cells, where L is the maximum allowed length of the phone number. That way, it will be able to store a cell for each integer number from 0 to 999999, and that 9 is going L times, where L is the maximum length of a phone number. So it will be basically enough to store each phone number of allowed length. And in this array, we will store the names corresponding to the phone numbers. So to store a name corresponding to some phone number P, we will first convert P to an integer and then store the name in the cell with this number. And if there is no contact with some particular phone number P, we will just store a default value NA in the corresponding cell. This is how it will look like. On the right is our array name, and on the left we have two contacts. Natalie with number 1234567, which is converted to 1,234,567 and is stored in the cell with this number in the array. It is somewhere in the middle of the array. There are a lot of cells before that. A few cells next to it are probably filled with default value NA, because of course you have much less phone numbers in your phone book than 10 to the power of 7, which is 10 million. And then there is another contact of Steve, which is stored at position 2232323. And of course, there are more NAs in this array. So as we know, operations in the direct addressing scheme work in constant time. However, the memory consumption is exponential in this case. It is big O of 10 to the power of L, where L is the maximum allowed phone number length. And that is problematic, because with international phone numbers, which can contain 12 digits or more for European countries, for example, we will need 1 terabyte just to store one phone book of one person. No smartphone is able to store a phone book of size 1 terabyte. And in the next video, we will suggest a scheme that avoids this problem with memory consumption. Another scheme that we know from the previous lesson is chaining. To use that, we first select a hash function with some cardinality m, then we create an array name, again, of size m, but instead of storing the names themselves in the array, we store chains or lists. And in these lists, we will store both names and the phone numbers. And to determine where to put name and phone number, we first convert the phone number to integer, then we apply a hash function to it, and get a hash value and put both name and phone number in the chain corresponding to the cell with such index. Here is how it looks like. For example, we have a contact of Steve and his phone number is 2232323. We first convert it to the number 2,000,000 and a few thousand, and then we compute the hash value of this integer number, and it turns out to be 1. Then we put both Steve's name and his phone number in the chain corresponding to the cell number 1 in our array name. Then we do the same for Natalie and her phone number, and it turns out that the hash value of the integer corresponding to her phone number is 6, so we put her contact in the 6th cell. And then we do the same for Sasha, and the hash value of his phone number turns out again to be 1. So Sasha gets in the same cell as Steve. There are the following parameters of the chaining scheme. First, n is the total number of phone numbers stored in our phone book. M is the cardinality of the selected hash function, which is the same as the size of our array name, which works as a hash table. C is the length of the longest chain in our hash table. We use big O of n plus m memory to store the phone book. And also alpha, which is n divided by m, the number of phone numbers stored, divided by the size of the hash table, which measures how filled up is our hash table, is called load factor, and we will need it later. So we know that the operations with the hash table run in time big O of c plus 1, and so we want both small m to use fewer memory and small c so that everything works fast. And here's a good example. We see a hash table of size 8 with a few chains, and we see that the length of the chains are relatively the same, with the longest chain being of length just 2. So everything will work fast. And here is a bad example, when we again have hash table of size 8, but all the keys fell in the same cell 1, and they make up a very long chain of size n. In this case, it is 8. So this is what we want to avoid. Let's try a few hash functions that come to our mind. First, let's select cardinality of 1000 and choose the first 3 digits as the hash value for the phone number. For example, for this phone number, it will be 800 because the first 3 digits are 800. However, there is a problem with this hash function because the area code, which is the first 3 digits, will be the same for many people in your phone book, probably because they live in the same city with you, and so they will have the same area code. And the hash values for their phone numbers will be the same, and they will make up a very long chain. Another idea is to take the last digits. Again, the cardinality is 1000, and we take the last 3 digits as the hash value. So for this number, it will be 567. But still, there can be a problem if there are many phone numbers in your phone book which, for example, end in 3 zeros, or in some other combinations of 3 digits. So another approach is to just select a random value as the hash function, a random number between 0 and 999. And then the distribution of hash values will be very good. Probably the longest chain will be short. However, we cannot use such hash function actually, because when we will call the hash function again to look up the phone number we stored in the phone book, we won't find it because we're looking in the wrong place, because the value of the hash function changed because it's not deterministic. So we learned that the hash function must be deterministic, that is, return the same value if given the same phone number as the input each time. So good hash functions are deterministic, fast to compute because we do that every time we need to store something or modify something or find something in our hash table, and they should distribute the keys well in different cells and have few collisions. Unfortunately, there is no universal hash function. More specifically, the lemma says that if the number of all possible keys, the size of the universe with keys, is large enough, much larger than the cardinality of the hash function that we want to use to save memory, then for any specific deterministic hash function, there is a bad input, which results in many collisions. Why is that? Well, let's look at the universe U and select some cardinality, for example, 3, then our universe will be divided into 3 groups. All the keys that have hash value 0, all the keys that have hash value 1, and all the keys that have hash value of 2. Now let's select the biggest of those groups. In this case, it's the group with hash value of 1. This group will definitely be of size at least 1/3 of the whole universe. And it can be even bigger. In this case, it's, for example, around 42%. And then if we take all these keys, or a significant part of these keys as an input, they will have the same hash value. And so all of them will make collisions between themselves, and they will form a very long chain in a hash table, and everything will work very slowly. Of course, if we change the hash function for this particular input, it will distribute the keys more uniformly among hash values. But for this particular hash function, this will be a bad input. And for any specific hash function with any cardinality, we'll be able to select a bad input this way. And in the next video, you will learn how to solve this problem. Hi! In the previous video, you learned that for any deterministic hash function, there is a bad input on which it will have a lot of collisions. And in this video, you will learn to solve that problem. And the idea starts from, remember when you studied quicksort algorithm. At first, you learned that it can work as slow as n² time. But then, you learned that adding a random pivot to the partition procedure helps, because now you know that quicksort works on average in n log n time, and in practice it works usually faster than the other sorting algorithms. So we want to use the same randomization idea here for hash functions. But we already know that we cannot just use a random hash function, because it must be deterministic. So instead, we will first create a whole set of hash functions, called a family of hash functions, and we will choose a random function from this family to use in our algorithm. Not all families of hash functions are good, however, and so we will need a concept of universal family of hash functions. So let U be the universe, the set of all possible keys that we want to hash, and then a set of hash functions denoted by calligraphic letter H, set of functions from U to numbers between 0 and m-1, so hash functions with the same cardinality. Such set is called a universal family if for any 2 keys in the universe, the probability of collision is small. So what does that mean? Our hash function is a deterministic function. So for any 2 keys, it either has a collision for those 2 keys or not. So what does it mean that the probability of collision for 2 different keys is small? It means that if we look at our family calligraphic H, then at most 1/m part of all hash functions in this family, at most 1/m of them have a collision for these 2 different keys. And if we select a random hash function from the family with probability at least 1 minus 1/m, which is very close to 1, there will be no collision for this hash function and these 2 keys. And of course it is essential that the keys are different, because if keys are equal, then any deterministic hash function will have the same value on these 2 keys. So this collision property with small probability is only for 2 different keys in the universe. But for any 2 different keys in the universe, this property should be satisfied. It might seem that it is impossible, but later we will learn how to build a universal family of hash functions in practice. So how our randomization idea works in practice? One approach would be to just make one hash function which returns a random value between 0 and m-1, each value with the same probability. Then the probability of collision for any 2 keys is exactly 1/m. But that is not a universal family. Actually, we cannot use this family at all, because the hash function is not deterministic, and we can only use deterministic hash functions. So instead, we need to have some set of hash functions such that all the hash functions in the set are deterministic. And then we will select a random function h from this set of hash functions. And we will use the same fixed function h throughout the whole algorithm, so that we can correctly find all the objects that we store in the hash table, for example. So there is a lemma about running time of operations with hash table if we use universal family. If hash function h is chosen at random from a universal family, then on average the length of the longest chain in our hash table will be bounded by big O of 1 plus alpha, where alpha is the load factor. Load factor is the ratio of number of keys that we store in our hash table to the size of the hash table allocated, which is the same as the cardinality of the hash functions in the universal family that we use. So it makes sense. If the load factor is small, it means that we only store a few keys in a large hash table, and so longest chain will be short. But as our table gets filled up, the chains grow. This lemma says, however, that if we choose a random function from a universal family, they won't grow too much. On average, the longest chain will still be of length just 1 plus alpha. And probably that is just a small number, because alpha is usually below 1. You don't want to store more keys in the hash table than the size of the hash table allocated. So alpha will be below 1 most of the time, and then 1 plus alpha is just 2. So this is a constant, actually. So the corollary is that if h is chosen at random from the universal family, then operations with hash table will run on average in a constant time. Now, the question is how to choose the size of your hash table. Of course, you control the amount of memory used with m, which is your cardinality of the hash functions, and which is equal to the size of the hash table. But you also control the speed of the operations. So ideally, in practice, you want your load factor alpha to be between 1/2 and 1. You want it to be below 1 because otherwise you store too much keys in the same hash table and then everything could become slow. But also you don't want alpha to be too small, because that way you will waste a lot of memory. And if alpha is at least 1/2, then you basically use linear memory to store your m keys, and the memory overhead is small. And operations still run in time big O of 1 plus alpha, which is a constant time on average if alpha is between 0.5 and 1. The question is what to do if you don't know in advance how many keys you want to store in your hash table. Of course, there is a solution to start with a very big hash table so that definitely all the keys will fit, but this way you will waste a lot of memory. So what we can do is copy the idea you learned in the lesson about dynamic arrays. You start with a small hash table and then you grow it organically as you put in more and more keys. Basically, you resize the hash table and make it twice bigger as soon as alpha becomes too large. And then you need to do what is called a rehash. You need to copy all the keys from the current hash table to the new, bigger hash table. And of course, you will need a new hash function with twice the cardinality to do that. So here is the code, which tries to keep load factor below 0.9. And 0.9 is just a number I selected. You could put 1 here or 0.8, that doesn't really matter. So first we compute the current load factor, which is the ratio of the number of keys stored in the table to the size of the hash table. And if that load factor just became bigger than 0.9, we create a new hash table of twice the size of our current hash table. We also choose a new random hash function from the universal family with twice the cardinality, corresponding to the new hash table size. And then we take each object from our current hash table and we insert it in the new hash table using the new hash function. So we basically copy all the keys to the new hash table. And then we substitute our current hash table with the bigger one and our current hash function with the hash function corresponding to the new hash table. That way, the load factor decreases roughly twice, because we probably just added one new element. The load factor became just a little more than 0.9, and then we increased the size of the hash table twice while the number of keys stayed the same. So the load factor became roughly 0.45, which is below 0.9, which is what we wanted. So to achieve that, you need to call this procedure rehash after each operation which inserts something in your hash table. And it could work slowly when this happens, because the rehash procedure needs to copy all the keys from your current hash table to the new big hash table, and that works in linear time. But similarly to dynamic arrays, the amortized running time will still be constant on average, because the rehash will happen only rarely. So you reach a certain level of load factor and you increase the size of your table twice. And then it will take twice longer to again reach too high value of load factor. And then you will again increase your hash table twice. So the more keys you put in, the longer it takes until the next rehash. So the rehashes will be really rare, and that's why it won't influence your running time of the operations significantly. Hi, in the previous video you've learned the concept of universal family of hash functions, and you learned how to use it to make the operations with your hash table really fast. However, now we need to actually build a universal family. And you will start with the universal family for the most important object, which is integer number. Because any object on your computer is represented as a series of bits or bytes, and so you can think of it as a sequence of integer numbers. And so first we need to learn to hash integers efficiently. So we will build a universal family for hashing integers. But we'll look at our example with phone numbers, because we need to store contacts in our phone book. So first we will consider only phone numbers up to length 7, and for example we'll consider phone number 1482567. And again we'll convert all those phone numbers we want to store to integers from 0 to the number consisting of 7 nines. And for example, our selected phone number will convert to 1,482,567. And then we will hash those integers to which we converted our phone numbers. So to hash them, we will need to also choose a big prime number, bigger than 10 to the power of 7. For example, 10,019,000 is a suitable prime number. And we will also need to choose the hash table size, which is the same as the cardinality of the hash function that we need. So now that we selected P and M, we're ready to define universal family for integers between 0 and 10 to the power of 7 minus 1. So the lemma says that the following family of hash functions is a universal family. What is this family? It is indexed by P. P is the prime number 10,019,000 in this case that we choose, and it also has parameters a and b. So those parameters are different for different hash functions in this family. Basically, if you fix a and b, you fix a hash function from this hash functions family, calligraphic H with index p. And x is the key. It is the integer number that we want to hash, and it is required that x is less than p. It is from 0 to p minus 1 or less than p minus 1, but definitely it is less than p. So, to create a value of this integer x with some hash function, we first make a linear transform of this x. We multiply it by a corresponding to this hash function and add b corresponding to this hash function. Then we take the result modulo our big prime number p. And after that we again take the result modulo the size of our hash table, or the cardinality of the hash functions that we need. So all these hash functions indexed by a and b will have the same cardinality m. And the size of this hash family, what do you think it is? Well, it is equal to p multiplied by p minus 1. Why is that? Because there are p minus 1 variants for a, and independently from that there are p variants for b. So the total number of pairs a and b is p multiplied by p minus 1. That is the size of our universal family. And the lemma states that it really will be a universal family for integers between 0 and p minus 1. We will prove this lemma in a separate optional video, and here we will look at an example of how this universal family works. So, for example, we selected hash function corresponding to a 34 and b equal to 2. So this hash function h is h indexed by p, 34 and 2. And we will compute the value of this hash function on number 1,482,567, because this integer number corresponds to the phone number we're interested in, which is 1482567. We remember that p that we chose is a prime number 10,019,000. So first, we multiply our number x by 34 and add 2. And after that, we take the result modulo p, modulo 10,019,000. And the result is 407,185. Then we take this result and take it again modulo 1000. And the result is 185. And so the value of our selected hash function on number x is 185. And for any other number x, we would do the same. We will multiply x by 34, add 2, take the result modulo p, then take the result modulo 1000. And so any value of our hash function is a number between 0 and 999, as we wanted. And if we took different a and b, instead of 34 and 2, we would just multiply x by different a, add different b, take it modulo p, take the result modulo m, and get the value of our hash function. So in the general case, when the phone numbers can be longer than 7, we first define the maximum allowed length L of a phone number, and we again convert all the phone numbers to integers, which vary from 0 to 10 to the power of L minus 1, and then we'll hash those integers. To hash those integers, we will choose a sufficiently large number p. P must be more than 10 to the power of L for the family to be universal, because otherwise, if we take some p less than 10 to the power of L, there will exist two different integer numbers between 0 and 10 to the power of L minus 1, which differ by exactly p. And then, when we compute the value of some hash function on both those numbers, and we take linear transformation of those keys modulo p, the value of those transformations will be the same. And then, when we take again modulo m, the value again will be the same. And that means that for any hash function from our family, the value of its function on these two keys will be the same. So there will be a collision for any hash function from the family. But that contradicts the definition of universal family, because for a universal family and for two fixed different keys, no more than 1 over m part of all hash functions can have collision for these two keys. And in our case, all hash functions have a collision for these two keys. So this is definitely not a universal family. So we must take p more than 10 to the power of L. And in fact, that is sufficient. Then we choose hash table of size m, and then we use our universal family calligraphic h with index p. We choose a random hash function from this universal family, and to choose a random hash function from this family, we need to actually choose two numbers, a and b. And a should be a random number between 1 and p minus 1, and b should be an independent random number from 0 to p minus 1. If we selected those two numbers, we defined our hash function completely. So now we know how to solve the problem of phone book in the direction from phone numbers to names. So we first define the longest allowed length of the phone number. We convert all the phone numbers to integers from 0 to the 10 to the power of L minus 1. We choose a big prime number bigger than 10 to the power of L. We choose the size of the hash table that we want based on the techniques you learned in the previous video. And then you add the contacts to your phone book as a hash table of size m, hashing them by a hash function randomly selected from the universal family calligraphic h with index p. And that is the solution in the direction from phone numbers to names. This solution will take big O of M memory, and you can control for M, and it will work on average in constant time if you select M wisely using the techniques from the previous video. And now we also need to solve our phone book problem in the different direction, from names to phone numbers, and that we will do in the next video. Hi! In this video, you will learn how to prove the upper bound on the expected chain length in a hash table using chaining and a hash function from a universal hash family. This proof is needed to be confident that our hash tables will work fast in practice. The proof will use some advanced math, which we won't cover, but this video is optional. We will use probabilities, mathematical expectation, and the linearity of expectations. First, let us recall what is a universal family. So if U is the universe, the set of all possible keys that we want to store, and calligraphic H is a set of functions from this universe to the set of numbers from 0 to m-1, where m is the selected cardinality of the hash function, then this set calligraphic H is called a universal family if for any two different keys from the universe, the probability of collision for a random hash function on these two keys is at most 1 over m. What do we mean by probability? It is taken over the random choice of a hash function from the set calligraphic H. Or in other words, the reformulation of this definition is that for any two different keys x and y from the universe, at most 1 over m part of all hash functions in calligraphic H produce a collision on these two keys. Let's also recall what is a load factor. If you have a hash table of size m storing n keys, then n over m is denoted by alpha and called load factor. That measures how filled up is your table. If you store just one key in a hash table of size 10, then load factor is 0.1. And if you store 9 keys in a hash table of size 10, then the load factor is 0.9. We also use the property called linearity of expectation. It says that for any finite set of random variables x1 through xk, the random variable y, which is equal to sum of these random variables, has expectation which is equal to the sum of expectations of these random variables. We won't prove it, we will use it as a fact from probability theory. Now the main theorem is that if you select at random a hash function from a universal family, calligraphic H, and it is used to hash n keys into a hash table T of size m, given load factor alpha, then for any key k, the expected length of the chain in table T, which contains key k, if it is stored in it, is at most 1 plus alpha. What it means is that on average, the length of the chain containing any key will be just 1 plus alpha, which is not too long. Of course, in the worst case, the chain containing some key can be very, very long, such as n keys, and all of them are in the same chain. But on average, if we select a random hash function from a universal family, the chain length will be at most 1 plus alpha, where alpha is the load factor. So to prove that, we fix some arbitrary key k and consider all other keys L, and define a random variable xkl, which takes value of 1 if the hash value of k is equal to hash value of L, if there is a collision between keys k and L, and it takes value 0 otherwise. Let's estimate the expectation of this random variable. It just takes two different values, so we need first to multiply first value 0 by the probability of 0, but we will anyway get 0. And we need to add to that 1 multiplied by the probability of 1, which is the same as the probability of collision, and we know that for a universal family, that probability is at most 1 over m. So expectation of xkl for k and any L different from k is at most 1 over m. Now let's estimate the number of collisions, and we denote by yk the number of collisions that k has with different keys L in the table. And to do that, we can just sum variables xkl for all L which are different from k and are in the table T. Why is that? Because when a collision happens for some key L different from k, variable xkl takes value 1, otherwise it takes value 0. So the sum of all these variables is just the number of collisions with key k. Then the length of the chain containing key k potentially in the table T is 1, because this key itself could be in the table, plus the number of collisions with different keys, which is yk. So the expectation of the number of collisions is, by the property of linearity of expectation, equal to the sum of expectations of variables x, k, l. And we have an upper bound on the expectation of each of those variables, which is 1 over m. So this sum is at most sum for all keys L different from k, which are in the table T, of value 1 over m. And there are at most n summands in this sum, because the size, the number of keys in the hash table T is n. So at most n of them are both in the table and different from k. So this sum is at most n over m, and that is the same as alpha, the load factor. And so the expectation of the chain length is the expectation of 1 plus yk, and by linearity is the same as expectation of 1 plus expectation of yk, but expectation of constant 1 is just 1, and expectation of yk we've just estimated from above, and so we have an upper bound on the expected chain length, which is 1 plus alpha. So we proved our theorem. Now here is a corollary from this theorem, which basically says that if you work with your hash table right, then your operations will on average run in constant time. More formally, if you do some n operations with your hash table, which include insertions, deletions, and modifications, but the total number of insertions is big O of m, where m is the size of the hash table, then the total time to make all those operations will be big theta of n. Well, of course, it will be at least n to make n operations, but it will be also at most proportional to n, and thus the amortized time per each operation will be big O of 1 on average. Let's prove this corollary. We have big O of m insertions, so the total number of keys stored at any moment is at most big O of m. N is big O of m, and then alpha, which is n over m, must be big O of 1, must be constant. And then 1 plus alpha, our upper bound on the expected chain length, is also big O of 1. And it means that on average, the expected running time of each operation is big O of 1. And then when we sum the expectations of running time for each operation, we get the expected running time of all n operations, again by linearity of expectation. And so the expected running time of n operations is big theta of n, because it's big O of n, and also it is at least n. In conclusion, we've just proved upper bound 1 plus alpha on the expected chain length in the case when you use a hash table with chaining scheme and select a random hash function from a universal family. And we've also proven constant amortized expected running time of operations with a hash table if you use universal family chaining and you don't put too many keys in your hash table. Basically, if you keep your load factor below 1, as we discussed in one of the previous videos, then your operations on average run in constant time. And in the next video, we'll also prove that the set of hash functions that we suggested as a universal family for integers is really a universal family. We will prove that formally. Hi! In this video, we will prove that the set of functions we suggested to use with integers is really a universal family of hash functions. This video will be heavy on math, but it is optional. We will use properties of prime numbers, of modular arithmetics, we will use the concept of one-to-one correspondence, properties of upper integral part of real number, and probabilities, of course. So the theorem is that the set of functions we suggested, calligraphic h with index p, is the set of all hash functions indexed by p, a, and b, where p is a prime number and a and b are parameters, and those parameters generate hash functions. So the formula for the hash function is on the slide, and parameters a and b are from 1 to p minus 1 and from 0 to p minus 1 respectively. So this is a family of hash functions which contains p multiplied by p minus 1 different hash functions for different pairs a, b. So this set of hash functions is a universal family for the universe of keys which are integers from 0 to p minus 1. And of course it will be also a universal family for any subset of this universe. Now let's prove this theorem. To do that we first need a lemma. So select some hash function with parameters a and b from our set calligraphic HP and fix some keys x and y which are different. Then the intermediate values which we compute while computing the hash value of keys x and y. So ax plus b modulo p and ay plus b modulo p, those are the intermediate values before we take the value modulo m and get the actual value of the hash function from our family. So those values are always different for different keys in the universe. We will prove this lemma by contradiction. So suppose r is equal to s, or ax plus b is equal to ay plus b modulo p. We subtract the right part from the left part, and we see that a multiplied by x minus y is equal to 0 modulo p. And that means that p divides product of a and x minus y. But now recall that p is a prime number, and so it means that either p divides a or p divides x minus y. But a is between 1 and p minus 1, so a is a positive integer less than p, and p is prime, so p cannot divide a, and thus p must divide x minus y. But x and y are between 0 and p minus 1, so their difference is by absolute value less than p, and p divides x minus y. So the only value for x minus y for which it is possible is 0. X minus y is equal to 0. And so x is equal to y. But this contradicts our initial assumption that x and y are different keys. And so we proved by contradiction that r is not equal to s. There is a corollary from that for a hash function h, which is without taking modulo m, there are no collisions. And an important corollary is that for a hash function which is before taking modulo m, there are no collisions for the universe of integer keys from 0 to p minus 1. Now we need another lemma, that for any pair of different keys x and y, there is a one-to-one correspondence between pairs of numbers a and b, which generate different hash functions in our family, and pairs of numbers r and s, which are the intermediate values in the computation of hash function of keys x and y. So let's prove that. First, note that different pairs a, b generate different pairs rs, and that is because if we have some pair rs, we can uniquely solve for a and b modulo p with these formulas. So if there is any other pair a prime b prime which leads to the same r and s, then actually a prime and b prime have to be equal to a and b respectively because of these equations. So now we know that different pairs a and b generate different pairs rs. And we know that the total number of pairs ab is p multiplied by p minus 1, because there are p minus 1 values for a and independently p values for b. So total number of pairs is p multiplied by p minus 1. And also it turns out that the total number of pairs rs is also p multiplied by p minus 1, because the total number of pairs rs with values from 0 to p minus 1 is p squared, but r must be different from s, so we must subtract p from that, and it will be p squared minus p, which is the same as p multiplied by p minus 1. So the number of pairs ab is the same as the number of pairs rs, and different pairs ab lead to different pairs rs, and that means that there is a one-to-one correspondence between these pairs and these pairs. And the corollary from that is that if we select some pair of different keys x and y, and we select any hash function at random from our family with equal probability, which is 1 over p multiplied by p minus 1, because there are p multiplied by p minus 1 different hash functions in our family, then each pair of values Rs, which are intermediate values, happen with equal probability, again 1 over p multiplied by p minus 1. So why is that? Well, we know that there is a one-to-one correspondence between pairs AB and pairs Rs, and selecting a hash function from our family is the same as selecting random pair AB. We know that the probability of any pair AB is 1 over p by p minus 1, and so the probability of any pair Rs is the same as the probability of the corresponding pair AB. So it is always 1 over p by p minus 1. So we proved our corollary. Now let's prove the initial theorem. The probability of collision for a fixed pair of keys x and y which are different is the same as the probability that r modulo m is the same as s modulo m. We know that r is different from s, but they still can be equal modulo m, because m can be less than p, and in most cases it is actually less than p. So we again note that each pair Rs has probability 1 over p by p minus 1, and we'll estimate the probability of collision using this fact. Note that for each fixed r from 0 to p minus 1, there are at most upper integral part of p over m minus 1 such value of s that s is different from r, and r modulo m is the same as s modulo m. So why is that? Well, let's assume without loss of generality that r modulo m is 0, and look at the row of numbers from 0 to p minus 1. Then the numbers which have the same remainder modulo m as r are 0, m, 2m, 3m, 4m, and so on, up to upper integral part of p over m minus 1 multiplied by m. We cannot multiply the next integer by m because that will be already bigger than p minus 1. So in total there are upper integral part of p over m different integers between 0 and p minus 1 which have the same remainder modulo m as r. But s also needs to be different from r, so the number of such s is less by 1. And now the probability of collision is equal to probability of r modulo m equal to s modulo m, and that is at most sum of probabilities of all such pairs Rs for which this equality holds. So we sum over all different values of r from 0 to p minus 1, and then we sum over all pairs which contain this r and for which s modulo m is the same as r modulo m. We estimated that there are at most integral part of p over m minus 1 such s for any fixed r. And the probability of any final pair of this r and any s with the same remainder modulo m is 1 over p by p minus 1. So the total probability is at most this sum. And the sum has exactly p summands, and it has p in the denominator, so we can just remove the sum and the denominator, and we get upper integral part of p over m minus 1 divided by p minus 1. Then we use the property that upper integral part of p over m is at most p plus m minus 1 over m. And then when we make the common denominator and remove all the things that cancel out, we see that it is equal to 1 over m. So we just proved that the probability of r modulo m being the same as s modulo m is at most 1 over m. And that proves that the probability of collision for some fixed pair of different keys x and y is at most 1 over m. And that is the property of universal family that we needed to prove. So we finally proved our theorem. In conclusion, we've just proved that the suggested family is really a universal family for integers, but note an important thing, that integers are not unbounded, only integers from 0 to p minus 1. So if you need to hash really big integers, you will need to select a prime number that is bigger, even bigger than the largest of those numbers. And then you will get a universal family for that prime number, and it will work for your integers. We also proved in the previous video the upper bound for expected chain length using a universal family and constant amortized expected running time of operations with hash table. We also proved in the last lecture. So now we have the whole picture. We have a universal family for integers, and we have proofs that if we use a universal family, that your operations work fast. So now we are confident that if you use the suggested family for integers, then the operations with the hash table storing those integers will run fast in practice, at least on average. Hi! In the previous videos, you've learned how to quickly look up name in your phone book given the phone number. And we want to learn to solve the reverse problem. Given a name, look up a phone number of the corresponding person. To do that, we need to implement the map from names to phone numbers. And we can again use hash tables, and we can again use chaining as in the previous sections, but we need to design a hash function that is defined on names. And more generally, we want to learn to hash arbitrary strings of characters. And by the way, in this video you will also learn how hashing of strings is implemented in the Java programming language. But first, let's introduce a new notation. Denote by s enclosed in vertical lines the length of string s. For example, the length of string A is 1, length of string AB is 2, and length of string ABCDE is 5. So now, how to hash strings? Well, when we are given a string, we're actually given a sequence of characters. From S0 to S length of S minus 1, we number the characters of the strings from 0 in this lecture, and S of I is an individual character that is in the ith position in the string. I state that we should use all the characters when we compute our hash function of a string. Indeed, if we don't use the first character, there will be many collisions. For example, if the first symbol of the string is not used, then the hash value of strings AA, BA, and so on up to ZA will be the same, because however we compute the value of the hash function, it doesn't use the value of the first character, and if everything else in the string stays the same, and we only change the first character that doesn't influence the value of the hash function, then the value of the hash function must be the same. And so there will be a lot of collisions, and we want to avoid collisions. So we need to use value of each of the characters. Now, we could do a lot of things with that. For example, sum the values of all the characters or multiply them, but we will do something different. Well, first, to even compute something on a string, we need to convert each character of the string to an integer code. For example, that can be ASCII code or Unicode corresponding to that symbol on your computer. That doesn't really matter. And also, we will again need to choose a big prime number p, the same as we used in the integer hashing. So suppose we've chosen some big prime number p. Now we introduce a new family of hash functions called polynomial family of hash functions. So calligraphic p is the family of hash functions which is indexed by small p, which is our big prime number, and also indexed by x. And x is a parameter which changes from 1 to p minus 1. And so the value of a hash function indexed by p and x on a string s is the following sum. It is a polynomial sum where we multiply the integer code corresponding to the ith character of s. We denote it by s of I, the same as the character itself. We multiply it by x to the power of I. We sum all these things up and we take the value modulo p. So this is a family of hash functions, and the cardinality of all those hash functions is p. So any such hash function returns value from 0 to p minus 1. And how many hash functions are there in this family? Well, of course, there are exactly p-1 different hash functions, because to choose to define a hash function from this family, we just need to choose the value of x. And x changes from 1 to p-1, and it's an integer number, of course. So how can we implement a hash function from this family? So the procedure polyhash, which takes as input string s, prime number p, and parameter x, implements the hash function from our family. It starts with assigning value of 0 to the result, to the hash value we will return in the end, and then it will go from right to left in our string and compute new value based on the value of the corresponding character. And there is a formula in the code that does exactly that, and I will show you by example that what we get in the end by applying this formula is exactly what we want. So basically we start with a hash value of 0, and then we start with I equal to 2 if the length of our string s is 3. We start with length of s minus 1, which is 2. We have current value of hash equal to 0, so we multiply this 0 by x and get 0. Then we add the value of s of I, which is s of 2, and take it modulo p. And so, after first iteration of the for loop, we get s of 2 modulo p. What happens is the next iteration is that I is decreased and I is now 1. And we multiply the current value s of 2 by x, and we add s of 1, and take everything modulo p. And what we get is the same as s of 1 plus s of 2 multiplied by x modulo p. And in the last iteration, I is decreased to 0. We multiply the current value by x, and what we get is s of 1 multiplied by x plus s of 2 multiplied by x squared. And then we also add s of 0 to the sum and take everything modulo p. And the result is s of 0 plus s of 1 multiplied by x plus s of 2 multiplied by x squared. Exactly as we wanted, a polynomial hash function with prime p and parameter x. And by the way, the implementation of the built-in hashcode method in the class string in Java is very similar to our procedure polyhash. The only difference is that it always uses x equal to 31, and for some technical reasons it avoids the modulo p operator. It just computes the polynomial sum without any modulo division. So now you know how a function that is used probably trillions of times a day by thousands and many thousands of different programs, how this function is implemented. So now about the efficiency of our polynomial family. First lemma says that for any two different strings s1 and s2 of length at most l plus 1, if you choose a random hash function from the polynomial family by selecting a random value of x, parameter x, from 1 to p-1, you can select a random hash function from the family. So if you select a random hash function from the polynomial family, then the probability of collision on these two different strings is at most L divided by P. So that doesn't seem like a good estimate because L can be big, but actually it is your power to choose P. If you choose very, very big prime number P, then L over P will be very small. And note that it won't influence the running time of the polyhash procedure, because the running time of this procedure is big O of length of s. It only depends on the length of the string. It doesn't depend on the length of number p, more or less. So if you select a really big number p, then the probability of collision will be very small and the hash function will still be computed very fast. The idea of proof of this lemma is that the equation, polynomial equation of power L modulo prime number p has at most L different solutions x. And basically, when we consider two strings s1 and s2, the fact that the hash value for some hash function from the polynomial family is the same for these two strings means that x corresponding to our hash function is a solution of this kind of equation. And the fact that strings are different makes sure that at least one of the coefficients of this equation is different from 0, and that is essential. If the strings were the same, of course, the value of any hash function on them will be the same, but if they're different, then the probability is at most L over P, because there are only L or less different x for which the hash function can give the same value on these two strings. Now we know a polynomial hash family for hashing strings, but there is a problem with that family. All the hash functions in that family have a cardinality of p, where p is a very big prime number. And what we want is the cardinality of hash functions to be the same as the size of our hash table. So we want a small cardinality. So we won't be able to use this polynomial hashing family directly in our hash tables. And we want to somehow fix the cardinality of the functions in the polynomial family. And the good way to do that is the following. We design a new complex transformation from strings to numbers from 0 to m-1. So we select the cardinality m, and we want to design a function from strings to numbers between 0 and m-1. And to do that, we first apply a random hash function from the polynomial family to the string, and we get some integer number modulo p. And then we can apply a random hash function from the universal family for integers less than p, and get a number between 0 and m-1 if we select it from a universal family with cardinality m. So we now have a complex transformation which is two-stage. First, take a string and apply a random function from the polynomial family, and then apply a random function from the universal family for integers to the result. And you get a number from 0 to m-1 from the string. Note that it is very important that we first select both random function from the polynomial family and the random function from the universal family for integers. And we fix them, and we use the same pair of functions for the whole algorithm. And then the whole function from string to integer number between 0 and m-1 is a deterministic hash function. And it can be shown that the family of functions defined this way is a very good family. It's not a universal family, but it's a very good family with low probability of collision. More specifically, if you take any two different strings s1 and s2 of length at most l plus 1, and you choose a cardinality m, and you apply the process described to build a hash family from strings of length at most l plus 1 to integers numbers between 0 and m-1, then the probability of collision for a random function from that family is at most 1 over m plus l over p. So that is not a universal family, because for universal family there shouldn't be any summand l over p. The probability of collision should be at most 1 over m, but we can be very, very close to universal family because we can control p. We can make p very big, and then l over p will be very small, and so the probability of collision will be at most 1 over m plus some very small number, and so it will be either even less than 1 over m or very close to it. So polynomial hash and then universal hash over integers is a good construction of a family of hash functions. A corollary from the previous lemma is that if we specifically select the prime number p to be bigger than m multiplied by l, then the probability of collision will be at most big O of 1 over m. So it won't be less than 1 over m itself, but it will be at most 1 over m multiplied by some constant. Why is that? Well, because if we rewrite 1 over m plus l over p by 1 over m plus l over ml, then the second expression will be bigger, because p is bigger than ml. And then it is equal to 2 over m, which is big O of 1 over m. So that way we proved that combination of polynomial hashing with universal hashing for integers is a really good family of hash functions. Now, what if we take this new family of hash functions and apply it to build a hash table? Well, I state that for big enough prime number p, we will again have running time on average big O of 1 plus alpha. The length of the longest chain will be big O of 1 plus alpha, where alpha is the load factor of our hash table. And so by wisely controlling the size of the hash table and the load factor, as we learned in the previous videos, we can control the running time and the memory consumption. Of course, computing the hash function itself on some string s is not a constant time operation, because the string can be very long and we need to look through the whole string to compute our hash function. But in the case when all the length of the strings in question are bounded, for example with names, definitely there are no names longer than a few hundred characters, I think, so all they are bounded by some constant L, and so computing hash function on the names takes, of course, big O of the length of the string time, but it is also big O of 1, constant time, because L is a constant itself. And so we can implement a map from names to phone numbers using chaining, using the newly created family of hash functions, which is complex. It first applies polynomial hashing to the string, to the name, and then applies universal family for integers to the result. So we can choose a random hash function from this two-staged family and store our names and phone numbers in the hash table using this hash function. In conclusion, you learned how to hash integers and strings really good so that the probability of collision is small. You learned that the phone book can be implemented as two maps, as two hash tables, one from phone numbers to names and another one back from names to phone numbers. And you managed to do that in such a way that you don't waste too much memory. Load factor of your hash table is between 0.5 and 1. And search and modification on average work in constant time, which is great. And in the next lesson, we will learn to apply hash functions to different problems, such as searching for patterns in text. Hi! In this lesson, you will learn about applications of hashing to problems regarding strings and texts. We will consider the problem of finding patterns in text. The problem is, given a long text T, for example a book or a website or a Facebook profile, and some pattern P, which can be a word, a phrase, a sentence, find all occurrences of pattern in the text. Some examples of that can be that you want to find all occurrences of your name on a website, or you want to find all the Twitter messages about your company to analyze the reviews of your new product, or you could potentially want to detect all the files on your computer which are infected by a specific computer virus. And in that case, you won't find patterns in text, you will find code patterns in the binary code of the program. Anyway, the algorithm will be the same. First, we introduce some new notation, substring notation. We denote by s from I to j the substring of string s, starting in position I and ending in position j. Both I and j are included in the substring. For example, if s is the string a, b, c, d, e, then s from 0 to 4 is the same string a, b, c, d, e, because we index our characters from 0, and a is the character number 0, and e is the character number 4. S from 1 to 3 is b, c, d, because b is the character with index 1 and d is the character with index 3. And s from 2 to 2 is also allowed. It's a string, a substring of length 1, string c. And I shouldn't be more than j, of course, because otherwise there is no substring from I to j. So the formal version of our problem to find pattern in text is that you are given strings t and p as input, and you need to find all such positions I in the text t that pattern p occurs in text t starting from position I. That is the same that to say that a substring of t from I to I plus length of p minus 1, the substring of t starting from I with length equal to the length of the pattern is equal to the pattern. So we want to find all such positions I. And of course, I can be from 0 to length of text minus length of pattern. It cannot be bigger because otherwise the pattern just won't fit in the text. It will be ending to the right from the end of the text. So we start with a naive algorithm to solve this problem. Basically, we go through all possible positions I from 0 to difference of the length of the text and pattern, and then for each such position I, we just check character by character whether the corresponding substring of t starting in position number I is equal to the pattern or not. If it is equal to the pattern, we append position I to the result. So first we need to implement a function to compare two strings, and we start with checking whether their lengths are the same or not. Of course, if the length of strings is different, then the strings are definitely different, so we return false. If that's not the case, then the length of the strings are equal. And then we go through all the positions in both strings with I going from 0 to length of the first string minus 1. And if the corresponding symbols on the ith position differ, then the strings are different. Otherwise, they are the same. Now we will use this function to find all occurrences of pattern in the text. The procedure find pattern naive implements our naive algorithm. So we start with an empty list in the variable result, and then we go through all the possible positions where pattern could start in text for I from 0 to length of text minus length of the pattern, and we check whether the substring starting in I with length equal to length of the pattern is equal to the pattern itself. If it is, then we append position I to the result, because this is a position where pattern occurs in text. And in the end, we just return the list that we collected by going through all possible positions of pattern in the text. I state that the running time of this naive algorithm is big O of length of the text multiplied by length of the pattern. Why is that? Well, each call to the function r=equal runs in time big O of length of the pattern, because both strings we pass there are of lengths the same as the length of the pattern, and the running time of r=equal is linear. And then we have exactly length of t minus length of p plus 1 calls of this function, which total to big O of length of t multiplied by length of p, because we always consider that length of the text is bigger than the length of the pattern, and so this is the upper bound for our running time. Actually, this is not just the upper bound, it's also a lower bound. For example, if we consider text T, which consists of many letters A, and pattern P, which consists of many letters A and then letter B in the end. And also we choose such text that it is much longer than the pattern, which is basically almost always true in the practical problems. Then for each position I in T, which we try to observe, the call to r=equal that we make has to make all the maximum possible number of comparisons, which is equal to the length of the pattern P. Why is that? Because when we call r=equal for substring of T starting in position I and for the pattern P, we see that they differ only in the last character. So r=equal has to check all the previous characters until it comes to the last character of P and determines that actually pattern is different from the corresponding substring of T. Thus, in this case, the naive algorithm will do at least proportional to length of T multiplied by length of P operations. Thus, our estimate is not just big O, it is big theta, which means that it is not only an upper bound, but also a lower bound on the running time of the naive algorithm. And in the next video, we will introduce an algorithm based on hashing, which has better running time. Hi! In this video, we will introduce the Rabin-Karp's algorithm for finding all occurrences of a pattern in the text. At first, it will have the same running time as the naive algorithm from the previous video, but then we'll be able to improve it significantly for the practical purposes. So we need to compare our pattern to all substrings S of text T with length the same as the length of the pattern. And in the naive algorithm, we just did that by checking character by character whether pattern is equal to the corresponding substring. And the idea is we could use hashing to quickly compare P with substrings of T. So how to do that? Well, let's introduce some hash function h, and of course if it is a deterministic hash function and we see that the value of hash function on the pattern P is different from the value of this hash function on some string S, then definitely P is not equal to S, because h is deterministic. However, if the value of hash function on P is equal to the value of hash function on S, P can be equal to S, or it can be different from S if there is a collision. So to exactly check whether P is equal to S or not, we will need to call our function R_equal on P and S. And so this doesn't yet save us any time, but we hope that we could call this function R_equal less frequently because there will be only a few collisions. So we will use polynomial hashing family, calligraphic P with index P small, with some big prime number P. And if P pattern is not equal to S substring of text, then the probability that the value of the hash function on the pattern is the same as the value of the hash function on the substring is at most length of the pattern divided by our big prime number P. And we will choose a prime number P big enough so that this probability will be very small. So here is the code of our algorithm Rabin-Karp. It takes as input text T and pattern P. And it starts by initializing the hash function from polynomial family. We first choose a very big prime number P. We'll talk later about how to choose it, how big it should be. And we also choose a random number x between 1 and P minus 1. Choose the specific hash function from the polynomial family. And we initialize our list of positions where pattern occurs in text with an empty list. We also pre-compute the hash value of our pattern, and we call the polyhash function to do that. And then we again need to go through all possible starting positions of pattern in the text. So we go for I from 0 to difference of the length of text and pattern. And for each I, we take the substring starting in this position I and of length equal to the length of the pattern, which is T from I to I plus length of the pattern minus 1. And we compute the hash value of this substring. And then we look at the hash of the pattern and the hash of the substring. If they are different, then it means that definitely P is not equal to this substring, and so P doesn't occur in position I, and so we don't need to do anything in this iteration, so we just continue to the next iteration of the loop without calling R_equal. However, if hash values P hash and T hash are equal, then we need to check if it's true that P is really equal to the substring of T starting in position I, or it is just a collision of our hash function. And to do that, we make a call to R_equal and pass there the substring and the pattern. If R_equal returns true, it means that pattern is really equal to the corresponding substring of text, and then we append position I to our result, because pattern P occurs in position I in the text T. Otherwise, we just continue to the next iteration of our for loop. So this is more or less the same as naive algorithm, but we have an additional checking of hash value, and so we're not always calling R_equal. We're calling R_equal either if P is equal to the corresponding substring of T or if there is a collision. let's estimate the running time of this algorithm. So first we need to talk about false alarms. We'll call false alarm the event when p is compared with the substring of t from I to I plus length of p minus 1, compared inside the R equal procedure, but pattern p is actually not equal to this substring. So it is a false alarm in the sense that p doesn't occur in the text t starting from position I, but we still called the R equal function, and we need to go character by character through p and the substring to test that they're actually not equal. So the probability of false alarm, as we know from the previous lesson, is at most length of the pattern over prime number p, which we choose. So on average, the total number of false alarms will be the number of iterations of our for loop multiplied by this probability. And so this total number of false alarms can be made very small if we choose prime number p bigger than the product of length of the text and length of the pattern. Much bigger. So now let's estimate the running time of everything in our code except for calls to the R equal function. So the hash value of the pattern is computed in time big O of length of the pattern. Hash of the substring corresponding to the pattern is computed in the same big O of length of the pattern time, and this is done length of text minus length of the pattern plus 1 times, because that is the number of iterations of the for loop. So the total time to compute all those hash values is big O of length of text multiplied by length of the pattern. Now, what about the running time of all calls to R equal? Each call to R equal is computed in big O of length of the pattern, because we pass there 2 strings of length equal to length of the pattern. However, R equal is called only when the hash value of the pattern is the same as the hash value of the corresponding substring of t. And that means that either p occurs in position I in text t, or there was a false alarm. And by selecting the prime number to be very big, much bigger than the product of the length of text and the length of pattern, we can make the number of false alarms negligible, at least on average. So, if q is the number of times that pattern p is actually found in different positions in the text t, then the total time spent in R equal on average is big O of q, which is number of times p is really found, plus the fraction t minus p plus 1 multiplied by p and divided by prime p, which is the average number of times that a false alarm happens. So q plus number of false alarms is the number of times that we need to actually call function R equal. And then the time spent inside the function R equal is proportional to the length of the pattern. So totally this is the same as big O of q multiplied by the length of the pattern, because the second summand can be made really small, less than 1, if we choose big enough prime number p, and we only get the first summand multiplied by length of the pattern. And now the total running time of the Rabin-Karp's algorithm in this variant is big O of length of text multiplied by length of pattern plus q multiplied by length of pattern. But, of course, we know that the number of times that pattern occurs in text is not bigger than the number of characters in text, because there are only so many different positions where the pattern could start in text. So this sum is dominated by the summand big O of length of text multiplied by length of the pattern. So this is basically the same running time as our estimate for the naive algorithm. So we haven't improved anything yet, but this time can be improved for this algorithm with a clever trick, and you will learn it in the next video. Hi! In this video you will learn to significantly improve the running time of the Rabin-Karp's algorithm. And to do so we will need to look closer into the polynomial hashing and its properties. Recall that to compute a polynomial hash on a string s, we first choose a big prime number for the polynomial family, Then we choose a random integer x from 1 to p minus 1 to select a random hash function from the family. And then the value of the hash function is the polynomial of x with coefficients which are characters of the string s. And to compute this hash function on a substring of a text t, starting in position I and having the same length as the pattern for which we are looking in the text, we need to also compute a similar polynomial sum. It goes from character number I to character number I plus length of the pattern minus 1. And we need to multiply each character by the corresponding power of x. For example, t of I will be multiplied by x to the power of 0, because this is the first character of the substring. And the last character will be multiplied by x to the power of length of the pattern minus 1. And here is a formula on the slide. And the idea for the improving of the running time is that the polynomial hash value for two consecutive substrings of text with length equal to the length of the pattern are very similar, and one of them can be computed given the another one in constant time. We introduce a new notation. We denote by big H of I the hash value for the substring of the text starting in the position I and having the same length as the pattern. Now let's look at the example. Our text is ABCBD, and we need to convert the characters to their integer codes. And let's assume for simplicity that the code for A is 0, for B is 1, for C is 2, and for D is 3. Then our text is actually 0, 1, 2, 1, 3. Also, we will assume in this example that the length of the pattern is 3. We don't need to know the pattern itself, we just fix its length. So we will need to compute hash values for the substrings of the text of length 3. There are 3 of them, ABC, BCB, and CBD. We start with the last one, CBD. To compute its hash value, we first need to write down the powers of x under the corresponding characters of the text. Then we need to multiply each power of the x by the corresponding integer code of the character, and we get 2x and 3x squared. Then we need to sum them, and we also need to take the value modulo p, but on this slide we will just ignore modulo p, it will be assumed in each expression. Now let's look at the hash value for the previous substring of length 3, which is BCB. We again need to write down the powers of x under the corresponding integer codes of the characters. We again need to multiply the powers of x by the corresponding integer codes and get 1, 2x, and x squared. We need to sum them. Now note the similarity between the hash value for the last substring of length 3 and the previous substring of the length 3. To get the last two terms for BCB, we can multiply the first two terms for CBD by x. And we will use this similarity to compute the hash for BCB given the hash for CBD. So again, big H of 2 is the same as hash value of CBD because it starts in the character with index 2, and it's equal to 2 plus x plus 3x squared. Now let's compute big H of 1 based on that. It's the hash value of BCB, and we know it's equal to 1 plus 2x plus x squared, modulo p. Now let's rewrite this using this property of multiplication by x, the terms for the CBD. So it's equal to 1 plus x multiplied by the first two terms for CBD, which are 2 plus x. Now we don't want to use just the first two terms for CBD, we want to use the whole CBD. So we write this as following: 1 plus x multiplied by the whole expression for CBD. But now we need to subtract something to make the equality true. And that something is the last term, x multiplied by 3x squared, which is the same as 3x cubed. So we subtract 3x cubed. Now we regroup the summands and we write as this is equal to x multiplied by the hash value for CBD, which is big H of 2. And we add 1 to it, and we subtract 3x cubed. In the general case, there is a very similar formula. So here is the expression for big H of I plus 1. And notice that the powers of x are, in each case, j minus I minus 1, because the substring starts in position I plus 1. So we subtract I plus 1 from each j in the sum. And the expression for big H of I is very similar, but for each power of x, we subtract just I from j, because the substring starts in position I. Now let's rewrite this expression so that it is more similar to big H of I plus 1. And to do that, we start summation not from I, but from I plus 1. And we also end it one position later. So the first sum is now very similar to the expression for H of I plus 1. Just the powers of x are always bigger by 1. And also we need to add t of I, which is not accounted for in this sum, and we need to subtract its last term because it's not in the expression for big H of I. And that is t of I plus length of the pattern multiplied by x to the power of length of the pattern. Now we notice that the first sum is the same as x multiplied by the value of hash function for the next substring, big H of I plus 1. And the second and third terms are the same. So now we get this recurrent formula. To compute big H of I, if we know already big H of I plus 1, we need to multiply it by x and then add t of I and subtract another term. Notice that t of I and t of I plus length of the pattern we just know, and x to the length of the pattern is a multiplier that we can pre-compute and use for each I. Now let's use this in the pseudocode. Here's the function to pre-compute all the hash values of our polynomial hash function on the substrings of the text t with the length equal to the length of the pattern and with prime number p and selected integer x. We initialize our answer, big H, as an array of length of text minus length of pattern plus 1, which is the number of substrings of the text with length equal to the length of the pattern. Also initialize s by the last substring of the text with the length equal to the length of the pattern. And we compute the hash value for this last substring directly by calling our implementation of polynomial hash with this substring, prime number p, and integer x. Then we also need to pre-compute the value of x to the power of length of the pattern and store it in the variable y. To do that, we initialize it with 1 and then multiply it length of p times by x and take this modulo p. And then the main for loop, the second for loop, goes from right to left and computes the hash values for all the substrings of the text, but for the last one for which we already know the answer. So to compute h of I given h of I plus 1, we multiply it by x, then we add t of I and we subtract y, which is x to the power of length of p, by t of I plus length of the pattern. And we take the expression modulo p. And in the end we just return the array with the pre-computed values. So to analyze its running time, we know that initialization of array h of s and the computation of the hash value of the last substring all take time proportional to the length of the pattern. Also, pre-computation of the x to the power of length of p takes time proportional to the length of the pattern. And the second for loop takes time proportional to length of the text minus length of the pattern. And all in all, it's big O of length of the text plus length of the pattern. Now again, polynomial hash is computed in time proportional to the length of the pattern. First for loop computing the power of x also, and the second for loop, which goes through all the substrings of the text with length equal to the length of the pattern, takes length of text minus length of pattern time. And the total pre-computation time is proportional to the sum of length of the text and the pattern. And in the next video, we'll use these pre-computed values to actually improve the running time of the Rabin-Karp's algorithm. Hi! In this video, we will use the pre-computed hashes from the previous video to improve the running time of the Rabin-Karp's algorithm. And here is the pseudocode. Actually, it is very similar to the pseudocode of the initial Rabin-Karp's algorithm, and only a few lines changed. So we again choose a very big prime number p, and we choose a random number x from 1 to p minus 1 to choose a random hash function from the polynomial family. We initialize the result with an empty list of positions, and we compute the hash of the pattern in the variable p hash directly using our implementation of polynomial hash. And then we call the precompute hashes function from the previous video to precompute big H, an array with hash values of all substrings of the text with length equal to the pattern P. We need them to check whether it makes sense to compare pattern to a substring if their hashes are the same, or maybe if their hashes are different, then there is no point comparing them character by character, because it means that pattern is definitely different from the substring. So then our main for loop goes for all I starting positions for the pattern from 0 to length of text minus length of pattern, as in the previous version of the Rabin-Karp's algorithm. And the main thing that changes is that we compare the hash of the pattern not with the value of hash function computed on the fly, but with the pre-computed value of the hash function for the substring starting in position I, big H of I. If they are different, it means that the pattern is definitely different from the substring starting in position I, and we don't need to compare them character by character, so we just continue to the next iteration of the for loop. Otherwise, if the hash value of the pattern is the same as the hash value of the substring, we need to actually compare them on equality character by character. And to do that, we call function requal for the substring and the pattern. If they are actually equal, we append position I to the result, to the list of all the occurrences of pattern in text. Otherwise, we proceed to the next iteration. And in the end, we return result, the list of all positions in which pattern occurs in the text. Let's analyze the running time of this version of Rabin-Karp's algorithm. First, we compute the hash value of the pattern in time proportional to its length. Then we call the precompute hashes function, which we estimated in the previous video, runs in time proportional to the sum of length of text and the pattern. And then the only other thing that we do is we compare the hashes, and for some of the substrings we call function requal. And we already know from the previous videos that the total time spent in requal is on average proportional to q multiplied by length of the pattern, where q is the number of occurrences of pattern in text. Why is that? Because we only compare pattern to a substring if they're equal or if there is a collision. And we can compare such a big prime P that the collisions have very low probability, and on average they won't influence the running time. So on average, total time spent in requal is proportional to q multiplied by length of the pattern. And then the total average running time is proportional to length of the text plus q plus 1 multiplied by length of the pattern. And this is actually much better than the time for the naive algorithm, because usually q is very small. Q is the number of times you actually found pattern in text. And if you are, for example, searching for your name on a website or for an infected code pattern in the binary code of the program, there will be no or only a few places where you actually find it. And that their number is q. And it is usually much, much less than the total number of positions in the text, which is length of the text. So the second summand, q plus 1 multiplied by length of the pattern, is much smaller than length of the text multiplied by length of the pattern. And if pattern is sufficiently long, then the first summand is also much smaller than length of the text multiplied by length of the pattern. So we improved our running time for most practical purposes very significantly. Of course, it's only on average, but in practice this will work really well. And to conclude, in this module we studied hash tables and hash functions, and we learned that hash tables are useful for storing sets of objects and mappings from one type of object to another one. And we managed to do it in such a way that you can search and modify keys and values of the hash tables in constant time on average. And to do so, you must use good hash families, and you must select random hash functions from good hash families. And you also learned that hashes are not only useful for storing something, but they are also useful while working, for example, with strings and text for finding patterns in long texts. And actually there are a lot more applications of hashing in distributed systems, for example, and in data science. And I will tell you about some applications in distributed systems in the next few optional videos. Hi! In this optional lesson, you will learn a bit about modern distributed systems. And we will start with some interesting inner workings of online storage services which you probably use, such as Dropbox, Google Drive and Yandex Disk. Have you ever wondered how a very big file of tens or hundreds of megabytes can be uploaded almost instantly to your Dropbox account? Or maybe you are interested how Dropbox, Google Drive and Yandex Disk save petabytes of storage space using the ideas from this module on hash tables and hash functions. Or maybe you are interested in distributed systems and distributed storage in general. Then this lecture is for you. So, services like Dropbox and Google Drive use exabytes of storage to store data of millions and millions of users worldwide. And there is a very simple idea on how to actually save some of that space and save some of the costs. So it sometimes happens that users upload the same files. So the first user liked a video with a cat and uploaded it to his Dropbox account just to save it and to show his friends. And then another user also loved this video file. He may have called it a different way, but still uploaded it to his Dropbox account, the exactly same video. And then another user also uploaded this video because this was a viral video and many people liked it, and some of them even decided to upload it to their user accounts in Dropbox. And then what we can do on the level of the whole Dropbox service is, instead of storing all 3 copies of the same video, just store 1 copy and have links from the user's files to this actual physical stored file. And then we've just saved 66% of the storage space because we basically reduced it 3 times. And if you have some large videos, which are also very popular, that you can save this way a significant portion of the storage space which all the users collectively use in Dropbox to store their files. So the question is how to actually implement that. So when you do a new file upload, you need to determine whether there is already the same file in the system or not. And if there is, you just ignore the upload and set a link to the already stored file in the user's account instead of a real file. So there are a few ways to do that, and we'll start with a really simple one. Naive comparison. You take the new file that user wants to upload. You actually upload it to a temporary storage. Then you go through all the stored files and you compare the new file with each of the stored files byte by byte. And if there is exactly the same file, you store a link to this file instead of the new file that user wants to upload. So there are a few drawbacks of this approach. First, you have to first upload the file anyway, so you won't see this miraculous instant upload time of large files with hundreds of megabytes. And second is to compare a file of size S with n other files. It takes time proportional to product of n and s, and that can be huge because the number of files in Dropbox or Google Drive is probably on the order of hundreds of billions or even trillions, and files uploaded are often also very large, like gigabytes. And also, if we use this strategy, then as n grows, as service for online storage grows, the total running time of all uploads will grow as n squared, because each new upload is big O of n, and it's longer and longer and longer as the number of files increases. So this approach won't work long term anyway. So what can we do? First, the idea is, instead of comparing the files themselves, try to compare hashes. As in the Rabin-Karp's algorithm, compare hashes of the files first. If the hashes are different, then the files are definitely different. And if there is a file with the same hash, then upload this new file that the user wants to upload to his account and compare the new file with the old file with the same hash directly byte by byte. Still, there are problems with this approach. First, there can be collisions, so we cannot just say that if two files have the same hash value, then they're equal and we don't need to store the new file. Sometimes different files can have the same hash value and we still have to compare the two files. And also we still have to upload the file to compare directly even if the same file is already stored. And we still have to compare with all n already stored files. So what can we do? Another idea is we can use several hash functions. If we have two equal files, even if we compute 5 different hash functions, their values on these two files will be the same. So the idea is choose several different hash functions independently. For example, take functions from polynomial family with different multiplier x or with different prime numbers p, and then compute all the hashes for each file. And if there is a file which is already stored and has all the same hash values, then the new file is probably the same as the file already stored. And in this case, we might want to not even upload the new file at all and save the time and make the upload seem immediate. And to do that, we need to just compute hashes locally before upload and only send through the network, which can be slow, the values of the hash functions, which are much less in terms of space than the initial huge file. So we compute the hash values locally, we send those 3 or 5 hash values over the network to the service. They're compared to the hash values of the files already stored, and if there is a file with the same set of hash values, we don't upload our new file. And this is how the instant upload works sometimes, when you try to upload the file which is already stored by someone else. Well, of course there is a problem with collisions, because collisions can happen even if you have several different hash functions. Still, there can be 2 different files which have the same set of hash values even for several hash functions. And there are even algorithms which on purpose find 2 different files which have the same value of a given hash function, if you know for which hash function you are trying to find a collision. However, for hash functions used in practice, collisions are extremely rare and hard to find. And if you use more than one hash function, if you use 3 or even 5, then you probably won't see a collision in a lifetime. So this is actually done in practice. You compute several different hash functions which nobody knows, and then it is so hard to find 2 files for which all the hash functions have the same values that a new file is considered to be equal to the old stored file if all the hash values coincide with the hash values of the file already stored. So we still have an unsolved problem that we need to do big O of n comparisons with all the already stored files. So how can we solve this problem? Well, we can first pre-compute hashes, because when a file is submitted for upload, hash values for this file are computed anyway. So we can store the addresses of the files which are already stored in the service in a hash table, and along with the addresses of the files, we'll store those hash values for each file. So we pre-compute them and store them. And when we need to search for a new file, we actually only need to search in the hash table, and we need only the values of the hash functions on this file to search for it. We don't need to provide the file itself. So we search for the hash values in the hash table, and if we find some file stored in this hash table with the same set of hash values, then we know that there is already such file stored in the system. So the final solution is the following. We choose from 3 to 5 different good hash functions for which it is hard to find collisions, so that we don't see collisions in practice. We store the addresses of the files and the hashes of those files in the hash table, and before we upload a new file, we compute the hashes locally, we send them over the network to the service, we check whether there is a file in a hash table with the same hash values, and if all the hashes for some stored file coincide with the hashes of the new file, then the search is successful, And in this case, we don't even upload the file. We just store a link in the user account to the existing already stored file. So this how we can do instant upload to Dropbox or Google Drive or Yandex Disk. And this is actually how they save a lot of space, probably petabytes of space in their services. However, there are more problems to this, because it turns out that billions of files are uploaded daily, for example, into Dropbox, and it means that probably around trillions are already stored there, and that is just too big for a simple hash table on one computer. And also, millions of users upload simultaneously their files, and so this is also too many requests for a single hash table. And so you need some more sophisticated solution to cope with those two things. And see our next lecture to understand how that problem is solved. Hi! In this video, you will learn how to store a whole lot of objects, how to store big data using distributed hash tables. So big data is when you need to store trillions or more objects, for example, trillions of file addresses in Dropbox, or user profiles or emails and user accounts, for example, in Gmail or services like that. And you need fast search and fast access to that data. So hash tables in general is a good solution for that problem because they give constant time search access on average, but for number of keys on the order of 10 to the power of 12, the amount of memory that a simple hash table will store becomes too big to store it on one computer. And so we need to do something else. We need to use more computers probably. And the solution to this is distributed hash tables. So the first idea for a distributed hash table is the following. Just get more computers, get 1,000 computers. If you are Google or Dropbox, you can do that. And then you will store your data on many computers. And you will do the following. You create a hash table on each of those computers. And then you will separate the data between those computers. So each computer will store its own part of the data. And you need to determine quickly and automatically and deterministically which computer should store some object O. And there is a simple way. You just compute some hash function of this object, modulo 1000. So you get basically a value from 0 to 999 for each object. And that will be the number of the computer which should store this object. And then you send request to that computer and search or modify what you need to do with that object in the local hash table of that computer. And that seems to already solve our problem, because if a new request comes, you quickly compute a hash function on the object and you know where to send your request, and then that computer just looks up in its local hash table. Each of the local hash tables can be 1,000 times less than the total amount of data stored, and so it is scalable. If you need more data, you just get more computers and everything works. Still, there are problems with this approach, and the main problem is that computers sometimes break. And especially if you have a lot of computers, then they break pretty often. For example, if a computer breaks once in 2 years on average, then if you have 1,000 computers, on average more than one computer breaks every day, because there are less than 1,000 days in 2 years and you have 1,000 computers. So what do you do in that case? You don't want to lose your users' data, so you need to store several copies of the data. So basically you cannot do it in a way that every computer stores its part of data. Each part of data should be stored on several computers. And what happens then when some computer breaks? Well, luckily the data which is stored on this computer is also stored somewhere else. But if that's the only copy left after this computer broke, you need to also copy that data to some other computer so that it is again stored in several places. And you need to relocate the data from the broken computer. And also, sometimes your service grows and you want to buy more computers, you want to reply faster to your clients, and new computers are added to the cluster. And then this formula take hash value of the object modulo 1000, and this is the number of computer on which your object is stored. It no longer works because the numbers of the computers always change, new computers come in, broken computers come out, and so you need something else. And one way to solve this is called consistent hashing. So First, we choose some hash function with some cardinality m, and we choose a circle, a regular circle, and we put numbers from 0 to m-1 on this circle in a clockwise order. And then each object O is mapped to some point on this circle corresponding to the number hash value of this object, which is from 0 to m-1, so it always maps to some of the numbers on the circle. And also each computer ID is mapped to the same circle. We hash the ID of the computer and we get the number of the point to which this computer is mapped. So let's look at the picture. Here's our circle, and for example m is 12, then we put 12 points around this circle and we put numbers from 0 to 11 around this circle. And then objects such as, for example, name Steve can be mapped to some of those 12 points, and if hash value of Steve is 9, then Steve is mapped to the point with number 9. And also computers can be mapped to points, and for example this computer with ID 253, if the hash value of 253 is 5, then this computer is mapped to the point 5. So what do we do then? We make a rule that each object is stored on the so-called closest computer. Closest in terms of the distance along the circle. And in this case, each computer stores all objects falling on some arc, which consists of all objects which are closer to this computer than to any other computer. Let's again look at the picture. This is the circle, and there are 6 computers. And these computers map to some points on this circle. And then the arcs of the same color as the computers near them are the sets of points which are closer to the corresponding computer than to any other computer. And so each computer is responsible for some arc of this circle, for all the keys that are mapped to this arc. And so what happens when computers come in, because new computers are bought, or when computers are broken? When a computer goes off, when it's broken, its neighbors take its data. So it has 2 neighbors, and its arc is divided into parts, and one part goes to the right neighbor, and another part goes to the left neighbor. And when a new computer is added, it takes data from its neighbor. So it comes between some 2 already existing computers, and it takes a part of the arc of one of them and a part of the arc of another one, and he gets its arc. So let's look at an example. For example, the yellow computer breaks and it goes away, and then the green and the blue computer will take its arc and divide it between themselves. So that's what happens. Another problem which still needs to be solved is that when some computer breaks, we need to copy or relocate the data. And how will a computer know where to send the data that it stores? Well, we need another rule for that. We cannot store the addresses of all the other computers on each of the computers, because that is inconvenient. We will have to constantly update that information. But each node, each computer will be so-called acquainted with a few neighbors. So it will store the network addresses of some of its neighbors. And the rule is that for any key, each node will either store this key itself, or it will be acquainted, it will know some other computer which is closer to this key in terms of the distance on the circle. And that way, if a request comes to some node, any node in the network, about some key, it either can find this key inside its own storage, or it will redirect the request to another node which is closer to this key. And then that node will either store the key or redirect the request to the next node which is even closer to that key. And in finite number of iterations, the request will come to the node which actually stores the key. So that's the idea. And in practice, what we can do is we can put the computers, the nodes on the circle, and then each node will know its immediate neighbors, its neighbors of neighbors, and then its neighbors on distance of 4, and distance of 8, and distance of 16, and for all powers of 2 it will know neighbors to the right and to the left at distance this power of 2. Of course less than n over half. And it's easier to see on the picture again. So suppose we have many nodes, and then the upper node will have links to its right and left neighbor, to its right and left neighbor on distance of 2, and to its right and left neighbor at the distance of 4, and so on. So each node will contain logarithmic number of links to other nodes, which is much better than storing all the other nodes. And if we need to come to some key from some node that doesn't contain it, we'll first jump in the direction where the distance to the key decreases, and we'll jump as much as we can. If the computer at distance 8 is closer than our computer to the key, we'll jump at least by 8. If computer with distance 16 is closer, we'll jump at least 16. If computer with distance 32 is farther, then we will jump just by 16. In this way, we will always jump by at least a half of the distance which divides us from the computer that stores the key itself. And so in a logarithmic number of steps, we will actually come from the current computer to the computer that actually stores our key. And this network of nodes which know some neighbors and they know some of their neighbors is called overlay network. So in conclusion, distributed hash tables is a way to store big data on many computers and access it fast as if it was on one computer. Consistent hashing is one way to determine which computer actually owns the data, which computer stores this particular object. And to do that, consistent hashing uses mapping of keys and computer IDs on a circle. And each computer stores a range of keys on an arc, which is closest to this computer in terms of distance along the circle. And also, overlay network is used to route the data to and from the right computer. So when a computer is broken, first its data needs to be copied to some other computers, and its neighbors take its data. So computer disappears and its arc disappears, but it is actually divided between two neighbor computers, and each of those arcs increases a bit, and they cover the whole data. And then we proceed. If a new computer appears, it takes some data from its right neighbor, some data from its left neighbor, and assembles an arc for itself. And I hope that after this lecture you understand how important are data structures we study in this course to the modern technological industry, distributed systems, and big data.
Hello everybody, welcome back. Today we're going to be starting with a new data structures topic. In particular, we're going to be talking about binary search trees. And today we're going to be giving sort of an introduction to the topic, and we're really going to try and do two things. One is to sort of motivate the types of problems that we want to be able to solve with this new data structure. And secondly, we'll talk a little bit about why the data structures we already know about are not up to this task, and why we really do need something new. So to begin with, let's talk about a few problems that you might want to solve. So one is you want to search a dictionary. You've got a dictionary and you want to find all the words that start with some given string of letters. Okay. Or similarly, you've got a bunch of emails and you'd like to find all the emails that were sent or received during a given period. Or maybe you've got a bunch of friends or a class or something, and you'd like to find the other person in this class whose height is closest to yours. Now, all of these are examples of what we might call a local search problem. What you want for them is you have a data structure that stores a bunch of elements. Each of them has some key that comes from a linearly ordered set. Something like a word sorted by alphabetical order, or a date, or a height, or something like that. And we want this data structure to support some operations. Things like range search, which should return all of the elements whose keys are between two numbers x and y. Or nearest neighbors, where given another key z, you want to find the things closest to z on either side in this data structure. So, for example, if we have such a data structure storing the following numbers, if we wanted to do a range search for 5 to 12, it should return 6, 7, and 10, the three numbers that are stored that are between 5 and 12. If we want the nearest neighbors of 3, we should return 1 and 4, since those are the closest things we have to 3 on either side. Now, if we just wanted to do that, it turns out you can do it. But in practice, you really want these data structures to be dynamic. You want it to be possible to modify them. So 2 more operations that we would like to be able to implement are insert and delete. Insert X adds a new element with key X, and delete removes an element with key X. Fine. So, for example, we have this array. If we want to insert 3 into it, we do whatever we need to. 3 is now stored in this data structure in addition to everything else. And then we can delete 10, remove that, and we've got slightly different elements that we're storing. So, just to make sure that we're on the same page, if you start with such a data structure and it's empty, and you insert 3, and then insert 8, and then insert 5, and insert 10, and then delete 8, and insert 12, and ask for the nearest neighbors of 7, what are you going to return? Well, if you figure out what the data structure stores at the end of the day, you've inserted 3, 5, 8, 10, and 12. 8 got deleted, so you've only got the other 4 left over. And you want the things closest to 7 of the remaining guys, which would be 5 and 10. So that should be the answer. Okay, so this is the data structure that we're trying to implement. What can we say about being able to do it? We've seen a bunch of data structures. Maybe one of them will work. For example, we could try implementing this by a hash table. Hash tables are good at storing and looking up elements very, very quickly. Unfortunately, they're hard to search. You can't really search for all the elements in a hash table in a given range, more or less at all. In some sense, all that a hash table lets you do is check whether or not a given element is stored there. You can't find about elements in a range. Similarly, nearest neighbors is not really a thing you can do with hash tables. But they are good at insert. Insertion into a hash table is O of 1, as is deletion. But the searching aspect doesn't work here. So maybe we need something else. Well, the next thing to try is an array. And in an array, you can do the searches, but they're a little bit slow. If you want to do a range search on an array, the best you can do is scan through the entire array, figure out which elements are in the range you want, and return those. Similarly, you have a nearest neighbors search in O of n time by scanning through the entire array, keeping track of the closest things on either side to your query, and then returning the best ones at the end. On the other hand, arrays, or at least if they're expandable arrays, are still fine with insert and delete. To insert a new element, you just add it to the next square over at the end. To delete, you can't just remove it from the array, because then you'd leave a gap. But if you take the last element and move it over to fill the gap, once again, this delete operation is O of 1 time. Perhaps more interesting than just any array, though, is a sorted array. Here we're storing all of our elements in an array, but we're going to store them in sorted order. And the critical thing about this is it allows us to do binary search. If we want to do a range search, we can do a binary search to find the left end of the range in our array, and that takes logarithmic time. And then scan through until we hit the right end of the range that we want and return everything in the middle. So the range search here is basically log n time, at least assuming the number of things we actually want to return is small. Similarly, nearest neighbors is logarithmic time. We do a binary search to find the thing that we're looking for, and we return the elements on either side of it. Unfortunately, updates to a sorted array are hard. You can't just insert a new element at the end of the array, because the array needs to remain sorted at the end, and this will generally destroy the sorted order. If you want to insert 3, it really needs to go between 1 and 4, but you can't really do that, because you can't just sort of add a new cell in the middle of an array. The only way to actually do this is you can put 3 in that plot, and then everything 4 and onwards needs to shift over 1 cell to make room. And so insertion here is O of n time, which is a lot longer than we want. Similarly, deletions are going to be hard. If you delete an element, you can't just leave a gap. You need to fill it somehow. You can't just bring an element over from one of the ends to fill the gap, because that would destroy your sorted structure. So the only way to fill the gap is to sort of take everything and shift it back over 1 in order to fill things up. And that, again, takes O of n time. The final thing to look at are linked lists. Now, here you can do a range search in O of n time. You just scan through the list and find everything in the range. Similarly, nearest neighbors are going to be O of n. Of course, linked lists insertion and deletions are very fast, O of 1, at least if you've got a doubly linked list. These things are very good. Unfortunately, our searches are slow. And even if you make this a sorted linked list, if you sort of guaranteed that everything comes in sorted order, you still can't do better than linear time for your searches, because you can't binary search a linked list, even if it's sorted, because there's no way to sort of jump to the middle of the list and sort of do comparisons. And so the moral here really is that the data structures we've seen up till this point don't work for this sort of local search data structure. And so we're going to need something new. And that's what we're going to start talking about in the next lecture. Hello, everybody. Welcome back. Today we're going to start talking about binary search trees. In particular, we're going to talk about what the binary search tree data structure is, how it's constructed, and the basic properties that need to be maintained. So last time we came up with this idea of a local search problem. We wanted a data structure to be able to solve it. And we noted that none of the data structures we had seen up till this point were sufficient to solve the problems that we wanted. But one maybe came closer than the others. Sorted arrays were okay in that you could actually do searches efficiently on them. But unfortunately, you couldn't do updates in any reasonable way. But the fact that these things allowed for efficient binary searches sort of maybe gives us a good starting point for what we're looking for. So what we should look at is we should really see this operation of binary search. What does it entail, and sort of what exactly makes it work? And so we all know how binary search works, right? So you've got your list of numbers, you pick the one in the middle, you ask, is the thing I'm looking for bigger than this or less than this? And if it's smaller, I sort of look at the middle of the first half of the array and say, is it bigger or less than that? If it's larger, I look to the second half of the array and ask, is it bigger or less than that? And I sort of keep on asking these questions, and each time it sort of narrows down my search space until I get an answer. But as you'll note, sort of associated to this sort of binary search procedure is a search tree. If you sort of consider which questions you ask, first I ask about, is it bigger than or less than 7? If it's smaller, I ask about 4. If it's bigger, I ask about 13. If I got 4 and said it was bigger than 4, I then ask about 6. And I have this sort of whole tree of possibilities. Every time I ask a question, it sort of splits into 2 different cases. And maybe the key idea here is that if you want to do a binary search, instead of doing it on the array, you could just have this search tree. You start at the top of the tree at 7, and then you head down to 4 or 13, depending on where you go, and then you keep going down until you find your answer. And so in some sense, the search tree is as good as the array. But while a sorted array, as we saw, was hard to insert into, the tree is actually a lot easier to work with in that way. And it turns out that this search tree is going to be the thing that allows us to implement these operations in a much better way. Okay, so what do we need to be the case for a search tree? Well, I mean, like all trees, it should have a root node. Each node should have 2 children. It should have a left side, which is sort of where you're going to go when you find out that things are smaller than that. And then you have a right side, which is where you go when things are bigger than that. So to be a little bit more formal, the tree is constructed out of a bunch of nodes. Each node is sort of a data type that stores a bunch of things. Importantly, it stores a key. It stores a value that you're comparing things to. It also should have a pointer to the parent node, and a pointer to the left child, and a pointer to the right child. And to be a search tree, it needs to satisfy one very critical property. If you look at the key of a node X, then, well, the stuff on the left should be where you're going if you do a comparison and find the thing that you're looking for is smaller than X. And that means that all of the keys stored on all the nodes in the left subtree of X, all the descendants of its left child, need to have a smaller key than X does. And similarly, if you found that something was bigger than X and go to the right, it had better actually be on the right. And so the things whose keys are larger than X need to be on the right subtree of X. So just to review this, I mean, we have these following 3 trees, A, B, and C. Which one of these trees satisfies the search tree property? Well, it turns out the only correct one is B. B, it works out. A has this issue that up at the top you've got this node 4, and on the left side it has everything bigger than 4, and on the right side it has everything smaller than 4. And it's supposed to be the other way around. But if you sort of switch 4's left and right sides, everything would work out there. Now, case C is a little bit more subtle. There's really only one problem here, and that's that you have this root node, which is a 5, and there's another 4, but 4 is part of 5's right subtree. And remember, everything on the right subtree of any node has to be larger than it, and this 4 is smaller. And so, other than that one mistake, things are okay there as well. Okay, so this is the structure. Next time we're going to talk about how to do basic operations on binary search trees and sort of give a little bit of pseudocode for how to do these things, and then we'll sort of have the basic start for this project. Hello everybody, welcome back. We're continuing to talk about binary search trees, and today we're going to talk about how to implement the basic operations of a binary search tree. So we're going to talk about this and talk about a few of the difficulties that show up when you're trying it. Okay, so let's start with searching. And this is sort of the key thing that you want to be able to do on a binary search tree. And the primary operation that we're going to look at for how to do this is what we're going to call find. Now, find is a function. What it takes is a key k and the root r of a tree. And what it's going to return is the node in the subtree with r as the root, whose key is equal to k. Okay, that's the goal. And the idea is pretty easy. I mean, the search tree is set up to do binary searches on. So what we're going to do is we're going to sort of start at the top of the tree. We're going to compare 6, the thing we're searching for, to 7. 6 is less than 7, and that means since everything less than 7 is in its left subtree, we should look in the left subtree. So we go left. We now compare 6 to 4, the root of this left subtree. 6 is bigger than 4. Everything bigger than 4 in the place that we're looking is going to be in 4's right subtree, so we head down that way. We now compare 6 to 6. They are equal, and so we are done with our search. And so this algorithm is actually very easy to implement recursively. If the key of r is equal to k, then we're done. We just return the node r at the root, and that's all there is to it. Otherwise, if r's key is bigger than k, we need something less than r. So the thing we're looking for should be in the left subtree, so we recursively run find on k and r's left child. On the other hand, if r is less than k, we have to look in the right subtree, so we find k in the subtree of r's right child. Okay, this works fine as long as the thing we're looking is in the tree, but what happens if we're looking for a key that isn't there? So we're trying to find 5 in this tree. We check it's less than 7, it's more than 4, it's less than 6. 6 doesn't have a left child, we have a null pointer. What do we do here? Well, in some sense, we could just return some error saying the thing you were looking for wasn't there. But we did actually find something useful. We didn't find 5 in the tree because it's not there. But we sort of figured out where 5 should have been in the tree if it were there. And so if you stop your search right before you hit the null pointer, you can actually return something useful. You find the place where k would fit in the tree. So it makes a little bit of sense to modify this find procedure so that if, say, our key is bigger than k, then instead of just checking the left pointer, we first check to see if r actually has a left child. If r's left child isn't null, we can recursively try to find k in the left subtree. But otherwise, if it is null, we'll just stop early and return r. And do something similar for the other case. And this sort of means that if we're searching for something that's not in the tree, we at least give something close to it. Okay, so that's one thing we can do. Another thing that we might want to do is sort of talk about adjacent elements. If we've got some element in the tree, we might want to find the next element. And so in particular, another function we might want, which we'll call next, it takes a node n, and it outputs the node in the same tree with the next largest key. And maybe one way to think about this is instead of searching for whatever key n has, we should search the tree for something just a tiny bit bigger than that. And now if n has a right child, this is kind of easy. The first bunch of steps lead you to the node n, and then you want to go right because it is bigger than n. But after you do that, you just keep going left because it's smaller than all of these other things that are a little bit bigger than n. And you just keep going until you hit a node where you can't go left any further. Its left pointer is null, and that's going to be the successor. Now, this doesn't work if n has no right child, because you can't go right from n. You also go looking on the left side of n doesn't work. Everything's going to be smaller there. So instead what you have to do is you have to go up the tree. You check its parent. And if its parent is smaller than n as well, you have to check the grandparent. You just keep going up until you find the first ancestor that's bigger than n. And once you have that, that will actually be the successor. So the algorithm for next involves a little bit of case analysis. If n does not have a right child, we're going to run this protocol we call right ancestor, which goes up until you take the first step right. Otherwise, we're going to return what we're going to call the left descendant of n's right child, which means you sort of go left until you can't go left anymore. Now, both of these are easy to implement recursively. For left descendant, if you don't have a left child, you're done, you return n. Otherwise, you take one step left and repeat. For right ancestor, you check to see if your parent has a larger key than you. If so, you return your parent. Otherwise, you go up a level and repeat, and just keep going until you find it. And so, putting these together, that computes next. Now, it turns out that this range search operation that we talked about before, this you're given two numbers x and y and the root of the tree, and you'd like to return a list of all the nodes whose keys are between x and y, you can implement this pretty easily using what we already have. So the idea is, well, you want to find the range search, say, everything between 5 and 12. First thing you do is you do a search for the first element in that range. In this case, it would be 6. Then you find the next element, which is 7, and the next element, which is 10. And the next element is 13, is too big, so you stop. So the implementation is pretty easy. We create a list L that's going to store everything that we find. We let n be what we get when we try to find the left endpoint x within our tree. And then while the key of this node n that we're working at is less than y, as long as the key is bigger than x, we're going to add this node to our list, and then we're going to replace n by next of n. We're just going to iterate through these nodes until they're too big, and then we return L. Okay, so that's how you do range search. And nearest neighbors, you can figure out. It's sort of a similar idea. Now, the interesting things are how do we do inserts and deletes. So for insertion, we want to be given a key k and the root r of the tree, and we'd like to add a node with key equal to k to our tree. And the basic idea is that unlike with our sorted array, with the tree, we can just have a new element and have it hanging off one of our leaves, and this works perfectly well. There is a bit of a technical problem here, though. We can't just have it hang off anywhere. I mean, 3 that we're inserting is smaller than 7, so it needs to be on the left side of 7. And furthermore, I mean, there are a whole bunch of other things that it needs to satisfy to keep the search tree property working out. But fortunately for us, this find operation, if we tried to find a node that wasn't in our tree, actually did tell us where that node should belong, more or less. So to insert, we just find our key within R, and that gives us P, and the new node that we want should be a child of P on the appropriate right or left side, depending on the comparison between things. And that's that. A little bit more difficult is delete. So here we just want a node n. We should remove it from our tree. Now there's a problem. We can't just delete the node because then, its parent doesn't have a child, its children don't have parents, it sort of breaks things apart. So we need to find some way to fill the gap. And there's a natural way to fill this gap. The point is you want to fill the gap with something nearby in the sorted order. So you try and find the next element, x, and maybe just take x and fill the gap that you created by deleting this thing. Unfortunately, there could be a problem. Now, x, it turns out, because it's the next element, it's often not going to have a left child, because the left child would be sort of even closer. But it might have a right child. And if it does have this right child, then by moving x out of the way, its right child is now going to be orphaned. It's not going to have a proper parent. So in addition to moving x to fill that gap, you have to move y up to fill the gap that you made by moving x out of the way. But once you do that, it's actually perfectly good. You've done a reasonable rearrangement of your search tree and removed the nodes you wanted. So the implementation takes a little bit of work. First, you check to see if n has a right child. If its right child is null, then it turns out we're not in this other case, but you can just remove n, and you need to promote n's left child if it has one. So n's left child should now become the parent of n's parent, sorry, the child of n's parent instead of the other way around. Otherwise, we're going to let x be next of n, and note that x does not have a left child. And then we're going to replace n by x and promote x's right child to sort of fill the gap that we made by moving x out of the way. But this all works. Just to review it, so if we have the following tree and are deleting the highlighted node, which of the following three trees do we end up with? Well, the answer here is C. The point is that we deleted 1, so we want to replace it with the next element, which is 2. So we took 2 and put it to the place where 1 was. Now 2's child, 4, needs to be promoted. So 4 now becomes the new child of 6, and everything works out nicely in this tree. Okay, so that's how you implement some basic operations for binary search trees. Next time we're going to talk about the runtime of these operations, which are going to lead us to some interesting ideas about the balance of these trees. Hello everybody, welcome back. We're continuing to talk about binary search trees, and today we're going to talk about balance. In particular, we're actually going to look at sort of the basic runtime of these operations that we talked about in the last lecture. And from that, we're going to notice that they'll sometimes be a little bit slow. And to combat this, we want to make sure that our trees are balanced. And, well, doing that's a bit tough, and we're going to talk a little bit about how we're going to do this with rotations. Okay, so first off, we've got this great operation. It can do local searches, but how long do these operations take? And maybe a key example is the find operation. So we'd like to find 5 in the following tree. We compare it to 7, and it's less than 7, and then it's bigger than 2, and then it's bigger than 4, and it's less than 6, and it's equal to 5, and we found it. And you'll note that the amount of work that we did, we sort of had to traverse all the way down the tree from the root to the node that we're searching for, and we had to do a constant amount of work at every level. So the number of operations that we had to perform was O of the depth of the tree. Now, just to sort of make sure we get this, so if we have the following tree, we could be searching for different nodes, A, B, C, or D. Which ones are faster to search for than which others? Well, A is the fastest, it's up at the root. Then D has depth only 3, B has depth 4, and C has depth 5. And so A is faster than D, is faster than B, is faster than C, probably. So the runtime is the depth of the node that you're looking for. But it's unfortunate, the depth can actually be pretty bad. In this example, we have only 10 nodes in the tree, but this 4 at the bottom has depth 6. In fact, if you think about it, things could be even worse. A tree on n nodes could have depth n if the nodes are just sort of strung out in some long chain. And so this is maybe sort of a problem, that maybe our searches only work in O of n time. We're not any better than any of these other data structures that didn't really work. On the other hand, even though depth can be very bad, it can also be much smaller. This example has the same 10 nodes in it, but the maximum depth is only 4. And so by rearranging your tree, maybe you can make the depth a lot smaller. And in particular, what you realize is, well, in binary search, the questions that we asked, in order for it to be efficient, we wanted to guess the thing in the middle, because then no matter which answer we got, we cut our search space in 2. And so what this means for a binary search tree is, at any node, you're asking that one question. You want the things on the left and the things on the right. Those two subtrees should have approximately the same size. And this is what we mean by balance. And if you're balanced, suppose that you're perfectly balanced, everything's exactly the same size, then this is really good for us. Because it means that each subtree has half the size of sort of the subtree of its parent. And that means after you go down logarithmically many levels, the subtrees have size 1, and you're just done. And so if your tree is well balanced, operations should run in O of log n time, which is really what we want. But there's a problem with this, that if you make insertions, they can destroy your balance properties. We start with this tree, it's perfectly well balanced, it just has one node, I guess. But we insert 2, and then we insert 3, and then we insert 5, and then we insert 4. And you'll note that suddenly we've got a very, very unbalanced tree. But all we did were updates. So somehow we need a way to get around this. We need a way to do updates without unbalancing the tree. And the basic idea for how we're going to do this is we're going to want to have some mechanism by which we can rearrange the trees in order to maintain balance. And there's one problem with this, which is that however we rearrange the tree, we have to maintain the sorting property. We have to make sure that it's still sorted correctly, or none of our other operations will work. And, well, there's a key way to do this, and this is what's known as a rotation. The idea is you've got two nodes, x and y, where say x is y's parent, and there's a way to switch them so that instead y is x's parent. And the sort of subtrees, A, B, and C, that hang off of x and y, you need to rearrange them a little bit to keep everything still sorted. But there is this sort of very local rearrangement. You can go back and forth, and it keeps the sorting structure working, and it rearranges the tree in some hopefully useful way. So just to be clear about how this works, it takes a little bit of bookkeeping, but that's about it. You let P be the parent of X, Y be its left child, B be its right child. And then what we're going to do is we just need to reassign some pointers. P is the new parent of Y, and Y is its child. Y is the new parent of X, and X is its right child. X is the new parent of B, and B is X's new left child. And once you sort of rearrange all those pointers, then everything actually works. This is a nice constant time operation, and it does some useful rearrangement. So what we really need to do, though, is we need to have a way to sort of use these operations to actually keep our tree balanced. And we're going to start talking about how to do that next time when we discuss AVL trees. Hello everybody, welcome back. We're still talking about binary search trees, but today we're going to talk about AVL trees. And AVL trees are sort of a specific way of maintaining balance in your binary search tree, and we're just going to talk about sort of the basic idea. Next lecture, we're going to talk about how to actually implement them. But, okay, what's the idea? We learned last lecture that in order for our search operations to be fast, we need to maintain balance of the tree. But before we can do that, we first need a way to measure the balance of the tree so that we can know if we're unbalanced and know how to fix it. And a natural way to do this is by what's called the height of a node. So if you have a node in a tree, its height is the maximum length of a path from that node to a leaf of your tree. Fair enough. So, for example, if we have the following tree, what's the height of the highlighted node? Well, this node has height 6. The following path of length 6 leads down from this node, and there's turns out to be nothing longer. Okay. So we can define height recursively in a very easy way. If you have a leaf, its height is 1 because you're just there and you can't go any further. Otherwise, well, the longest path downwards you can have, it's either through the longest path on your left side or the longest path on your right side. So you want to take the maximum of the height of your left child and the height of your right child. And then you need to add 1 to that because n sort of gets added to this path. Okay, that's fine. Now, in order to actually make use of this height, we actually are going to want to add a new field to our nodes. So the nodes that made up our tree previously stored a key and a pointer to the parent and the left child and the right child. And now they also need to store another piece of data, the height of the node. And note that we're actually going to have to do some work, and we'll talk a little bit about how to do this later, to ensure that this height field is actually kept up to date. We can't just store it as a number and leave it there forever. If we rearrange the tree, we might need to change this height. In any case, back to balance. Height is a very rough measure of the size of a subtree. For things to be balanced, we want the size of the two subtrees of the left and right children of any given node to be roughly the same. And so there's an obvious way to do this. We'd like to force the heights of these children to be roughly the same. So the AVL property is the following. For all nodes n in our tree, we would like it to be the case that the difference between the height of the left child and the height of the right child is at most 1. And we claim that if you can maintain this property for all nodes in your tree, this actually ensures that your tree is reasonably well balanced. Okay, and so really what we'd like to know is that if you have the AVL property on all nodes, then the total height of the tree should be logarithmic. It should be O of log n. So basically what we want to say is that if you have an AVL tree and it doesn't have too many nodes, then the height is not too big. But it turns out that the sort of easier way to get at this is to turn this on its head. We want to show instead that if you have an AVL tree and the height isn't too big, then you can't have too many nodes. And this we can do. So we're going to prove the following theorem. Suppose that you have an AVL tree, or tree satisfying the AVL property, and n is a node of this tree with height h. Then the claim is that the subtree of n has to have size at least the Fibonacci number f sub h. And so just to review, we talked about Fibonacci numbers way back in the introductory unit for this, or for the previous course in this sequence. But they're just the sequence of numbers. The 0th one is 0, the first is 1, and from thereafter, each Fibonacci number is the sum of the previous 2. Now, these were nice. They sort of are a nice predictable sequence. They grow pretty fast. The nth Fibonacci number is at least 2 to the n over 2 for all n at least 6. Okay, so let's look at the proof. We're going to do this by induction on the height of our node. If the node we're looking at has height 1, it's a leaf, and its subtree has 1 node, which is the first Fibonacci number. Great. Next, we need an inductive hypothesis. If you've got some node of height h, by sort of definition of the height, at least one of your 2 children need to have height h minus 1. Then, by the AVL property, your other child needs to have height at least h minus 2. So, by the inductive hypothesis, the total number of nodes in this tree is at least the sum of the h minus 1st Fibonacci number plus the h minus 2nd Fibonacci number, which equals the h Fibonacci number. And so that completes the proof. So what does this mean? It means that if a node in our tree has height h, the subtree of that node has height at least 2 to the h over 2. But if our tree only has n nodes, 2 to the h over 2 can't be more than n. So the height can't be more than 2 log base 2 of n, which is O of log n. And so the conclusion is that if we can maintain the AVL property, you can perform all of your find and operations and such in O of log n time. And so next lecture, we're going to talk about how to maintain this property, but this is the key idea. If we can maintain this property, we have a balanced tree and things should be fast. So I'll see you next time as we discuss how to ensure that this happens. Hello everybody, welcome back. We're continuing to talk about AVL trees, and in particular today we're going to talk about how to implement an AVL tree, how to make sure that you can maintain the AVL property even as you update the tree. So let's see where we were before. So an AVL tree is a tree that has the property that any node in the tree, its 2 children, have heights that differ by at most 1. Now, we saw last time that if you have this property, you've got at most logarithmic depth, which means that all of your search operations are very fast. The problem, though, is when we try to do updates. The point is that if we add a new node, say where this blue node is located here, when we add this new node, it will change the heights of a bunch of other nodes in the tree. And when we do this, it could cause, even though we were satisfying the AVL property before, it might no longer hold after we perform this update. And so we're going to need to find some way to correct this problem, to do some sort of rebalancing of the tree to make sure that this stays balanced. Now, one thing that is going in our favor is that when we make this update, it actually doesn't affect the heights of most of the nodes in the tree. The only nodes whose heights are affected are nodes that can sort of see the new node that we inserted. And so only nodes on the sort of search path, the insertion path for this new node, are actually affected. And so only those are the places where we might need to rebalance. Now, just to make sure that we're all on the same page here, suppose that we have the following AVL tree, and we want to insert a new node at one of A, B, C, or D. Now, which of these insertions will force us to have to rebalance in order to satisfy the AVL property? It turns out that D is the only one that matters. If you insert at D, then it adjusts the heights in the following way, and yes, there are a couple of places where the AVL property is now violated. The other three, you can compute it all out and determine that you don't need to make any such changes. Okay, so let's start on insertions. So what we're going to need is we're going to need a new insertion algorithm that, in addition to adding a new node to the tree, also does some rebalancing to guarantee that the AVL property is maintained at the end of the day. Now, the basic idea for this is pretty simple. Firstly, we're going to insert our node into the tree as we would before. This, of course, can violate the AVL property. So what we're then going to do is we're going to find that node in the tree, and then we're going to run some rebalance protocol on that node. And what rebalance is supposed to do is it rebalances things at that node and then moves up to the parent and maybe does some rebalancing there and then the grandparent. And it has to work its way all the way up the tree because all of the ancestors of this new node might be unbalanced. And so we need to sort of maybe do some work at all of them. But one thing to note is that if we have the AVL property, we only have to deal with things along this insertion path, which is at most O of log n depth, and so this should hopefully not take too long. Okay, so how do we do this rebalancing? Well, if you have a node and the height of its left child and the height of its right child differ by at most 1, you're actually fine. There's nothing more that you need to do. They're already satisfying the AVL property. Of course, if the heights differ by more than 1, you need to do something. If the left child is much heavier than the right child, somehow you need to change things around. Probably you want to sort of move the left child further up in the tree because its subtree is heavier, so it should be higher up relative to the right side. Now, one thing that we'll note that we'll take advantage of throughout this is that when our tree is unbalanced like this, it's actually never unbalanced by more than 2. And this means that we don't have to deal with, two guys where the heights of the children are n and n plus 5. We might have to deal with n and n plus 2, but that's not so bad. Okay, how do we rebalance? Well, here's the code. The first thing that we need to do is we need to store a pointer to the parent of our node. Because after we rebalance at n, we're then going to want to rebalance at its parent. Fine. The next thing that we do is we say, well, if the left child of n has height that's more than 1 bigger than the height of the right child, we need to rebalance things rightwards in order to fix that. If the height of the right child is more than 1 more than the height of the left child, we need to rebalance leftwards. After we do that, we then need to look at the height of n, and we might need to readjust it. Because we might have modified things below it in the tree, we might need to change the height of n, that's stored height of n, because it might have changed. And then finally, if this pointer to the parent is not null, if the node we started with wasn't the root, we then need to rebalance recursively at the parent. So that's what we do. This adjust height protocol is actually pretty simple. All you do is you set the field for the height of node n to be what it should be. 1 plus the maximum of the height of the left child and the height of the right child. This just makes sure that if we were storing the wrong number, we adjust things so that we now have the correct number. The bigger question is, how do we actually do this rebalancing step? And the basic idea is that if our left child is too heavy, we need to bring it higher up in the tree, so we should rotate our node to the right. And in a lot of cases this works, but there's one where it doesn't. So suppose our node's B, it's got left child A and right child C. If A's height is largely due to its right child, then the thing that happens when we rotate to the right, what happens is the right child of A moves to the other side of the tree and becomes the left child of B. And this means that when we perform this rotation, while our old tree was too heavy on the left side, the new tree becomes too heavy on the right side, because this sort of problematic grandchild just switched sides of the tree. And so in this case, we actually need to do something a little bit more complicated. So here we note, though, that in this case, there's this sort of problematic grandchild. And the basic point is the problematic grandchild was too far down in the tree. So to fix this, we just have to rotate it upwards. So the first thing we're going to do here is we're going to take this problematic grandchild, rotate it upwards, and then we're going to rotate our root node to the right. And it turns out that once we do these two operations, the thing you end up with is actually good. It does satisfy the AVL property. So the code for rebalancing right is as follows. First, we let M be the left child of the node N. Then what we're going to do is, if the height of M's right child is strictly bigger than the height of M's left child, we need to rotate M to the left. That's this sort of more complicated case. Then, whether or not we did that, we rotate N to the right. And then, for any of the nodes where we change the height of that node, we might have to run adjust height on that node just to make sure that the height field on all of the nodes in our tree stays up to date. But once we do this, we actually have successfully rebalanced the tree at that node. We then just need to do the same at the parent and grandparent, and so on. Okay, so that's insertion. It turns out that deletions also need to be mixed up with some rebalancing. So if you recall how a delete worked, well, we found the node we wanted to delete, and we couldn't just remove it from the tree, so we found its successor. Now, its successor didn't have a left child, but it might have a right child. It can't be too tall because of the AVL property. But then what you do is you take this successor, you use it to replace the node you're deleting, and its right child replaces it. Now, the problem here is that if you look at this successor node, the one that went up and replaced the node that we deleted, the height of the node at that location has decreased by 1. Either it went from being a single node to not being there anymore, or it went from being a node of height 2 as pictured to a node of height 1. And this can cause the parent of that node to become unbalanced. And so, once again, we're going to need to do some rebalancing steps in order to fix this problem. So the new code for delete is actually quite simple. The first thing that we do is we delete N as we would have before. We then let M be the parent of the old parent of the node that replaced N in the tree. And then we need to rebalance at M, and again, all the way up the tree. But this works. And the thing to note is that all of these operations are O of log n time. Our rebalance operations do a constant amount of work at each level. There are logarithmically many levels in this AVL tree. And so we finally have a fully functional binary search tree that can do all of these find and insertion and deletion operations all in O of log n time per operation. And this is great. So next lecture, we're going to talk about a couple of other operations that you can perform on AVL trees, and then we'll get into talking about some applications. So that's all for this lecture. I'll see you next time. Hello, everybody. Welcome back. Last time we talked about AVL trees and showed that they can perform your basic binary search tree operations, but now we're going to introduce a couple of new operations and talk about how to implement them. So another useful feature of binary search trees is that in addition to being able to search them, there's also a bunch of sort of interesting ways that you can recombine them. And so we're going to discuss here two of these operations. One of them is merge, which takes two binary search trees and combines them into a single one. And the other one is split, which takes one binary search tree and breaks it into two. So let's start with merge. And the idea is, in general, if you have two sorted lists and want to combine them into sort of a single sorted list, this is actually pretty slow. It's going to take O of n time, because you sort of need to figure out how the lists interleave with each other. This is the thing you do in merge sort. However, there is a case where you can merge them a lot faster, and that's in the case where they're separated from each other, where they're sort of one's on one side, one's on the other side. And so this is the case that merge is going to work with. So you're given two trees, R1 and R2, or the roots of these trees, and they're going to need to have the property that all the keys in R1's tree are smaller than all of the keys in R2's tree. And if we're given this, we should then return the root of a new tree that has all of the elements of both of the trees. So just to review this condition that we have, of the three trees below, which of them can be properly merged with the one above? The answer is that only A can, because all of the elements of A are less than all of the elements of the guy above. B has this problem that it's got a 9, and 9 is between 8 and 10, so it can't really be separated from them. And C has the problem that it has both 2, which is smaller than everything above, and 12, which is bigger than everything above. So A is the only guy that actually works here. Okay, so how do you do this merge operation? Well, there's actually a case where it's super easy to merge trees, and that's if, instead of just being given the 2 trees, we also have an extra node that we can use as the root. Because then you just have the node up top, you have the guys in R1, the small guys on the left of it, the guys in R2, the big guys on the right of it. That's your tree. So the implementation, we'll call this function merge with root, is you let R1 be the left child of T, R2 be the right child of T, let T be the parents of these two. If you need to do things involving storing heights, you adjust those as appropriate, and then you return T. This takes O of 1 time. Very simple. The problem is, well, what if we're not given this extra node? Then there's actually a pretty simple solution. You find the largest element of, say, the left subtree, you remove that, and then turn it into the root of the new guy. And that works. So now if we want to merge R1 and R2, you're going to find the largest element of R1, call that T. You're going to delete T from its subtree, and then you're going to merge with root. And that works. The runtime's a little bit worse. You have to spend O of the height time to find this node T. But other than that, it's pretty efficient. So just to review, we've got this tree. We find the biggest element of the left tree, 8. We then delete it, and then we merge with root. That's all there is to it. Now, if we didn't care about balance, that would be all we'd have to say about this operation. Unfortunately, this merge operation doesn't preserve balance properties. And the problem is that, well, the 2 trees, you didn't really touch them very much, so they stay balanced. But when you stick them both together under this same root, well, if one tree is much, much bigger than the other, suddenly the root is very, very unbalanced. And this is a problem. So we need a way to fix this. And there's actually a not very difficult way to do that. The idea is that we can't merge the, say, left subtree with the right subtree because the left one is way too big. So what we're going to do is not merge the whole guy with the whole guy here. We're going to have to find some node of approximately the same height as this guy on the right so that we can merge that with him. And so what we're going to do is we're going to sort of climb down to the sort of right edge of the bigger tree until we find a subtree of the right height that we can merge with our guy on the other side. Okay, so how do we implement this? AVL tree merge with root. What we're going to do is if the heights of the 2 trees differ by at most 1, we can just merge with root as before. We then figure out what the height of T needs to be and return it. That's simple. Otherwise, though, what happens if, say, R1's height is bigger than R2's height? Well, what we want to do is we want to step down to, instead of merging R1 with R2, we merge R1's left child or right child with R2. So we use merge with root to merge the right child with R2 at this T, and we get some new tree with root R prime. R prime, we set that to be the right child of R1, and similarly set R1 to be the parent. And then we need to rebalance this at R1 because things might be off by a little bit, but it turns out not more than about 1. We know how to deal with that with our old rebalance operation. And then we return the root of the tree. If, on the other hand, R1's height is smaller than R2's height, we sort of do the same operation, but on the opposite side. Okay, so let's analyze this. Every step we take down the side of the tree decreases the height difference by either 1 or 2. So we're just going to keep decreasing the height difference until we're off by at most 1. Then we merge and we sort of have to go back up the chain. But the amount of time that this takes isn't the depth of the tree. It's sort of the number of steps we need to take down the side. And that's approximately the difference in the 2 heights. And this will actually be important in a bit. Okay, so that was the merge operation. Next, we're going to talk about sort of the opposite operation, split. Merge takes two trees and turns them into one. Split breaks one tree into two. What you do is you pick an element, say 6, and then you've got the tree consisting of all the elements less than 6, and then another one from all the elements bigger than 6. So split should take the root of a tree and a key x, and the output should be two different trees. One with all the elements less than x in your tree, and one with all the elements bigger than x. Okay. Now, the idea is actually not so hard. What we're going to do is we're going to search for x, and then the search path, well, it's got a few nodes on the path, and then it has a bunch of trees hanging off to the left of the path. These things are all going to be smaller than x. And it's going to have a bunch of trees hanging off to the right that are all going to be bigger than x. And so all we have to do is take these trees that are smaller than x, merge them all together, take these things bigger than x, merge them all together, and then we have two trees. So let's see how this works. So we're going to do this recursively. We're going to split at r at this point x. If our root is null, if we just have the null tree, we just return a pair of null vectors. Whatever. Next, if x is less than the key at the root, what that means is that everything on the right is bigger than x. That's sort of all on the right, but the left side of the root, we need to split that in two. So we're going to recursively run split on r.left, and that gives us two trees, r1 and r2. Now, r1 is actually everything in the whole tree that's smaller than x. That half is done. But r2 needs to be combined with the whole right subtree of our original tree. So we run merge with root on r2 and r.right, with r as the root. Fortunately, we have this extra node to use as the root. And this gives us an r3, and we can return r1 and r3 as our splitting. If x is bigger than the key, we do the same thing on the opposite side. Hopefully you can figure that out. Okay, so the first thing to note is that if we, instead of just doing a merge with root, we used AVL merge with root, this ensures that the two trees we produce are both balanced, which is good. Also, if you look at the runtime of this algorithm, well, the runtime of AVL merge with root is O of the difference in the two heights. So we have to look at the difference between the biggest height and the next biggest, and the next biggest, and the one after that, and so on. This sum actually telescopes. And the total runtime is O of the maximum height of one of these trees we're trying to merge, which is just O of log n. And so we've got these two operations. Merge combines trees, split breaks them in two, and both operations can be implemented in O of log n time using AVL trees. So that's these two operations. Next time we're going to talk about a couple of applications. One of them is going to sort of talk about a way that we can make use of these split and merge in an interesting way. Hello everybody, welcome back. Today we're going to talk more about binary search trees, and in particular we're going to give a couple of applications to computing order statistics and then a sort of additional use of binary search trees to sort of store sorted lists. Okay, so there are some questions that you might want to ask. You've got a bunch of elements that are stored in this binary search tree data structure. They're sort of sorted by some ordering. Things we might want to do. We might want to find the 7th largest element. Or maybe we want the median element or the 25th percentile element. Now, these are all instances of an order statistic problem. We would like to be able to, given the root of a tree T and a number K, we should be able to return the kth smallest element stored in the tree T. So the basic idea is that this is sort of like a search problem. We sort of should treat it like one. But to do that, we need to know which subtree to search in. So, I mean, is the kth smallest element in the left subtree? Well, the left subtree does store a bunch of the smallest elements, but the real question is, does it store k of them? If it stores at least k, kth smallest element should be in there, otherwise it won't be. So the thing that we need to know is how many elements are in the left subtree. And so we really need a tree where we can easily tell how many elements are in each subtree. Well, there's an easy fix for that. You just add that as a new field. So n.size should return the number of elements in the subtree of n. It's a new field, it stores that. It should satisfy the property that the size of n is the size of the left subtree and the size of the right subtree plus 1, all added together, where if you have null pointers, these have size 0. Okay. Now, we have to be a little bit careful. Just like with the height, we couldn't just define this field and hope that it always has the right value. You actually need to do some work to make sure this stays correct. For example, when you perform a rotation, the sizes of various subtrees will change. Fortunately, only the sort of 2 nodes that you moved around will actually have their subtree sizes change, but you do need to deal with those. And so we're going to have an operation called recompute size, which just recomputes the size as the sum of its size of its left child and the size of its right child and 1. And then to do a rotation, we should do this as we did before, but then we need to recompute the sizes of the 2 nodes that we rotated. And you need to make sure to do this in the right order, actually, because the size of the parent depends on the size of the child. So you need to recompute the child first. Okay, but once you've got all the sizes of nodes stored, it's actually not hard to compute order statistics. So to compute the kth smallest element in your tree R, what you do is we let S be the size of the left subtree, the r.left.size. Now, if k is equal to s plus 1, there are exactly s things smaller than the root. The root is the s plus first smallest element, so we return r. Otherwise, if k is less than s plus 1, the kth smallest element is in the left subtree, so we recursively return the kth smallest element of r.left subtree. On the other hand, if k is bigger than s plus 1, we need to look in the right subtree. Now, unfortunately, it's no longer the kth smallest element of the right subtree, because there were already s plus 1 smaller elements. So what we actually need to compute is the k minus s minus first smallest element in the right subtree. But with this minor adjustment, this algorithm works. The runtime is O of the height of the node that you search for. It's basically just a binary search, but we need to use these sizes of trees in order to figure out which side to look at instead of, comparing the actual keys. But this works perfectly well. Now, here's a puzzle that I'm going to give you. We're not going to do homework on this, but it's something you should think about. What we've shown you how to do is, given a rank, k, we can find the kth smallest node. How would you do the opposite? Given a node, figure out how many nodes in the tree are smaller than it. You can do it using this kind of thing, but it takes a little bit of thinking. Okay, that was one problem. We're going to talk about one more application of binary search trees. And this problem is a little bit weird, but it's going to introduce some very important ideas. So we have an array of squares. They're each colored black or white. And we want to be able to perform this flip operation, which what it does is it sort of points at some square x, and every square after that index, it flips them from black to white and white to black. So in the array pictured, we're flipping the last 4 guys, and they go from being white, white, black, white to being black, black, white, black. Okay. So formally, we sort of want a data structure that maintains this. You can create an array of size n. You can ask for the color of the nth square. Or you can run this flip operation, which flips the color of all the squares after index x. Okay, those are the things we want to support. Now, we could do this by just having an array and storing all the colors. The problem is that the flip would be pretty slow, because if you want to flip all the things with index bigger than x, then there's no good way to do this. You just have to sort of go through every square of index bigger than x and flip them, and that could take linear time. So it turns out that there's a nice way to use binary search trees to solve this. And this requires sort of a slightly different way of thinking about binary search trees. Up till now, we thought of a search tree as sort of having a bunch of elements that are stored, and they allow you to do searches on them. And so somehow you're given the keys, and the search tree allows you to find them. But there's another way to do it, and maybe a good way to illustrate it is by looking at the logo for our course. So this is a binary search tree. Every node has a letter in it. But you'll note that this isn't sorted in terms of these letters. For example, O is the left child of I, but O comes after I in alphabetical order. These things aren't sorted alphabetically. On the other hand, you'll note that the binary search tree structure actually does tell you what order these letters are supposed to be going in. I mean, the smallest thing here should be A, because it's the left child of the left child of the left child of the left child. Then L is the next smallest, then G, then O, R, I, then T, H, M, S. And so it tells us what order these letters are supposed to be in. They spell algorithms. And that's the basic idea, that you can use a tree to store some sort of sorted list of things in a convenient way. So, for example, we have the following tree. There are like no actual keys stored on them. But of this A, B, C, D, and E, one of these is the fifth smallest element in the tree. Which one is it? Well, it's D. I mean, you sort of count the smallest is on the left, then B, then this other thing, and D is the fifth smallest. Okay. So what's the point? How are we going to use this to do our flip arrays? What we're going to do is, instead of storing the sequence of black and white cells as an array, we're going to store it as a list. And in this list, we're going to have a bunch of nodes that are going to be colored black or white. Fine. Actually, there's a bit of a clever thing. We're actually going to want two trees. One with the normal colors and one with the opposite colors. And the reason for this is that when we want to do flips, we want to be able to replace things with their opposite colors. So it helps to have everything opposited already stored somewhere. But now comes the really clever bit. If we want to do this flip operation, say we want to take the last three elements of our tree and flip all of their colors. Well, this second tree, this dual tree, the last three elements of that tree have the opposite colors. So all that we need to do is swap the last three elements of the tree on the left with the last three elements of the tree on the right, and we have effectively swapped those colors. And what's even better is that using these merge and split operations from last time, we can actually do this. So let's see how this is implemented. Firstly, to create this thing, we just build two trees, where T1, all of the things are colored white, and T2, they're all colored black. Great. To find the color of the nth node, you just find the nth node within T1 and return its color. Great. The flip operation is the interesting bit. If we want to flip at x, what you do is you split T1 at x into two halves, and you split T2 at x, and then you merge them back together. But you merge the left half of T1 with the right half of T2, and you merge the left half of T2 with the right half of T1. And that effectively did move around the sort of last n bits, and it works. And so, as the moral, like, trees can actually be used for more than just sort of performing searches on things. We can use them to store these sorted lists, and merge and split then become very interesting operations in that they can allow us to recombine these lists in useful ways. Okay, so that's all for these applications. Next time we're going to we're going to have an optional lecture. It's going to talk about an alternative way to implement many of these useful binary search tree operations. So please come to that. It'll be interesting, but it's not really required. It's sort of another way to do some of this stuff. But I hope I'll see you then. Hello everybody, welcome back. Today we're going to talk about splay trees. So the basic idea is that we spent a lot of time talking about AVL trees and sort of as a way to keep your binary search trees balanced and thus keep everything efficient. But AVL trees are not the only way to do this. There are a bunch of binary search tree data structures. There are red-black trees, and there are treeps, and there are a bunch more. But today we're going to talk about splay trees. And these are another thing. They're actually reasonably easy to implement, and they have a lot of very nice properties. And maybe to motivate this, let's talk about non-uniform input sequences. So if you're doing searches for sort of a bunch of elements in random order, then it turns out that O of log n time per operation is actually the best that you could possibly do with a binary search tree structure. On the other hand, it could be the case that if you say some items are being searched for more frequently than others, in this case, you can actually hope to do better than log n time per operation by putting the frequent queries near the root. For example, in the following tree, it's actually not a very well-balanced tree for its size. It's got some pretty deep nodes. But the 3 highlighted nodes are all very close to the root. And if you somehow knew that these 3 nodes were being the ones that you were asking for 90% of the time, this might actually be a much better structure to use than a balanced one. So how do we ensure that the frequently queried nodes stay near the root? Well, one thing you could do is if you sort of knew how often you were going to ask for various things, you could specifically rearrange the tree to make that work. But if you don't know what the frequent accesses are, you need something a little bit more adaptive. And there's a cool idea for how to do this, and that's that whenever you query a node, you bring it up to the root of the tree. And that means that if you query a node a lot of the time, since you keep bringing it up to the root, hopefully it stays somewhere near the top. And that's the idea behind splay trees. Now, the simple way to try and implement this is every time you query a node, just rotate it upwards over and over again until it hits the root. And unfortunately, this doesn't actually work for us. It could be the case that you started with a very unbalanced tree, and then you perform these rotations and you have an almost as unbalanced tree at the end of the day, and you could just keep going back and forth, and your tree stays very unbalanced, and it's a mess. So we need to modify this idea, and we actually only need to modify it a little bit. So what you do is when you're trying to bring this guy to the top, you look not just at his parent, but also his grandparent. And there are a couple of cases. If the parent and grandparent are sort of on the same side, this is what's called the zig-zig case. You rearrange this so that you now have the node and its parent as the child and its grandparent as the grandchild. The other case is the zigzag case, where the parent and grandparent are on opposite sides of the node. Then you bring the node up where the parent and grandparent are now its 2 children. Finally, there's one more case where for just one step below the root, we don't have a grandparent. This is called the zig case, and there you just do a rotation. So the idea of using these to bring our guy to the top, this is an operation called splay. And to splay n, what you do is the following. Firstly, you determine which case you're in, zig-zig or zigzag or zig, and you apply the appropriate local rearrangement of the tree. Then, if you're not the root, if your parent still is not the null pointer, you splay again. And you just keep going until you hit the root of the tree. Fair enough. So just to make sure we're still on the same page, we have the following tree. We've got this highlighted node 4 at the bottom. We'd like to splay that to the root. What is the resulting tree after we do this splay? So the answer is A. So the point is, first at the bottom, we're in the zig-zig case. Its parent and grandparent are both sort of on the same side of it. So we bring 4 up with 3 and then 2 as its child and grandchild. Next, we're in the zigzag case. And so we bring 4 to the root, 1 and 5 become its children, and this 3 needs to hang off 1 in that particular location, and so that's where it goes. So that's all that it does. Okay, so now we need to analyze this. And there is a bit of a problem. In an AVL tree, every operation is O of log n. But in a splay tree, sometimes the operations are slow. Sometimes you have a very unbalanced tree, and then going all the way down to the bottom node and splaying it all the way up could take O of however deep it is. And this is slow potentially. So in order to have a good runtime analysis, we actually need to make sure that the analysis is amortized. And in order to do this, we need to pick a correct potential function. Now, it takes a while to figure out what the right potential should be, and the following is one that works pretty well. So you let the rank of a node be the log of the size of its subtree. And from this, you define a potential function, phi, to be just the sum over all nodes in the tree of the rank. And it turns out this thing's kind of big when your tree is unbalanced and small when your tree is balanced, so it's a pretty good potential. So the thing that we now need to do is we need to say, if I perform my splay operation, what's the change in my potential function? So let's start off with a zig case. So I do this rearrangement. I'll note that the ranks of all the nodes, except for the 2 that I touched here, stayed the same. And so the change in my potential is just the sum of the new rank of n and the new rank of p minus the old rank of n and the old rank of p. And I can do a little bit of pretty easy manipulation to see that this is at most the difference between the new rank of n and the old rank of n. Great. What next? Next, we have the zigzag case. And here, things are a bit more complicated. But using the same sorts of ideas and a little bit of trickery about logarithms and such, you can show that the change in the potential is at most 3 times the difference between the new rank of n and the old rank of n, minus 2. The zigzag case, you can do something similar. You get a similar bound. And so putting this all together, if we do an entire splay operation, what's the change in our potential? Well, it's going to be something like 3 times the final rank of n, minus the rank of n one step before that, minus 2, plus 3 times the rank of n one step before the end, minus the rank of n 2 steps before the end, minus 2, and so on and so forth. Now, this sum telescopes. It's at most 3 times the rank of n at the beginning of the day, minus the rank of n at the start of the day, minus 2 times the depth, or something like that. Now, the rank of n at the end of the day is at most log n. So this is O of log n minus the depth, and the depth is proportional to the work that you did. So O of log n minus the depth, the work that you're doing. So the amortized cost of doing a splay, or doing a find and then a splay, is the change in potential plus the work, which is O of log n. And so the amortized time of a splay is actually logarithmic, which is pretty good. Okay, so now let's look at the other operations of a splay tree. And it turns out once you have splay, everything's pretty easy. To find, what we're going to do is we're first going to find the node as we did before. Then we're going to splay it to the root and return it. And the cost of the find might be big if the depth is big, but sort of if the depth is big, our splay causes a big decrease in the potential, and this is O of log n. Insert is very easy as well. We first do our insert, then we find the node we inserted and splay it to the top. And the point is, you need to do the splays because the insert could be very, very deep and involve doing a lot of work. And if that's the case, you need to run a splay in order to simplify things in the future. To do delete, there's actually something a little bit clever that you can do. What you're going to do is you're going to splay both n and its successor, bringing them both to the top of the tree. And when you do this, n's the root, and it's got its successor, and its successor is right next to it, so it can't have anything on its left. And then you can just delete n in a very natural way, and it works out quite beautifully. So here what we're going to do is you're going to splay the next element of n to the root, and then splay n, and then delete n. And it all works. Split is also very easy on splay trees. What you're going to do is you're going to split at x. You first find the node close to x. You then splay that to the root. And now at the root, you've got n, and then to the left, you have things smaller than x, and to the right, you have things bigger than x. And all you need to do is split the tree into 2 pieces. And it's that easy. For splay tree merge, it turns out you can do basically the same thing that you do with normal merge. You find the biggest element of, say, the small tree. You splay it to the top. And now you just sort of add the big tree on as a right subtree of that thing. Now, this preserves the sorted order. The total cost is reasonable. You have to be a little bit careful with what does merging these 2 trees together do to your potential function. But it turns out you're okay there as well. So, in summary, a splay tree can perform all the basic tree operations in amortized O of log n time per operation. But it actually turns out that it's a little bit better than this. If you did random updates, as we said, you can't do better than O of log n. But if your updates have structure, you can hope that maybe you can do better. And in fact, a splay tree often does. So here's one thing. Suppose that you assigned weights to the nodes in any way you like, such that the sum of the weights is equal to 1. Then the cost of accessing a node n, it turns out, is amortized O of log of 1 over the weight of n. Now, if all the weights were the same, this is just O of log n, which is what we saw before. But if some nodes are being accessed much more frequently than others, you could think of those nodes as having a higher weight, and that would make those accesses cheaper. Now, the other great thing about this bound is that you don't actually need to pick the weights. Any weights you could have picked, the splay tree attains this runtime, which is pretty nice. Another thing, suppose that you're doing a bunch of accesses to your tree, and you don't do random accesses, but you sort of access things that are near to things that you accessed recently. So you access 1, then 3, then 4, then 7, then 6, and so on. You sort of meander around a little bit. It turns out that you can show that with splay trees, the cost of accessing a node, amortized, is O of log d plus 1, where d is the distance between your in rank between your last access and your current access. So, for example, if you're trying to access all the nodes of the tree in order, d is always going to be 1, and this is only going to cost you constant time per operation rather than logarithmic time. Another case where splay trees work well is if you have a tendency to access nodes that you've accessed recently. There you can show what's known as the working set bound. The cost of accessing a node, n, is O of log of t plus 1, where t is the amount of time, the number of steps that have elapsed since you last accessed n. And this is also very nice. In fact, there's what's known as the dynamic optimality conjecture. This says that if you have any sequence of binary search tree operations, inserts, deletes, finds, etc., and you say how long does it take a splay tree to perform that sequence of operations, and then you compare that to the best possible binary search tree for that sequence, possibly something that's been carefully optimized to do that sequence of operations very, very well. The conjecture is that the splay tree does worse by at most a constant factor. And this says that if you have any sequence of inputs that you expect you can do better on than random, you might want to use a splay tree because it might already do that. So, in summary, splay trees are sort of an alternative to AVL trees, another way to do this sort of binary search tree data structure. They have some advantages. They're easy to implement. They're also O of log n, amortized time per operation. And in fact, splay trees can be much better if the queries that you're making have some sort of structure to them. So that's it for splay trees and for, I guess, this module and the course for that matter. I hope you enjoyed the course and learned a lot, and I hope you'll see us in our next module.